ജോയിൻ ചെയ്ത് നോക്കാം. ഈ മാറിയെല്ലാം ജോയിൻ ചെയ്തിട്ടുണ്ടല്ലോ. ഒന്ന് വിളിച്ച് ജയകുമാരൻ നമ്പർ എടുത്തൊന്ന് വിളിച്ചു തൊണ്ടോ ഒന്നിട്ട് നോക്കട്ടെ. സാറിന് HOD എന്നുണ്ടോ നടക്കുന്നത്. ഹലോ ഹലോ ജയകുമാർ.
Good morning, sir.
Good morning. Good morning. Good morning. I'm waiting for Professor Jayagumar. I have contacted through WhatsApp, but he mentioned that he already joined, but not here in this group. Sebastian is here.
Just send the link once again.
Okay.
So there are a bit confusion. ഏത് ലിങ്ക് എടുക്കണ്ടെന്നുള്ള സംശയം
KUP clear ആണ്.
അതെ എന്നാലും
Okay. Okay. Now we are okay. Let us start this session. Good morning, everybody. Good morning, Professor Hira. Professor, hello. Today, now it is time to start the program. Today we have in this venue, in the first session is on distribution theory, and we have 2 invited speakers and 4 contributory speakers. The first invited speaker is Professor K. Jayagumar. He is the professor and head of the Department of Statistics, University of Calicut, and he is also an alumni of our department, Kerala University, our Department of Statistics. And he is our prestigious alumni. In fact, he has several credits. I'm not extending all those things. Anyway, he is an expert in the area of distribution theory, time series analysis, stochastic modeling, and some other related areas too. And he has published several articles and produced more than 10 PhDs, and also he is the prestigious Jan Tinbergen awardee, and several things are there. I'm not extending too much. I invite Professor Jayagumar to carry over, please, to this session, and please take care of the. Please, we are waiting for your nice talk.
Thank you, Professor Sadish, for your nice introduction. So first of all, I congratulate the ISPS and the Department of Statistics for giving me an opportunity for this one. And let me go to my presentation.
No, it is. It is okay. It is okay.
It is on some generalization of the well-known Gomez distribution. So we are looking for the generalizations of the Gomez distribution that arises the distribution of random maxima or random minima. So before going into the details, I will first explain some of the basic aspects of this one, and then I will go to my presentation. So as we all know, there is recently a number of distributions are coming into the literature, and the question arises whether some such models are necessary or not. So let me try to answer this question. And so it demanded the introduction of a variety of probability models for the assessment and proper decision making, as all of us know. And it is highly essential to introduce useful probability models for better exploration of real life phenomena. And so let me look for the history of statistics, that is the history of Gomez distribution. Gomez distribution was introduced in 1825 in the journal Philosophical Transactions of the Royal Society by Gomez, which provides a statistical formulation of the Gomez life mortality. So in fact, he has noted that the age-specific mortality rates increased exponentially with age over much of our adult lifespan. So that is, or in other words, the hazard rate is in fact exponentially increasing. So we can see that that assumption may not be true in most of the situations, and as such, we all expect that some modifications are appeared in the literature. So many generalizations of the Gomez distributions have came into the literature, starting from his work in 1825, and I may list some of the generalizations. The first generalization was by Meckham in a paper which appeared in the Assurance Magazine and Journal of Institute of Actuaries in the year 1860, in which he has introduced the well-known Gomez-Meckham distribution. And you can see that after a century or so, not much work on this Gomez distribution has done, especially concentrating on some generalizations and so on. But the inferential aspect and other works have been done in the literature. So since my talk is mainly on the distributions and its generalizations, Elgore et al. In 2013, in applied mathematical modeling, introduced the generalized Gomez distribution and also some other generalizations are appeared in 2014, 2017, weighted Gomez, and also transmitted generalized Gomez and Marshall-Olkin Gomez distribution, and introduced the exponentiated generalized extended Gomez distribution. These are all some of the generalizations of the Gomez distribution that appeared in the literature so far. And in a paper by Tahir and Cordero, they have in fact considered why we are looking for the additional parameters for existing distribution, because it may make the system more complex, and whether you are getting any additional information by introducing that parameter, is it necessary or not, whether they have addressed that problem. So and as I have already told, that is often introducing extra parameter brings more flexibility to a class of distribution functions, and it can be very useful for data analysis purpose. And one of the such method is by compounding approach, and this compounding approach is in fact compounding the continuous random variable using some discrete models, mainly the well-known discrete distributions such as geometry, Poisson, logarithmic binomial, negative binomial, discrete, Pythagorean, etc. So with the continuous lifetime models, you can compound it, that is, you can find the random sums of random variables, and there are situations in which one may come across the random sums of random variables, and which is you can in fact see with the book by Kusubuski and Klebanov and so on, which in fact is in fact titled by random summation and its applications. And there is a book by Korolov on random summation. So now we are looking for the distribution of random minimum. So the basic idea of introducing compound models of the families of a lifetime in a system with n components and the positive continuous random variable xi can be denoted by the non-negative random variable y, which is in fact the minimum of x1, x2, etc. xn, or z is equal to maximum x2, x1, x2, etc. xn, where we may have to model the situation. We may have to model a series system or a parallel system. So based on our idea of modeling the series system or parallel system, we may come across the random, that is in fact the random minimum. So it is in fact well known in the literature. So I'm not looking for into the details of it. So if I may have y as the minimum of x1, x2, etc. xn, where my xi's are IID random variables and n is a continuous, n is a discrete random variable which is independent of n is a discrete random variable which is independent of xi's, then the distribution of the random variable y is given by equation number 1. Similarly, you can look for the maximum. And if n is the discrete random variable, in general, I am taking it as the truncated Poisson random variable because I am taking it as the truncated Poisson since my random variable in fact takes the values from 1 to 1 onwards. So that I am looking for the truncated random Poisson power series random variable which is truncated at 0. So that it will the PMF will take the form an theta raised to n by f theta minus a naught, where n greater than 0 and theta greater than 0. So that is the compound class which I may get using the power series distribution. This is the truncated power series random variable, and you know that the PGF of n is given by equation 3, and automatically the distribution function of this is in equation 2. It will turn out to be the distribution function. You may be able to evaluate it using the PGF. That is, you have when we simplify it, we will get it is the PGF evaluated at the point f of z. That is, it is in fact turn out to be gz is equal to f z theta minus a naught by f theta a naught. So that is what we will get. And if I may assume that my n is a logarithmic series random variable with Pm of as probability that n is equal to n, which is equal to p raised to n by that, then the PGF of n we know that it is given by equation number 5, that is ln of 1 minus ps by ln of 1 minus p, and the corresponding distribution of the random maximum will turn out to be ln of 1 minus p fz by ln of 1 minus p, and I will talk of the situation where I am replacing my fz by Gomez distribution. So which is useful for modeling the systems of parallel nature that I have already described. And other works in this direction are in the distributions of random minimum, which is appeared in a paper by Narada, myself, and Ristik, which appeared in Journal of Statistical Computation Simulation, where we have considered the distribution of random minimum, where this is the situation where the random minimum where I am taking my n as the truncated negative binomial random variables, and we have given sufficient notification for why we have taken the truncated negative binomial random variable as the compounding variable in that situation in that paper. So if I may take un as minimum of x1, x2, etc. xn, And if I may denote G bar as the survival function of UN, so by using the truncated negative binomial random variable, I will get a class of distributions that is G bar X, which is given by the survival function thus. So you will get the generalizations of F by putting Fx as the Gomez distribution in equation number 8, and you can see that whenever theta is equal to 1 and gamma tends to 1, the models F bar and G, that is the F and G, that is your X and UN, that will coincide. That is, in fact, you may be able to see that it is a generalization of the F bar. And using that idea, we have introduced the generalization of uniform distribution. So that is a paper which appeared in 2016 Statistica. So where we have replaced by this Fx by the distribution function of uniform random variable. So if I am taking the distribution function of the uniform random variable, you can see that it is Fx is simply x, and so that your G bar x will turn out to be this one, that is gamma raised to theta by 1 minus gamma raised to theta, gamma plus 1 minus gamma into x raised to minus theta minus 1, and you can see that whenever theta is 1 and gamma tends to 1, it will in fact turn out to be the usual uniform distribution. So that is the generalization of the uniform distribution that is in fact available in the literature. That is we have introduced this, and you can see the densities and other properties of it, and you can see that so. Now let me turn out to be. So I have described 3 situations where we may be able to define the generalizations of the random variables. So I am looking for the minimum of x1, x2, etc. xn, where n is in one situation I am taking it as logarithmic series distribution, other it is the truncated negative binomial, and then other one I am making use of with the generalized uniform that we have introduced. So before going that, so let me introduce some basic aspects of the Gomez distribution. The Gomez distribution all are familiar with, that is even the students are familiar in their classrooms. So the probability density function, for the sake of completeness, let me just give a brief note on the Gomez law. That is, the probability density function is given by equation 11, and the hazard rate, you can see that it is exponentially increasing. That is, as I have already told, and the form is true. And this the Gomez distribution is applied in various contexts of mortality studies and lifetime analysis. And one of this one is that is Windsor in 1932 utilized the Gomez curve as a growth curve. You can see that you may be able to take it as a growth curve. And the Gomez equation also played a fundamental role in laying foundation for actuarial science, which influence the price of life insurances and annuities. And another the work in that area is by Blossom and Rover, and also they have applied the Gomez curve in duration analysis. And this is in fact the structure of the PDF, and this is the structure of the hazard rate that you can see that the hazard rate is increasing. So now generalization, you can see that the Gomez and uniform are connected through this equation 13. So this is the transformation from uniform, that is the usual simulation procedure. We will take that is our y is uniform 0, 1, and you can replace that. Then you will get your x as the Gomez random variable from the equation 30. From the equation 30. So if I may replace y by generalized uniform random variable, so automatically I may give rise to a generalization of x. The random variable, it may be a generalization of the Gomez random variable. So what I may try here is, I may replace this my y by the generalized uniform that we have introduced into 2016, and we will look for what is the resulting x. So that is what we are looking at now. So you can see that the corresponding density function is of this form, and you can see that whenever this is a distribution with already you have two parameters a and b. Additionally, you have two more parameters gamma and theta, and so that it may makes the model complicated. And you can see that the complicated model may be of use provided that it has real life applications and the estimation of it may be so easy. Otherwise, it may not be of no use rather than the mathematical curiosity. So let me look for some properties of the model. So you can see that as I have already told, whenever your gamma theta is 1 and gamma tends to 1, the distribution of x reduces to the Gomez distribution. And you can see that the density has x tends to infinity, the density tends to 0, and as x tends to 0, it has this gamma tends to 1. And the distribution is both a unimodal and positively skewed.
Hello?
Hello?
There are 2-3 minutes remains.
Okay, I will go in. The distribution is unimodal and positively skewed, and these are the other properties of it, and these are the resulting density from the forms of the density. So you can see that, and this is the distribution function. This is the hazard rate function. You can see that by this one, you can see that the hazard rate is in fact it is of not necessarily of monotone nature. It may possess the non-monotone nature, which may be more realistic as compared to the increasing nature of the hazard rate. That is in fact one of the motivation for introducing this distribution. So you can see that it is of the bathtub shape, and you may get so many other shapes corresponding to the distribution, which we may be able to prove using the Laplace's theorem and so on. And these are some other properties. I am not looking for it because of the lack of time. And we may be able to generate it so easily. And one of the important properties is the characterization result. So based on the function, which I can write like this one, that is based on the truncated moments, I may be able to characterize the distribution of the new generalized Gomez distribution based on the Glancel's theorem, and we will get a number of results based on this. That is, you can see that a continuous random variable, let x be a continuous random variable, and you have your q1 and q2 are given by these equations. These are your q1 and q2, and if we have q1 and q2, and if q1 and q2 is this form, we can see that the distribution is Gomez, and Gomez also is true. Also, based on the hazard rate, if the hazard rate satisfies the differential equation, you can see that the corresponding random variable is Gomez and NDC, and new generalized Gomez and so on. And also, this result is also hold in terms of the proposition 3, holds in terms of the generalized reverse the hazard rate. And now these are, then you may be able to look for the limited distributions of x strings. That is another area one may be interested in. So if we are looking for the distributions of x strings, you have the well-known result, which is one may be able to see in the paper by Arnold 1992, and we can see that for the distribution of minimum or the smallest order statistic, we have this result. And if I may look for the Gomez distribution, you can have let xm be the smallest order statistics. Then you can see that limit n tends to infinity. Probability of this one is this. The Weibel type, if and only if this result holds, and it also possesses the stochastic order relations and you can see that if your NGC has the parameters where gamma 1 and gamma 2 are in fact ordered in such a way that gamma 1 is greater than gamma 2, then the corresponding random variables satisfies the likelihood ratio property, and also you can find the estimates based on the MLEs. We have considered the MLE method of least squares, weighted least squares, Kramer-Warmers estimators, and we have considered the other generalizations, and then we have just compared the performance, and we have seen that the distribution fitted well. And some more investigations of this is still continuing. With that, let me stop.
Thank you, Professor Devkumar. In fact, a very nice talk. Whether anyone has any, if it is serious, you can allow one question. Anyone has? Okay, I think let us go to the next speaker. Thank you, Dr. Devkumar, for your nice presentation. Thank you so much for concluding in time. Now we have Dr. Sebastian George. Is also, in fact, an alumni of our Department of Statistics, University of Kerala, and presently the head of the Department of Statistical Sciences of Kannur University. And he is a very active researcher, and he has produced more than 8 PhDs and several publications. Several publications to his credit, and he is an expert in several areas of, especially in multivariate statistical methods, Bayesian inference as well as classical inference, SQC, etc., statistical quantitative node, etc. I would, on behalf of the Indian Society for Probability and Statistics, I invite you, Dr. Sebastian, for your talk. Please.
Thank you, Professor Sadish Kumar, for the nice introduction. I am thankful to all of his bearers of ISPS for inviting me, for giving me this opportunity to present my recent work, especially Professor Balakrishna, Professor Sadish Kumar, and all. Well, today, let me take my presentation. This. 1 minute, I will take my.
Okay.
Right. Yeah, my topic is review on log symmetric and reciprocal symmetric distributions. In fact, myself and this is actually a joint work with Professor Joby Kejos and Dr. Thomas Xavier of my department. And this is actually, this problem came into my mind or our team when we analyzed the data related to the Bitcoin returns. And in fact, we had considered a few distributions to deal with distributions with a heavy tail or with a high volatility. So I will just review that kind of distributions that myself and my students considered. And then I will switch over my talk to the concept of what we call the R-symmetric distributions. So the ordinary symmetric distributions we know, the distributions like normal, Laplace, Cauchy, etc. And you know, if in terms of the probability density functions, you know, if f of x plus mu is equal to f of mu minus x for every x in R, we will be saying that the distribution is ordinary symmetric. Or in terms of random variable, in the standard case, if x and minus x are similarly distributed. Now, this concept, of course, we can do it in terms of logarithmic scale. So we will be saying that a probability distribution is log symmetric if the probability density function satisfies this condition. Or in other words, if provided x is a positive random variable, but here you don't have a restriction like that. So you'll be saying that it is log symmetric if x upon delta, that is distributed as delta upon x. And you can see that this log symmetry, you can of course talk in terms of ordinary symmetric distribution, because if you take the logarithm of on both sides, then you can see that the log x minus delta, that is distributed as log delta minus log x. So it is more or less similar to the ordinary symmetric distributions. But the log symmetric distributions plays a very important role. The well-known examples of log symmetric distributions are log normal distribution, log Laplace distribution, or if you take the logarithm of any symmetric distribution, then you will be getting essentially a log symmetric distribution. That is, if x is a standard symmetric distribution, I mean symmetric around 0, ordinary symmetric. So if you take logarithm of, if x is a positive random variable, the log x will be essentially symmetric distributions. That is what happens in the case of log normal and log Laplace distributions. And you can see that in many situations we will be dealing with the ratio of two random variables. You can see that if you have IAD non-negative random variables, then the ratio of IAD random variable is essentially following a log symmetric distribution. So you can say that for the log symmetric distribution, you have the advantage that your delta would be the median of the distribution according to the earlier definition. And another thing is that you can easily define the quantile function. The quantile function f inverse and the hazard function hx of log symmetric distribution will satisfy this particular property. So if you, in the first case, if you put u is equal to half, you can see your median of the distribution is essentially delta. Or if you consider the standard distributions or the exponential versions of Cauchy distribution or normal distribution, that is, if x follows Cauchy, e raised to x is a log symmetric distribution. And you can see that it's you can see in that case the median of that distribution is essentially 1. And Sebastian and Preeti generalized the concept of log symmetry to the class of distributions with the support R. And it can be shown that the ratio of two IAD random variables, just like the standard result, like ratio to normal distribution is Cauchy. It has also the property that if x is Cauchy, then 1 by x is Cauchy. There are many other distributions. Of course, one example is F distribution with the degrees of freedom equal, n1 equal to n2. So similarly, if you have any symmetric distribution, symmetric around 0, if you have two independent random variables, IAD random variables, if you take the ratio, its distribution will satisfy the property that x is distributed as 1 by x. And so, if you consider the class of such distribution, its advantage is that you can easily compute its quantiles. Remember, its mean need not exist, and most often, if the probability density function of x1 has a non-zero quantity f0, or if f0 is greater than 0, and most often the mean may not exist, but the median would be mu. And moreover, you have another interesting property that the first quantile would be mu minus sigma, and the third quantile would be mu plus sigma, or you have probability of mod x minus mu less than sigma, that is equal to probability of modulus of x minus mu greater than sigma, which would be equal to half. So these are the distribution having these particular interesting properties. So if you the advantage is that if you want to estimate mu and sigma, you can of course use either Q1, Q3 or the order statistics. And moreover, you have a because of the symmetric structure, you can do that. And now we are basically introducing another type of distribution. It was introduced by Mutolkar and Wang in 2007. That is what we call it as R-symmetric distributions. Earlier, we were talking about the log-symmetric distributions, and it has a property that x is distributed as 1 by x or x by delta, distributed as delta upon x. But here, what we do is that we will be saying that is R-symmetric if f theta x is equal to f theta given x. I'm sorry, here it is for every x greater than 0 and some theta greater than 0. Now, this kind of distributions exist. A number of distributions you can point out. In fact, Chaube, Mudolkar, and Jones, they are giving a construction of this type of distribution. And that is given in this theorem. If Gx is the PDF of a symmetric random variable x defined on R, that is g of x is equal to g of minus x for all x in R, that is symmetric around 0, then f of x is equal to twice g of x minus 1 by x, x greater than 0, is an R-symmetric density, and conversely, any R-symmetric density f gives rise to an ordinary symmetric G on R through Gx is equal to Gx in that particular form. So this essentially established the connection between the R-symmetric distribution and ordinary symmetric distributions. So from an ordinary symmetric distribution, you can consider R-symmetric distribution and conversely also. And this gives the connection between log-symmetric distribution, that was again these or this. An R-symmetric random variable x can be expressed as x is equal to u times maximum of z upon 1 by z plus 1 minus u times minimum of z1 by z in terms of a uniform 0-1 random variable u and an independent log-symmetric random variable z. So this gives the connection between R-symmetric and log-symmetric. So you can see that these distributions are essentially closely related. But you can see R-symmetric has several important properties, especially for modeling data with a heavy tail nature. That is what we are essentially dealing with here. Now, for dealing with heavy tail distribution, Sebastian and Dace introduced a subfamily of asymmetric Laplace models known as Escher transform Laplace models. In fact, it is a subfamily of the family of probability distribution introduced by several others and well studied by Kosovoski et al. Asymmetric Laplace distribution. But the advantage of this model, of course, this is a standard model. You can make into a location scale family of distributions also. But you can see that the assured parameter theta is in -1 to n. This gives a number of important interesting distributions that can model both, exponential tail distribution and the distributions having high variance also. They need not be. It will not, the variance will be existing, but the variance may be very high according as the value of the parameter theta. If value of theta is nearer to 1 or -1, then you can see that the distribution will have a high variance. If theta is equal to 0, then it reduces to the usual Laplace distribution. And the advantage of this family is that this is a subclass of one parameter exponential family. You can easily obtain the complete minimal sufficient statistics, and you can obtain estimate of theta easily. So that is not the case of general asymmetric Laplace distribution. You can see always there is a discontinuity at some one point where the mode is coming. But here, this distribution is so smooth, so you can carry out the analysis. You can use it for modeling a number of situations. Typically, we have considered that in the context of process capability analysis, for dealing with micro array data, and Days and Sebastian in 2013 we considered it for time series analysis also. Now the CDF corresponding to an exponentially an assured transform Laplace distribution has this particular form. So you can obtain the quantile function. You have expectation of x is this one, and variance of is equal to 1 plus theta squared by 1 minus theta square. So when theta is nearer to -1 or +1, you have high variance. So in several situations, that is a flexible model to deal with those distributions having heavy tail, but still the variance is finite. And you can obtain the quantile function also here. So even if you can, in fact, this distribution is quite useful for the study of quantile regression also. These are the shape of this distribution. You have a variety of probability density functions, symmetric. Of course, the symmetric is the Laplace distribution. Negatively skewed, positively skewed, and having somewhat high kurtosis. Now, we introduce a typical R-symmetric distribution, and it is essentially closely connected with the Escher transformed Laplace distribution. One side is essentially a Pareto distribution, the other one is a power distribution. So the form of the distribution is f of x is equal to 1 by nu alpha square minus 1 by 2 alpha x by nu raised to sine of delta. This is in fact nu. I'm sorry, here instead of delta we have nu here. Nu minus x times alpha, where both nu and alpha are positive. Now the densities in this class has a distinct dense shape, and their non-complex nature among other properties give them a number of modeling advantages. And you see the structure of this one. Basically, all these distributions are positively skewed. This is what happens in many situations when we are dealing with the financial data in which, with a growing tendency. Of course, it may come down, but most of the returns are not most, but probably a positive tendency. So some plots of the density function given here, this is for different value of alpha and mu. Now you can see that it's expectation of x power h is equal to this one, or expectation of x by mu is this quantity for all alpha greater than h plus 1. And mean is mu times alpha square minus 1. upon alpha squared by 4, and variance is this one. Now, this is actually an important property of reciprocal symmetry. In fact, expectation of x by nu upon h, that is equal to expectation of x by nu, the whole raised to minus h plus 2. So you can see that expectation of, if in the standard form when nu is equal to 1, expectation of x is equal to expectation of x raised to minus 2. So this is similar to the log symmetric distributions, a closed form expression for all the moments of the random variable if it follows a log symmetric distribution like log normal distribution is closely associated with its moment generating function. And similar to that, for the R symmetric distribution, you have this one, and this, of course, allow you to obtain estimate of nu and alpha. And you can easily obtain the moment estimates. Of course, you can obtain the maximal likelihood estimates also, but as the starting value, you can use this as the estimates also. So that way, it is useful. And another thing is that in the earlier setup, this is essentially belonging to an for non-new. And in many situations, especially when we are dealing with the returns, you can see that your delta is essentially one in that we will see by means of an example. And in that case, I mean, nu is 1. So, so basically what happens is that this family will be an exponential family, and there is no discontinuity for the probability density function at nu, as we are seeing in many other situations. And that is not only that thing, it's useful to deal with many important financial things. Basically we considered an application that is Bitcoin data. As you know, that is a new trend among in this century. People are using Bitcoin. Bitcoin is used to be a new kind of money and a version of electronic cash that allows online payments to be sent directly from one party to another without going through a financial institution. We use the historical daily adjusted closing price of Bitcoin in US dollars from September 17, 2014 to September 1, 2021 from Yahoo Finance. A total of 2,533 observations are considered for the analysis after removing the missing values. The time series plot looks like this. See, it was slowly increasing, then coming down. But of course, it has a increasing trend. And for such kind of data, if you, for example, the returns of the prices is obtained and the summary statistics is given there, so you can see that more or less the median is 1.0020. So if you use the R symmetric distribution, for the R symmetric distribution, the median is nothing but nu, but that nu is approximately equal to 1.121. Yeah.
Hello, 5 more minutes. Okay?
Yeah, I will finish in time. No problem. So this is the graph of the Bitcoin data. We considered, because they were nu is nearly 1, so we took nu is equal to 1 and obtained the estimate of alpha as the MLE of alpha as 39.25. The histogram of this data is this one. So you can see that it is essentially a positively skewed data. But still its median is near around 1. We tried it with several distributions like log normal distribution, and then some other asymmetric Laplace distributions, Weibull distribution also. But all these distributions will give you a very high BIC or AIC. So these are some of the distributions that we have considered. One is R symmetric distribution, the other one is log normal, Weibull distribution, gamma, and the other one is generalized beta distribution. And many people are suggesting for such kind of skew distribution, generalized beta type distribution is a good candidate. But still, we could see that it's a very nice fit for such kind of data. And our estimate MLA of alpha is 33.9, 19, and AIC and BAC bots very, very small. It's not like it's comparatively, when you compare it with the log normal or DP2 distribution, it's a very nice fit. And with this, I will finish it off here. I could not give the complete reference here. I have given some of references in which basically I am involved. Okay.
Okay, thank you.
Thank you, sir.
Dr. Sebastian, for your nice presentation. It is possible for to pose one or two questions if needed. Anyone has any query, please, or any comments, suggestions? One question only needed.
Yeah, please.
Anyone? Okay, and there is a chance to contact you or interact with you via email and other media, online media.
Thank you very much.
Okay. Let us give a big clap to Dr. Sebastian and Dr. Jayakumar for their nice talks in the invited talks. Now we have four contributory speakers. We have to first of all, I would like to check whether all these four contributory speakers are there in this group. Rashid Genia, please raise your hands. That facility you can utilize. While I'm calling, please raise your hands in the using that Google Meet facility. Yeah. Rashid Genia, whether he is not. What about Rashid Genia? What about Ishar Khan? Ishar Khan. Amita Susan Anian. Okay, very good. Amita is here. Yeah. What about Sagaya Christie?
Yes.
Yes, okay. Other persons, once again, Genia, Rashid Genia, Ishar Khan, Muhammad Ishar Khan, Muhammad Ishar Khan. Anyway, let us start our talk, your presentations. In fact, for contributory speakers, 15 minutes is allotted, in which 12 minutes for their presentation and 3 minutes, or 12 or 13 minutes you can take, and 2 minutes for discussion if needed. Or since the other persons are not here in this group, we can give some more time, or 2-3 minutes. That's enough. Let me I invite, I think the first person mentioned here is Anita Susan Anian.
Shall I start,
Please.
sir?
Okay. Anita, okay. Susan, okay. Please.
Good morning. My name is Anita Sosinanian, doing research under the guidance of Dr. Dace George. Today I'm going to present about alpha logarithm transform Pareto distribution. The overview of my presentation is shown here. In recent years, an impressive array of new statistical distributions has been unearthed by statisticians. The necessity to develop an extended class of classical distributions is even more in areas such as survivor data analysis, finance and risk modeling, insurance modeling, rare events, etc. Since 1980, the focus of statisticians to generate a new distribution is adding parameter to a classical distribution or combining existing distributions. This addition of parameters has been proved useful in exploring tail properties and also for improving the goodness of fit of the family under study. Alpha logarithmic family of distributions. If f of x is an absolute continuous CDF with corresponding PDF f of x, in 2012, Papas et al. Introduced a new family of distribution with the following CDF and PDF respectively. The CDF and PDF are given in equation 1 and 2, where capital G of x is the baseline CDF. It has to be noted that when alpha is equal to 2, the CDF and PDF in equation 1 and 2 reduce to the CDF and PDF of the logarithmic transform method proposed by Maurya et al. In 2016. In 2017, they et al. Used the method of Papas et al. 2012 to introduce a new generalization of the generalized exponential distribution and referred to as alpha logarithmic transform generalized exponential distribution. In 2018, Nasser et al. Introduced a new three-parameter generalization of the Weibull distribution referred to as alpha logarithmic transform Weibull distribution. In 2019, they et al. Proposed a new lifetime model called the alpha logarithmic transform Fresher distribution as an extension of the Fresher distribution. We know that Pareto distribution is a well-known distribution used to model heavy-tail phenomena. And Pareto distribution is successfully used by the projection of losses in an insurance company, liability experience of hospitals, etc. In the recent past, many generalizations of the Pareto distribution have been attempted by the researchers. And the notable among them are beta Pareto, Kumaraswamy transmuted Pareto distribution, cubic transmuted Pareto distribution, and MG exponential Pareto distribution in 2020. If X follows Pareto distribution with parameters lambda and beta, then the probability density function and the CDF associated to X are given by equation number 3, where lambda and beta are the scale and shape parameters respectively. Here we introduce a new lifetime model called the ALTP distribution as an extension of the Pareto distribution using the similar idea proposed by Papas et al. 2012. The CDF of ALTP distribution is given in equation number 4. The corresponding PDF and hazard rate function are given in equation number 5 and equation number 6 respectively. When alpha tends to 1, the PDF of ALTP distribution reduces to the PDF of Pareto distribution. Using Maclaurin series and binomial expansion, the PDF of ALTP distribution can be written in the following mixture representation. This is the PDF plot of ALTP distribution. Mathematical properties. The quantile function is given in equation number 7. The measure of skewness S based on quantiles defined by Galton is given in equation number 8. And the measure of kurtosis defined by Moose is defined in equation number 9. The rth ordinary moment of ALTP distribution is given in equation number 10. And the incomplete moments is given in equation number 11. Let mu be the mean and m be the median of the LTP distribution. The mean deviations above the mean and above the median can be calculated respectively as d of mu and d of capital M. And the moment generating function is given in equation given as mx of t. Order statistics, the CDF and the PDF of the jth order statistic for the LTP distribution are given by equation number 12. Methods of estimation. We describe two methods of estimation for estimating the unknown parameters of the LTP distribution. The methods are maximal likelihood estimation and Bayesian estimation. In maximal likelihood estimation, let x1, x2, xn be a random sample from the LTP distribution with unknown parameter theta. Then the log likelihood function is given in equation number 13. From equation number 14 and 15, we can see that it's a nonlinear system of equation. So by applying a suitable numerical method like Norton-Raphson, we obtain the MLS of alpha and beta. Since x element of lambda to infinity, the maximal likelihood estimator of lambda is the first order statistic x01. All the computations are performed by using our software. Bayesian estimation. We obtain the Bayesian estimates of the unknown parameters of a model underscored error loss function using the non-informative prior Jeffreys as priors for these parameters. The John prior, in case of Jeffreys prior, is written as pi of alpha beta lambda proportional to 1 by alpha beta lambda. The John Poster distribution is given in equation number 16. We can see that the John-Poster distribution of the parameters takes a ratio form of two integrals, which cannot be solved analytically. So we use the approach developed by Lindley in 1918. So we can approximate these base estimates into a form containing no integrals. Therefore, the base estimate of the unknown parameter underscored error loss function are alpha cap b, beta cap b, and lambda cap b. The formula for obtaining VI, A, B, C are shown here. And rho is the log of John prior distribution. Simulation study. A Monte Carlo simulation study is conducted to compare the performance of the different estimators of the unknown parameters for the ALTP distribution. The performance of the different estimators are evaluated in terms of the mean square errors. And we generate 1,000 samples of the LTP distribution where n is equal to 20, 50, 100, and 200. And by choosing lambda as 1 and 2, beta as 0.5 and 2.5, and alpha as 0.5 and 2.5. The average values of the estimates and their corresponding MSEs are obtained and displayed in tables 1 to 4. Conclusion, we observe that all the estimates show the property of consistency. That is, the MSEs decrease as sample size increase. The research shows that Bayesian estimation produces the best result for estimating the parameters in terms of MSEs in most of the cases. And this is the reference. Thank you.
Okay, thank you, Anita. You completed your presentation before time, and if there is any questions, you can please. It is open for the floor. Anyone has to raise any questions or comments or suggestions, please? Once again, I would like to know whether Rashid Khani, Dr. Rashid Khania and Dr. Muhammad Isar Khan were there in this group. If they are in this group, please raise their hand, please. Anyone, please? Okay, before starting the next speaker, going to next speaker, if they are here, it is better to give their to use their chance. Otherwise, we can give maximum time to the next speaker. That's why. More time to the next speaker, if needed. Hello, what about whether Dr. Rashid and Dr. Khan?
That's it. Hello.
Hello.
Sir, Shali present.
Okay, wait. Okay, once again, if there is no question, to Anita and the other people are not here in this group, let us. I'm waiting for their response. If no one is there, I invite Dr. Sagaya Christie, please.
Yeah, okay, sir.
Okay.
So can you receive the slide, sir?
Not yet. Now it is coming.
Okay, sir, okay.
But we can see your laptop only now. Yeah, now it is okay.
It's visible, sir, now?
Yeah, now it is visible. You can make it full screen.
Yeah.
Okay, very good. Very fine.
Okay, sir. Good morning to one and all present here. Hi, I am Saya Christie Beulah, Research Scholar of Presidency College under the guidance of Dr. R.K. Radha ma'am. I have chosen the paper was Vengat distribution and its applications. The introduction of this is the inverse gamma distribution is a two-parameter family of continuous distribution, which is the reciprocal of the gamma distribution. I have taken the reference for the Lera and Beckman in 2016, introduced 5 different algorithms based on method of moments, maximum likelihood estimator, and full Bayesian estimation for learning the parameters of the inverse gamma distribution. The Salah et al. Study the general properties of the inverse gamma distribution. What is the probability density function of the inverse gamma distribution is given by f of x alpha comma theta, which is equal to theta to the power alpha gamma alpha x to the power of alpha minus 1 e to the power of minus theta divided by x. In this case, x is always greater than 0. The cumulative distribution function of inverse gamma distribution is whether the beta is greater than 0 as a scale parameter and the alpha is greater than 0 for the shape parameter. Then the function is given by what is that is f of x alpha comma theta, which is equal to the gamma of alpha comma theta divided by x divided by the gamma alpha. I have to take this is our equation 2. Then we'll move to the gamma of u comma v. The integral of v to infinity, the e to the power of minus 3, t u minus 1 dt. I have to take this is your equation 3. In this equation 3 is the upper incomplete gamma function and the gamma of mu comma 0, which is equal to gamma of mu. It is a complete gamma function. I have concluded my paper. The paper name is Venkat distribution. In this paper, an attempt has been made to obtain a new distribution for modeling lifetime data by considering a two-component mixture of an inverse gamma distribution having the shape parameters of 4 and the scale parameter is theta, and the inverse gamma distribution having the shape parameter is 5 and the scale parameter is theta with their mixing proportions. Then the probability density function of this proportion is a new one parameter of lifetime distribution. It is introduced as f of x comma theta, which is equal to theta power 5 divided by theta plus 1, then 1 divided by x to the power of 5 plus 1 divided by x to the power of 6 into e to the power of minus theta divided by x. In this case, we have to take in that x is always greater than 0 and the theta value is always greater than 0. So I have to take in this is the equation 4. Then this distribution is named as Venkat distribution. And this distribution it can be easily expressed as the mixture of the inverse gamma distribution. We have to take in that is 4 comma theta and inverse gamma is 5 comma theta. With that, the mixing proportion, whether the P is theta divided by theta plus 1 and 1 minus P is 1 by 1 theta plus 1 respectively. Then we have f of x comma theta, which is equal to, what is that? P of inverse gamma of 4 comma theta plus 1 minus P of inverse gamma of 5 comma theta. In this case, where P, which is equal to theta divided by theta plus 1, and the inverse gamma of 4 comma theta, which is equal to 1 divided by gamma of 4, t to the power of theta the power of 4, e to the power of minus theta x divided by x to the power of 4 plus 1. And another case is the inverse gamma distribution of 5 comma theta, which is equal to 1 divided by gamma 5, t to the power of 5, e to the power of minus theta x divided by the x to the power of 5 plus 1. Then the cumulative distribution function of this Venkat distribution is f of x, which is equal to theta power 5 divided by theta plus 1 for the gamma of 4 comma theta divided by x plus the gamma of 5 comma theta divided by x. Whether the x is always greater than 0 and the theta is always greater than 0, we have to take and that is the equation 5. From this Venkat distribution, the moments and related measures, the rth moment about the origin of Venkat distribution is mu r dash, which is equal to theta divided by theta plus 1, theta the power of r, the gamma of 4 minus r divided by the gamma of 4, plus 1 divided theta plus 1, theta to the power of r, the gamma of 5 minus r divided by gamma 5. So we have to take in the r value is 4 moments. What are the 4 moments is 1, 2, 3 and 4. So I have to take in, this is your equation 4. The first 4 moments about the Venkat distribution is mu 1 dash, which is equal to theta divided by theta plus 1, that is 4 theta plus 3 divided by 12 is the result for mu 1 dash, and mu 2 dash, which is equal to theta square divided by theta plus 1, 1 plus 2 theta divided by 2, 12 is the mu 2 dash. Then mu 3 dash, which is equal to theta 3 divided by theta plus 1, the 1 plus 4 theta divided by 24. Again move our mu 4 dash, which is equal to theta 4 divided by theta plus 1, 1 plus 4 theta divided by 24. Then the moments about the mean of Venkat distribution is, we have to get that value is mu 2, which is equal to theta square divided by 144 theta plus 1 the whole square. Then we'll get that is 2 theta plus 1 the minus of 4 theta plus 3 the whole square. So how to check on this mu theta equation is 7. Then mu 3, which is equal to theta cube divided by 864 theta plus 1 the whole cube. Then the values, bracket values is 36 theta plus 1 the whole square, 4 theta plus 1 minus 18 theta plus 1, 2 theta plus 1, 4 theta plus 3 plus 4 theta plus 3 the whole cube. This is the moment about mean of Venkat distribution mu 3. So I have to take and that is the equation 8. Then I have to find out the mu 4. So what is the value for the mu 4 is mu 4, which is equal to theta power 4 divided by 600912 theta plus 1 the whole power 4, 288 theta plus 1 cube, 4 theta plus 1 minus 64 theta plus 1 the whole square, 4 theta plus 1, 4 theta plus 3, plus 24 theta plus 1, 2 theta plus 1, 4 theta plus 3 the whole cube, whole square, minus 4 theta plus 3 the whole power 4. Then the coefficient of the variance of the Wenger distribution. So what is the coefficient of the variance of the Wenger distribution is, which is equal to sigma divided by mu dash, which is equal to root of theta of 2 theta plus 1 minus 4 theta plus 3 divided by 12 theta plus 1. This is the result. I have to get it in the coefficient of variation in the Wenger distribution. So I have to put that is here equation 9. Then the coefficient of skewness and kurtosis for the Wenger distribution is, the new distribution is beta 1, which is equal to, always we know the formula for mu 3 square divided by mu 2 cube, which is equal to, I will get it, 4 of 2 theta plus 1 the whole cube, theta plus 1 the whole cube, minus 4 theta plus 3 the whole power 5, divided by 1296 theta plus 1 the whole power 4, 4 theta plus 1 the whole square, minus 324 theta plus 1 the whole square, 2 theta plus 1 the whole square, 4 theta plus 1 the whole square, plus 4 theta plus 3 the whole cube. Then I have to find out the kurtosis of the Wenger distribution is beta 2, which is equal to mu 4 divided by mu 2 square, which is equal to 3 of 2 theta plus 1 square, theta plus 1 square minus 4 theta plus 3 the whole power 4, divided by 288 theta plus 1 the whole cube, 4 theta plus 1 minus 64 theta plus 1 square, 4 theta plus 1, 4 theta plus 3 plus 24 theta plus 1, 2 theta plus 1, 4 theta plus the whole square minus 4 theta plus 3 the whole power 4 have to taken, that is the equation 11. From this Wenger distribution, the maximum likelihood estimation is if x1, x2, etc., xn is a random variable from Wenger distribution of f of theta, then the likelihood and log likelihood functions are given. So what is the likelihood function is L of theta, which is equal to theta to the power of 5n divided by theta plus 1 the whole power n, e to the power minus theta divided by summation of I equal to 1 to n xi, the product of I equal to 1 to n, 1 divided by xi the power 5 plus 1 divided by xi the power 6. This is the likelihood function. Then the log likelihood function of this distribution is log L of theta, which is equal to 5n log theta, minus L log theta plus 1 minus theta divided by the summation of I equal to 1 to n xi plus summation of I equal to 1 to n, the log of 1 plus xi the power 5 plus 1 divided by xi the power 6. I have to take in that equation 9. From the maximum likelihood estimation of theta for the Wenger distribution is the solution of the equation is dou log L of theta divided by dou theta, which is equal to 0. By given the solution for the following quadratic equation, I will get it is theta square minus 4n square x bar minus 1 theta minus 5n square x bar. Then the simulation of the Wenger distribution is simulation study for estimating unknown parameters of Wenger distribution for different sample size was conducted. So what are the sample size we have to take, and that is the experiments were conducted according to run size K, which is equal to 10,000, and with the sample size N equal to, I have to taken 10, 25, 50, 100. So this is a small and moderate and large samples. Then the result was tabulated as follows. See the result, the summary of Wenger distribution when theta, which is equal to 0.5. So I have to take in the sample size 10, 20, 25, 50 and 100. So in the sample size, I have to using the R programming, I have to getting that answer for the mean is 0.14047, 0.13804, 0.13900, 0.13851. From the same sample size, we have to get it that median is 0.12601 and 0.12441, 0.12528 and 0.12569. Again, I have to get it the skewness and kurtosis is 2.85859 and 2.2227044 and 2.143836 and 2.083623. This is the skewness, and again I'll get the kurtosis is 29.94832, 12.5621 and 11.8523 and 11.1395. In the above table, what is the summary for the statistics of Wenger distribution is presented. It is inferred that there exists a positive skewness since the median value is less than median, and the positive kurtosis represents that the distribution is more peaked than the normal distribution. So also we have to find out the maximum likelihood estimation of the theta is 56.24 when the sample size n equal to 10. If the sample size is increases, the theta values is also increases. Then the maximum likelihood estimation of the table, I have to take that sample size and parameter estimator of theta value. See, 10, 25, 50 and 100 is the sample size, but the parameter value is 56.2446, 3490.13 and 1400.25, 5600.25. So the parameter of sample size means the estimated is also increased. The parameter estimates of theta is presented in the above table. So with the sample size to present small, medium and the large samples we have to taken. So the conclusion for this Wenger distribution and its application has been proposed. What is that is? It's moments based on measures including coefficients of variations, skewness and catalysis have been obtained. Their nature has been discussed through simultaneously. So the method of maximum likelihood estimation have been discussed for estimating its parameter. So what are the reference I have to follow for this is, I have to given that. Thank you.
Okay, thank you.
I have a few questions, Sadish.
Yeah. Okay, please.
One is your parameter theta is greater than 0. Am I right?
Yeah.
Theta greater than 0. You just check that your mean and that coefficient of variation in particular. I could see that expression. That can be negative some values of theta. That should not happen.
Okay, sir. Okay, sir.
That because theta is the mean should be positive because theta your random variable is also the real positive part x greater than 0. Am I right?
Yes, sir. Yes.
So that you have to doubly check. Second point is I have gone through the simulation studies and maximal likelihood estimation, and I could see that when the sample size changes, your maximal likelihood estimate changes. What is that? I cannot understand that one. The theta value, theta hat, in one case sample size 10, you are 56. In another case, sample size 25, your value is 300 or 3000, something like that. It is changing. It should not happen.
It's changed when it's happen. Whether I have to do the calculation, it will be changes only because I have to take in the sample size is 10 means the parameter value of theta value. I will get it that 56.2446. Again, I have to put the sample size is 25 means the value should come 3490.
No. That's what I'm telling. When you are simulating with some specific values, theta equal to 50 or theta equal to 100, your estimate should be close to that value. It cannot be changed like this. 56, 3000, 5000, something is something wrong in that part.
Okay, sir. By the way, sure, I will check it again. Okay.
Okay, Sadish.
Okay, very good. Thank you, sir. Any more comments or suggestions whether anyone has to support her with more comments or suggestions?
No, we want comment from Satish Kumar.
Yeah, please.
I want comment from you, sir. I am Venkat.
Hello, Professor.
Yeah. So I am asking you just give the comments. You want, please give your comments.
Yeah.
Chairman's comments.
In fact, what Professor Shankaran mentioned is correct because you have to.
Yeah, that's true.
That is a crucial point. I also noticed. In fact, while calculating the bias, etc., this bias should be reduced. Yeah, that.
You're absolutely correct. Absolutely correct. Okay, thank you.
Yeah. What about our other speakers? If whether anyone is here in this group? Once again, Ishar Khan is here. Hello, Khan.
Yes, Assalamu alaikum. Yes, I'm here.
Yeah, please.
Good morning, sir.
Good
morning, sir. How are you?
Now you are lucky because you have to spend whether your talk is here in this group.
Yes, I'm talking in this group, your group, sir. Satish, sir.
In the beginning, while I calling you, there is missing. That is why.
No, actually, sir, I am living abroad in Kingdom of Saudi Arabia. The time difference between here and India, 2.5 hours.
Okay.
Okay, that's why I'm extremely sorry to my yes.
Okay. What about Dr. Rashid Ghani? Rashid Ghani? Okay. Anyway, I invite Dr. Muhammad Issa Khan. Please,
okay,
please present your.
Okay.
Please note that we have I think now 11, 16. Okay. You can take 15 minutes for your presentation.
Okay, just 1 minute, sir. Let me just give an idea how I take this as a paper, and because Google is not our university, I am not much aware.
Okay, you can present your slides. Yeah.
Yes.
You please first go to in the bottom there, most probably in the bottom, there is a upward arrow.
Yes.
So before going to presentation, first you open your slides and minimize or put it in.
Okay, sir. Okay.
Then now you can click on that present now button. That is an upward arrow. Just to click on.
Okay. Just 1 minute. Just 1 minute. This is the your entire screen.
Yeah, entire screen you can take.
Okay, entire screen. Okay, sir.
You can click. Yeah. Then.
Yes. This is.
You just click on then the share button will be active. Just click on share.
Did you see? Can you see?
Now it is coming.
Okay, sir.
Okay, very good. Now you can go to your slides.
Okay. Thanks a lot.
Yeah.
Okay.
Yeah.
Now, very good morning, all of you. Can you see my slides, sir?
It is visible and it is good, but you can.
Okay. Thanks for your support, sir. Thanks for your support.
You can make it.
Yes. Just. Good morning, all of you. Myself, Muhammad Izhar Khan. I am presenting this work virtually from Saudi Arabia. Today my talk is the entitled paper, The Length Bias Powered Inverse Rayleigh Distribution with Applications. In this paper, a new distribution called length bias powered inverse Rayleigh distribution is introduced. Some statistical properties of the proposed distribution are derived. Method of maximum likelihood estimation is used for estimation of the parameters, and the proposed distributions also apply to real data set for illustrative purposes. Among the probability distribution, the Rayleigh distribution was the most commonly used distribution. The Rayleigh distribution was originally proposed in the field of equastrics and optics by the Lord Rayleigh. The Rayleigh distribution is originated from the two-parameter Weibull distribution, and it plays a key role in modeling, analyzing the life data such as life testing, diagnostic imaging, theory of communication, physical science, and so on. After this one, then the inverse Rayleigh distribution was introduced by Trier to an important model for lifetime analysis. What I studied some properties of the maximum likelihood of its scale parameters and applied in reliability and data analysis. In recent years, several extensions of probability distribution have been made to increase its applicability and flexibility. The power transformation technique has been first proposed by Box and Cox. One of the most important use of the PT techniques to develop new distribution out of well-known distribution by adding an additional parameter which gives several desirable properties and offers a more flexible model. The PT technique has been used in many statistical aspects. It can be shown by transformation of a random variable. If the random variable t has a Rayleigh distribution, then random variable x equals to 1 over t has the inverse Rayleigh distribution. I am talking about my distribution. Who introduced this one? Nashab introduced the power inverse Rayleigh distribution, which was published in the Pakistan Journal of Statistics, through the power transformation, which is take x is equal to t power 1 over alpha, and this is the given. Then the probability density function of power inverse Rayleigh distribution is given in 1, where alpha is a shape parameter and theta is a scale parameter. If you look equation number 1, if I put alpha equals to 1, then it is reduced to inverse relative distribution, and corresponding cumulative distribution function corresponding to 1, it will be given the 2, and this is the moments formula is given equation because I need in the further. In this talk, the outline of this paper is as follows. The length bias power inverse relative distribution is introduced in section 2 and study the structure shape properties of the probability density function, cumulative distribution function, reliability and hazard rate function. Section 3 discusses the different statistical properties of the proposed model, and section 4 with ends with the parameter estimation by method of maximum likelihood estimation. And our study is supported by the data analysis which is done in the section 5, and finally our article ends with the brief conclusion in section 6. Here just we are going to explain about the concept, the length bias power inverse relative distribution, because in the previous section I explained the power inverse relative distribution. Now the length bias. The statistical interpretation of length bias distribution was originally identified by Cox in the context of renewal theory. This situation refers to instances where the recorded observation cannot be considered as a random sample from the original distribution. This may occur due to non-observability of some events or damage caused to the original observation, resulting in the reduced value or adoption of a sampling procedure, which gives unequal chance to limits in the original. Various works are done to establish the relationship between original distribution and corresponding to the length bias form. Actually, in the length bias distribution, we are not going to allocate all the equal probability, and some of them the big, some of the small. This is unequal probability. A lot of the authors, we can see this is the reference which is given 70 to 20. Now the formation of the length bias power inverse distribution, let X be a random variable of power inverse relative distribution with PDF fx. Then this is the formula. Gx will be x fx over expected value of x is the PDF of length bias power inverse relative distribution. And we denoted is this is LBPI distribution with shape parameter alpha and scale parameter theta. And this corresponding probability density function of LBPR distribution is given equation 4. And cumulative distribution function is given equation 5, whereas the gamma x is the incomplete gamma function, and the reliability function is given equation 6. And this hazard rate function is given equation 7, and these are the some following plotters of the PDF and the CDF and the HRF and the reliability function, which is given. This is following figures for the different values of parameter. What we conclude from the figure graphs, the figure 1 can show the shape of the parameter of LBPI or distribution unimodal and positively scored. Also from the figure 4, if we can look, we can see here, in the certain place it is increasing and then after it is a decreasing, which is depicted in this picture. Well, then the section 3, we are going to explain this as derive the some statistical properties of our proposed distribution. Here in the section, we are going to explain this is the mean, median, mode, entropy, and all the things. Statistical properties of a distribution is explained here. This is the first theorem regarding the moments of a LBPR distribution, which is given the equation 8. And as we know, in the any continuous distribution, how can find the mean? This is the as usual practice. And substitution from 3 into 9, we can find our the desired result, which is given equation 8. And from this result, we can find it if I put R will be 1, it is the expected value of this is the mean, and this is the variance. And skewness and the kurtosis can be also calculated from this is this formula, and skewness and kurtosis. And as far as mode is concerned, as we all just we take the logarithm of the PDF and differentiate with the first time and equate equals to 0. Then by checking the second derivative and should be the less than negative, then we conclude from here the PDF of LBPR distribution, the maximum value as x equal to 1 over theta and power 1 over 12. And this is the unimodal. Therefore, the mode of this distribution. The second theorem discusses about the moment generative function of LBPR distribution, which is given in equation 10. And just we write the formula for any distribution, find the MXT as I write the formula and then make an exponential expansion and put the formula with the help of the equation 3 and put into 11. I found this one. In the following table, just we are going to see the some statistical measure. We calculate the some statistical measure of our proposed distribution, like the mean, variance, standard deviation, skewness, and the kurtosis, which can be seen here. This is the different value of alpha, mean, mode, variance, skewness, and the kurtosis. And this 3.2 section discuss about the measure of uncertainty. Here, just we discuss about the entropies. And in information theory is mathematical origin in entropy notion that is related to thermodynamic and statistical mechanics. Also, it has various fields of applications such as ecology, statistics, and quantum information. The entropy of random variable probability density function, the measure of variation of uncertainty of a system. A large value of entropy indicates the greater uncertainty in the data. Many entropies are available, but basically there are the two main entropy. This is the Renai and the Tercels entropy are as follows, which is given over the following Rx. This is for the Renai and this is for the Tercel. And this is the, after the calculation here I wrote this is the directrix value. Then another is inequality measures. We discuss about the Bonfori and the Lorentz curves because it is used in the economics, not in the economics, but also fields of the reliability and the demography, insurance and the medicine. And Bonfori and Lorentz curves are defined by this is the formula. From our proposed distribution, we can help using the formula, we can find this is the Bonfori and this is the Lorentz curves. The section 4 discuss about the estimation of parameters. Here I follow the maximum likelihood estimator for finding the unknown parameter. Just we take the likelihood of the proposed distribution, then again take the likelihood, and this is as usual. As usual, in the traditional method, we differentiate with respect to the parameters and equate equals to 0. Then we find this is equation 13 and 14, and this is the where xi(x) is given d over dx logarithm of gamma x. As far as the confidence interval is concerned, then I need this is asymptotic confidence bounds. In the section, we derive asymptotic confidence interval of these parameters where alpha is bigger than 0 and theta is bigger than 0, and the inverse and observed information matrix is given in equation 15. And these are the technique. Now, we are going to say our proposed distribution. How I are proposing our proposed distribution is superior to the other model. Just we have to take the some numerical results. If our distribution AIC, AICC, BIC, and other measures are less than the other adjacent distribution, then we say our proposed distribution is superior to the other models. To check this is the flexibility and applicability over the all length and inverse relative distribution. Just we took the two examples. This data set, one example is came from, this is the grass and clocks, which is the reference is 32, which is the consider 20 observation. And from this, just we calculate our this is the parameters, inverse relative distribution, powered inverse relative distribution, length bias inverse relative distribution, and this is the which one our proposed distribution is length bias powered inverse distribution. And if you see this is a corresponding, our this is the result is acceptable because it has a lower as compared to the AIC value, AICC value, and BIC and HQIC. It means our proposed distribution is superior to other previous model. From the table 2 show that LBPR distribution provides the best fit for the data set as it has lower AIC, AIC, and BIC and HQIC than other competitor models. Hence, we can conclude that LBPR distribution leads to better fit over the inverted relay, power inverted relay, and the length bias inverted relay distribution. The variance and covariance matrix is given, and the 95% confidence interval of alpha and beta is also given. And if we make a graph, then we find that the ML is a unique for the alpha and the beta. Now the second data set, this data set to reduce the time to failure of turbocharger of engine studies by Zhu et al. 33. Data is given. From this data, we can find this is the AIC, AICC, BIC, HQIC for the other four models, and inverse relay distribution, powered inverse relay distribution, length bias invert relay distribution, length bias powered inverse relay distribution. And we see our proposed distribution is superior to other because if the data is less than all the its value. And same the technique I here say from the table, if they see from the table, we observe this our proposed model is superior over the other model. Our proposed model is the best model. And the variance covariance matrix is given, and 95% interval is also given. Now this came to the conclusion part. This paper presents a new probability distribution called length bias power inverse relative distribution. The proposed distribution is of keen interest due to its desirable properties. To estimate the parameters of new distribution, maximum likelihood estimation procedure is used. Furthermore, to evaluate the performance of the proposed distribution, it was fitted two real data sets, which have been shown here, data 1 and data 2. The results show that the new distribution provides a better fit to this data set as compared to the other version of the Rayleigh distribution. And these are some references which have been cited or used in the preparation during the preparation of this paper, which is given this one. And last but not the least, thank you all of you for having this is listening by the talk. Now, just I need any suggestion from any big professor, any suggestion?
Sadish?
Yeah. Please.
One thing is, this is actually in particular case of inverse Weibull distribution.
Definitely.
Oh yeah, inverse. So this distribution.
No, this is not a particular. No, sir. This is not a particular. This is the power transformation.
You just refer. Yeah, you just refer. This you just refer the density, and this is a particular case of inverse.
Yes, okay, sir.
Not Weibull distribution, inverse Weibull distribution.
Yes, agree, sir. Okay.
So you can one or two papers studied the ordinary distributional properties and reliability properties of this model, inverse Weibull distribution. And of course, this is used in lifetime data studies, especially in the case of left sensor data studies. Okay, that's a parametric model. Okay,
sir.
When you submit the paper, you have to be very careful, and you have to go through the literature and supplement the result what you have contributed to this area. Okay,
sir. Thanks for sharing. Thanks.
Okay, Dr. Khan, what mentioned is you have to check where, in fact, it is, there is a question of novelty.
Okay, definitely, sir. I accept your suggestion. Okay.
You can do some other aspects, that's better.
Okay.
Okay, thank you. Thank you, Dr. Khan.
Thank you all of you. Thanks all of you together. Now I stop sharing?
Yeah, you can stop.
Yes, sir. Thanks all of you.
Okay.
Sir, your mic is in mute. We couldn't hear anything.
Sorry. Extremely sorry. Thank you for your mentioning that. In fact, I'm calling whether Dr. Kenny, Dr. Rashid A. Ghani is there in this group, whether that is what I'm inquiring. If Dr. Ghani is not in this group, and if everyone is okay with the presentations of these the speakers, or there is time for if you have any inquiry, or you have to ask any questions to our invited speakers, can, if they are here in this group, we can give chance. Otherwise, we can conclude this session. Okay, I think it is better to stop here in this session. Once again, let us give a big clap to the speakers of this session, especially the invited speakers, Dr. K. Jayagumar, Dr. Sebastian George, and the contributory speakers. Since one speaker is not here in this group, let us wait for the next session. That next session will start only at 11:55. So 11:55, the session is on statistical finance. So, and that session will chair by Ishapadik Das. Let us wait for now I think 11:37, so that 15 minutes. Yeah, let us wait up to 11:52 or 53. Yeah.
Can't hear anything. Hello? Can't hear anything. What's happened?
Dr. Satish Kumar, this is Dr. Sanjay Zodpe. I just wanted to confirm that I'm at the right place.
Okay, okay. Hello?
Yeah, my name is Dr. Sanjay Zodpe. I'm
Okay.
supposed to speak at 11:55, so I just wanted to confirm that I'm at right place.
Sanjay, you have, I think, Sanjay, you are not in this group. You are in the other group. There is a MD UP, 8 MD UP2.
Oh, but they sent me this link only. I clicked on the link which they forwarded to me.
Oh, the other, okay, okay. In the front of this our program schedule, the link is there. You just click on there, or otherwise you please contact the coordinator. I think Professor Malik, so that
I think the coordinator is.
You are the first speaker there. You please do it.
But he is not picking up the phone.
Oh, you can not coordinate that. That is the organizer of your session. I think it is better to contact Malik, Professor Malik.
Okay, in the program the link is there because I have the program. I'm just looking.
In the program schedule, in the first sheet, there is the link, and also their phone numbers are there. Okay.
It is at the bottom or where?
In the first sheet, there is a table is there in which a table venue different venues are there.
Malik one. So I am in MD.
Yeah,
I am in MD.
Yeah, MD UP.
Okay, okay. I will click on that then. Yeah.
Okay, okay.
Okay.
Okay. Now it is the time here. Let us start our session. It is Professor. In fact, we have this is a special session organized by Dr. Ishapadik Das on statistical finance. And the session is to be chaired by, in fact, Dr. Ishapadik Das. Dr. Das is a faculty member of IIT Tirupati. After he completed his MSc program from IIT Kharagpur, he did his PhD from I think IIT Mumbai, isn't it? He's a very active researcher. I utilize this occasion to invite, on behalf of ISPS, I invite Dr. Ishapadik Das. He's also an EC member of our society. I invite Ishapadik Das to carry over these proceedings. Yeah.
Thank you very much, Professor Satish Kumar.
Welcome. Yeah.
Thank you very much. I would like to take the opportunity to thank the organizer, Professor Satish Kumar, and others to organize this conference very nicely. Actually, I am enjoying this. Yeah, thank you very much. And in this session, there are 3 invited lectures and 1 contributory lectures. So one is by myself and another Dr. Ananda Lahiri, and another is by Arnab Chakraborty, and 1 contributory Monikanto Bhoi. So for giving adequate time to the other speaker, I'd like to invite. I will present at the end of the invited session. I thought. So that time can be adjusted for this session. So I request Ananda Lahiri. So she has completed her MTech from ISI Delhi, Indian Statistical Institution Delhi. Then she did her PhD from IIT Kanpur, and then she was very much active researcher also, and also inspired fellow and faculty in CMI, Chennai. Then she joined IIT Tirupati. Recently, she is working as assistant professor in IIT Tirupati. And now she is very much active research. She has several international journal publications. Now she is presenting here lacked long memory covariance matrix analysis from Indian stock market. So I request Ananda, Dr. Ananda, to present her this. So
Yeah. So
Yeah.
thank
Yeah.
you, organizer, for conducting very nice conference, and thanks, Dr. Ishapathik, for inviting. It's a very good opportunity for me. So maybe I'll share my screen.
Yeah, sure, please.
Just 1 minute. Is it visible?
No, yeah. Yeah. Now it is
coming.
Yeah, coming. Yeah. And now it is visible.
Yeah.
Okay.
You can make it full screen. Yeah. Yeah. Now it is fine.
Okay. So thank you again for this opportunity. So today I am going to talk about lagged long memory covariance matrix analysis from Indian stock market. This work is essentially work with my PhD student, Naga Vaishnavi. So most of that, so I will just try to explain what is the problem, and this is actually an ongoing work. So let's see how far we can proceed. So first, the terms used in the title. So what is lagged, what is long memory, and then what is the covariance matrix analysis, and then of course the Indian stock market. So I will try to describe everything in terms of graphs and plots, so if that helps. So what is the motivation for going it? So in the literature of the financial data, they have studied lagged cross correlation matrix. So what is it meant for? So we know in the stock market, there are different stocks, right? Different company, and one can buy their company shares, and that's the price of the shares, and we call this stocks. Okay. So the study of this kind of correlation things is due to the fact these stocks are linked. They interact with each other. So how it is possible? Say in the stock market, there are some companies which are from say IT sector. There are some companies which are for say coming from banking sector. There are companies which are coming from pharmaceutical sector. So the interest is how a banking company is interact with other banking companies. So the thing is that if it's say stock of a particular bank say increase, say some bank, SBI bank is increased, so will that affect to the other banks, IDBI? So will that also going to be increased, or how it is going to be moved, how the movement is going to be? So that is the part of interest, and that's why people do this correlation structure study. Now the question is the what is about this so that is actually about cross correlation. Now the thing is that next thing is the what is about lagged cross correlation. So the thing is that say today's price for say bank say SBI, does it affect just the today's price of the IDBI or the yesterday's or maybe 2 days back IDBI price, means that get influenced. So the thing is that if it is earlier observation, say SBI is two days back. So because SBI 2 days back did something, so today IDBI is doing something. Or because 2 days back IDBI is doing something, so today SBI is going to take some policy. So their stock price is changing. Is that the way? So that's exactly the lag. So lag is that time that it is how this quantities are relating to the a particular day, not necessarily they are relating to the in a fixed date. So they can be related to the earlier date also, okay? And their interaction. So in the literature, they actually studied this kind of matrices. So if there are say think of 100 stocks, then how many interactions we're going to get out of this 100 stock if I just take 2 at a time interaction. So I take any 2 of the stocks from the 100 stocks, and of course their own interactions to itself, which we called essentially the variance, not the covariance. So this 100 choose to where we can choose out of 100 stocks to any 2 stocks. So what we're going to do that we tries to write down their interaction in the form of matrix, in the sense that first element of the matrix is the interaction between itself. Second one is first with the interaction with the second one. Third position, 1, 3 position is the first stock interacting with the third stock, like that. So that's where this matrix is coming into the play. Now what this matrix analysis is going to give. So essentially this kind of matrix analysis is useful for portfolio analysis. So the thing is that if it happens, say that the banking stocks are all going together. So the thing is that if some financial crisis happen, if SBI collapses, then all other banks collapses. So what is going to happen that if I invest my money in SBI and I just invest only in the banking sector, then the problem will have this one collapses and every other which are actually greatly linked, they all go into collapses, then all my money will go. So that's what they don't want. So they want, okay, so you don't keep all your money in the same pocket. So you keep it in different baskets, right? So we want to know that how these stocks are moving, so that I will not going to put all which are actually similar kind of similar in nature. I will not going to invest the money in all this same basket. So I need a portfolio selection. It essentially, this portfolio is I want to invest in some stock, but how do I choose that stock? So definitely I will going to choose it so that they have good interactions or bad interactions, but I do not want from a very layman's perspective that whenever some stock is doing very bad, then all other stocks, I will not going to choose other stocks which are exactly similar like this particular stock. So then all my money will go. So for that kind of study, it's important. Now, what does matrix analysis people does? So this matrix analysis that does it essentially, that's what you see about the matrix study of the matrix. So in this matrix study, if the matrix is okay, I take the simplest possible scenario is a positive definite matrix and maybe the symmetric matrix. So we know their eigenvalues are all positive. So then we can actually study the eigenvalues distribution. Now, in case of the matrix is not positive definite, turns out to be, then also we know that if it is still symmetric, then at least we'll have a real eigenvalue. If it is neither of it, then we are going to end up in complex eigenvalues. So essentially, with the matrix things, we try to see how the eigenvalues distribution. Okay. Now, long memory we are going to come later. What is long memory? So what is the interest of studying these things? Because people have done a lot of analysis, but not much what has been done towards how to model these interactions. So there is no mathematical modeling in terms of explanations doing in a precise mathematical for this lagged covariance structure. Okay, and that also not particular for a particular lag. It actually have a for all lags. So we have say some time say 1 time lag, 2 time lag. So it will going to give a precise mathematical structure for all the time lag together. So if that whole history, if we can give a model, then that helps. So that's the motivation. So let us see what is the, so this is the sample stock price data. So we just take some Reliance. So it is all Indian stock market I talked about. So it is from Indian stock market. This is a Reliance Industry stock data. So looking at the data, we see that there is ups and downs, and then there is sometimes rapid fall and all these stuff. But our interesting to know study is that how they interact. So I will just in the next slide show this plot. So it is a Tata consultancy stock. Now note it around 2018, both actually have seen some sharp fall, right? Somewhere it's a back, it is 2018 if this marked here, it is somewhere before and somewhere it is just after. So question is this kind of, but it is some similar kind of things we can see here. Is it, can it be, and but they have actually, the events are actually not at the same time. Okay, so and they may be just there is no link, but is there any link, or at up to what extent there is link? So we can see that this fall has happened because there is an steep upward movement. There is also some upward movement and then this fall. So some very similar pattern actually, if you look into this stock prices, if one can say, and they are not occurring at the same time, so there is a lag. So whether we can do any precise mathematical analysis. So we tries to denote this time series plot as ST, okay, and we tries to see that if this is the time series plot, and you can see this is clearly non-stationary. This has a trend. So we want to make it, and this another important thing is that the scale. This scale is 1000 to 2000, whereas this scale is 1000 to 2500. Okay, so the stock price are not in the same scale. So we want to this scaling thing. So it is standard in finance literature. Then they take the log return price. Okay, so we choose the log return price, and then we try to see that how it is looking like. So we see that log return price. So it is this graph. It seems almost okay, quote unquote stationary, but is it really stationary, or any further analysis one can do? Okay, it seems nice stationary, and this also. So this is for Reliance, say this is for Tata. Now, to know that whether it is really good stationary things or nice, then we will going to see what we see in the time series, so which is called autocorrelation function. So if the mean variance exists, then one can actually define autocorrelate covariance functions like this, where if its mean depends on time, this is not stationary case. But in case it is a weak stationary condition, then it autocovariance function is only depends on the lag. So whatever lag it is a function of lag. And it also have a properties that autocovariance functions symmetry around the lag. So whether you go plus side or minus side of the time, future or past, from a given time point, it's symmetry. And from autocovariance functions, you can calculate autocorrelation function. So if we do not have any, we don't know whether it is stationary or non-stationary or whatever, but no matter what, we can, from sample, we always can calculate sample autocovariance function. And this is how we will going to calculate it, given a time series. So we are going to see the autocorrelation functions plot for, say, Reliance. So the thing is that it seems that, okay, it is a bound that the magnitude very small inside this bound, and that's fine. Point is, even if it is small, it is not going to close to be 0. And even the small, if I zoom it up, which we actually did it, there is a pattern still remains. The question is coming there about that long memory. So we call a process actually have long memory if this autocorrelation function is not summable. So a very simple example from real analysis, that we know 1 by n sequence is converging to 0. But if we try to sum 1 by n sequence, it is infinite, right? So the thing is that this autocorrelation function, it is essentially sequence, because this lag integer values, right? Lag 1, lag 2, right? So it is sequence. In the sequence, there's very small amount, but the thing is that the question comes that is this is going to be very small, doesn't necessarily mean that they can be summable. So if are they really decaying down, or they are not? So the thing is that it doesn't seem they're decaying down. So this, looking at the thing, it is not very small is not enough. Whether it is summable or not, that condition is important. So if you just plot it, then you're going to see, yes, even the 500 lag, in fact 1000 2000 lag, still there. So no matter what, it is very small, It's still not, if you just add it up, it still gives the very large quantity. And if that thing happens, that is what we call a long memory process. Okay. So it is not enough that it is decaying fast, but it is not summary. Now to check it directly from the data, so we called something called Hart's coefficient, and given a data, one can actually check whether it actually has long memory. So in a practically one can check for a Hart's coefficient. It's supposed to be between 0 and 1 in case of this apparent stationary case. And if it is greater than 0.5, then we will call it long memory. So for our data, depending upon how we have taken the window length of the data, because we have taken this, the data is for this many years, right? So it actually gets some portions of the data, if you take, it actually has a Hart's parameter more than 0.5, okay? And this calculation also depends on what is the total length of the data and what is the window size, how much window you have taken to calculate it. So yes, so it is coming that yes, there are stretches which is actually gives the idea of it actually has a long memory. Okay. So next comes to this thing, so the cross correlation function. Now, what happened with the cross correlation function? Now, cross correlation functions for calculating, we need two jointly distributed random samples, and it is quantity similar like autocovariance, okay, but between two different series. So it is the auto is not the meaningful word. So cross, so time series X and Y, and then their mean. And then this, in case of weak stationarity kind of thing, this cross correlation function is like this. So there is a dangerous mistake that is exactly not is going to happen. So it is not symmetric. So there is a typo. It has to be, it is not symmetric. So the thing is that autocovariance function is symmetric, but cross covariance function is not symmetric. So there has to be a cross sign. So maybe I go here and make the correction. It is not symmetric. So okay, and given the things whether we know or not, we can from sample we always can calculate the cross correlation function. So here is the cross correlation function. Now it same happens. See, it is around 0 because it is not symmetric. You can see that okay, both the sides the graph is different. But no matter what, it is inside the band, but it is not getting decayed down at all. So this is the motivation to know that yes, it really has the long memory. Now what we have tried, maybe I will try to be quick enough. So we have 84 stocks from Indian stock market. We can calculate this lagged covariance matrix. Now naturally, if this is happening, it is not symmetric. The covariance matrix, whatever we are going to consider, because these two quantities are not symmetric, right? Xth stock and Yth stock is not symmetric or giving cross correlation that Yth stock and Xth stock. So we will not going to end up in a symmetric matrix. So the eigenvalues will be complex. So people already have studied their eigenvalue, complex eigenvalues. Now what we have tried, we tried to see that get a symmetrized lag covariance matrix to get these eigenvalues real. So here is one plot from these eigenvalues, okay, and this is for a very particular lag, say lag 9. So that's the eigenvalue distribution turns out to be, and we try to see that what is the spectral distribution. So if it is that this histogram, on this histogram we try to plot the density. So density is looking like this, and it actually have a nice structure that it actually have a most of the eigenvalues are close to 0, but there is an outside bulk eigenvalues. So what is our work, we tries to develop, and we develop actually a stochastic modeling for this cross correlation function. Okay, and we have simulated that from that model, and we try to study their properties, and from this model we try to simulate what is the eigenvalues. Okay, so here the things from this our simulated matrix eigenvalues histogram. So it is quite matching. So essentially we are trying to propose a model which we have done. So I'm not going, this is an ongoing work, so I'm not going too much details. So we able to see that from our proposed model, we are going to get that it is actually going to give that proposed cross correlation function is actually characteristically matching with it, as well as their eigenvalues distribution is matching. So here is actually the eigenvalues densities after doing the plot. It looks like, so it is whatever we are getting from the data, okay, from the Indian stock market, and this is whatever we are achieving from our model. So then we will try to explain that why this eigenvalue, which eigenvalues are there, and for what stocks they are actually responsible for, and how these stocks, collection of stocks, corresponding eigenvectors, those are the main eigenvectors for this eigenvalues, and how they are changing with the time, because we are doing this on this time, how it is changing, so it is able to capture it. So that's what we try to do. So here are some reference. Okay, so if you need, I can give the whole journal. Details are not there, but there are a lot of work actually has been done. So essentially the work comes under this random matrix and theory and the study of this. Thank you.
Yeah, thank you, Dr. Vandana. So any questions? Please.
Hello, sir. Good afternoon,
hello.
Sir. Good afternoon,
hello.
Sir. Good afternoon.
Hello. Yeah.
Yeah, please ask questions, Dr. Rosit. Hello, I think you are not audible now, Dr. Rosit. You may have asked some questions. Please continue.
Shall I ask a question?
Yeah, please, sir. Please.
Yes, sir. Yes, sir.
Yeah. When you're performing this autocorrelation and cross correlation, if they are almost the same, if they are significantly different, then you may get better result. I suppose so. So is there any test for testing whether the autocorrelation and cross correlation are same and different? And if that is so, if they are significantly different, it may have larger impact, I suppose.
So the autocorrelation so from the autocorrelations, this is zero lag matrix. So so one interesting thing is that zero lag matrix actually turns out to be a symmetric matrix. So the cross correlation is not symmetric in the thing. So we are not studying to see how the absolute values. We are trying to see it how they are linking with the earlier values, and with the time change, how it is, how what pattern is actually carrying. So maybe I will just.
No, compared to different stocks, which stock you can consider can be decided based on cross correlation, I suppose.
Yes, cross correlation. But then we want to see that cross correlation in the dynamic fashion. We want to do it in dynamic fashion in the whole window span. So it is not checking one cross correlation matrix. It will be it is the sequence of cross correlation matrix. So it is a sequence of matrix actually moving, and we want to capture that whole sequence matrix.
Yeah.
Does that give the answer? So it is not a single cross correlation matrix we are interested in matching. So I show you one single, but it is lag cross correlation matrix for different lags. So we have a sequence of matrix, random matrix, and we just want to see that their spectrum is actually changing across with the time.
That's fine. That's fine. Okay.
Okay. Yeah. Any other questions? Someone may ask. Okay. So we are running out of time. So thanks, Dr. Ananda, for the nice presentation. So we'll go in the next presentation. I think, yeah, Dr. Arnab Chakraborty. So he is going to present a new filtering technique for convolutional networks from high-dimensional data. So 1 minute. Okay, so he has completed his postdoctoral researcher. He is recently a researcher of IIM Ahmedabad. And hello, am I audible?
Hello, sir.
Yeah. Just I am
Hello, sir.
I'm just want to give a brief about his presentation and also about him. So he has did PhD, completed his PhD from Indian Statistical Institute and MSc from Department of Statistics, Calcutta University. And recently he is doing a postdoctoral research at IIM Ahmedabad. He has excellent research profile and he has published mainstream journal, international journal, several publications. So thanks for accepting our invitation for presenting here. So please, Dr. Arnab Chakraborty, I request you kindly proceed with your presentation, please.
Thank the organizers for organizing this beautiful conference, and of course, thanks to Professor Das for inviting me here. It's a great opportunity. So I will share my screen. Is it visible now?
It is coming. Yeah. Now it is visible.
Okay, fine. Okay, so so I will have half an hour, right?
Some sound problem is there from your.
Okay, fine.
Yeah, you may try to complete 25 minutes so that 5 minutes discussion. Yeah. Okay. Please go ahead. Your audio not coming. Your audio. Yeah.
To unmute, please.
Okay, now it is coming.
Yes, audio also coming, and you may full screen your presentation.
Okay, so okay, fine. So
Yes.
You didn't probably hear anything.
Now
Yes,
it is
yes,
fine.
Yeah. Yeah, this is fine. Yeah.
Okay, so first I would like to thank the organizers for organizing this beautiful conference, and of course Professor Das for inviting me here. It's a great opportunity for me. Okay, so the title of the presentation is a filtering technique for co-movement networks from high-dimensional data. So there are a lot of jargons. So I will explain each and every part. So first, let me ask this question that why we need network analysis. So basically, this is talking about co-movement network. So the first question is that why we need network analysis. And so the answer is that you will never get a network. Someone will not give you a network and ask to analyze it. So you will have a regular data, but you will then try to represent the data in a network form, such that some of the key insights about the system is available through that representation, which are otherwise not possible to get using the usual statistical methods. And so basically, we are going to look at the financial network. But before that, we can take some examples of network. And for example, you see that now some of the data are natural candidate for in a network analysis. For example, Facebook network. So in Facebook networks, each individual or the account is a node. And if two accounts are friends and two persons are friends, then there is an age between these two nodes. And if they are not friends, there is no age between them. So basically, we have a bunch of nodes and you have a bunch of edges, and the edges are not directed. So basically, if I am friend with you, then you are also friend with me. It's not one way; it's both way. Whereas if you look at the Twitter network, it is basically a one, this is directional network. There is direction of the ages. So because I am, say, I am following, say, one celebrity, say Shahrukh Khan, but that doesn't mean that Shahrukh Khan is, following me back. So it's basically one direction. So there are some directed networks, but the kind of networks we are going to consider here is basically the undirected but weighted network. So each age has a weight. And what is that network? So what is co-movement network we're talking about? So basically in a co-movement network, there is, each node is a variable, and the association and each age is their corresponding correlation or covariance, whatever, So that is basically the co-movement network. And what we actually do in this work, we would like to see we'll take, say, p number of stocks, and then we will take the daily returns, and we will take the covariance of the return the return vector, and that covariance matrix is giving me the adjacency matrix. That means it's giving me the weights of the network. So if two nodes have a significant correlation, then there will be an age which has significant proportional weight. Okay, so now we have explained what is co-movement network, but then the question is that what is network filtering, because we are trying to propose a new filtering technique. So what is network filtering? So network filtering, I'll explain this through this figure. So this is basically a network obtained by, if we have taken 50 stocks and took the returns over 30 days, and then we created this network. We just take the sample covariance matrix and created this network. So each age is having a weight which is equal to the covariance of between those stocks. But the thing you can see here, it is very much messy. You cannot really see any pattern coming out of this network. And of course, you have to go through sophisticated methods. But even the visualization is not helping you anything. To gain any insight about the system, the market. So the question is that, well, can we just delete some of the unimportant ages and probably some of the spurious ages such that a deeper structure can reveal? So basically, what we do in network filtering is that the first thing you want to do is that you want to get rid of the spurious ages. Right, the ages which are present in the sample covariance matrix, but that's not present in the population covariance matrix. So suppose the population covariance matrix is 0, that means in the true network there is no age. However, when you calculate the sample covariance matrix, due to some error, there will be always some value. So then in the sample correlation matrix or covariance matrix, the age will be there. So we want to delete those ages. That is the first objective. The second objective is going beyond that. Even you try to remove some of the true ages such that some kind of underlying structure of the network emerges. So what do we mean by underlying structure or skeleton? So you can look at this small example. This is a toy example. You can see in the left hand side, the figure you can see is a true network, suppose. Okay. So what we are seeing is a complete graph. It's in every node, every age is connected to any other node. Any node is connected with any other node. It's a complete graph, and we are not getting any particular insight about it unless we reduce it to this filtered network shown in the right side. So what we have done, so you can see there are some of the ages which are bold. I have intentionally made them bold to represent the fact that those correlations are really high, say greater than 0.8, whereas this age or this age, which are in a thin line, it represents a correlation less than 0.1, say something like that. Okay, so those are relatively weaker ages. So when we delete these weaker ages, what we get is this in the right side. So it actually gives you a very condensed information about the system. And it's what we see here is that one node, this is node number 1, is very central in the network, and all other nodes are in the periphery. So basically, all other nodes are dependent on the first node, but they are not. Otherwise, there's not much interaction between them. So that is the filtering thing. That is the objective of the filtering. So that's the second objective. So even we are going to remove some of the true edges, such that a kind of underlying structure or skeleton of the network emerges. But then the question is that we are not sure, or we cannot assume that every time you look at a network, there is a star-shaped network that is just shown in the figure emerges. So there can be any kind of structure, and you probably you don't know what kind of structure is lying underneath. So so basically you have to specify some kind of structure, and while you are focusing on that structure and you are trying to get a kind of formal filtering technique such that it captures that structure, and also it can capture some other hidden structure. Probably it can capture some other hidden structure that is present in the network. So that is basically network filtering. Basically, you want to remove some of the unimportant edges such that an internal structure can emerge. So the first thing is that we need to consider one structure when we are considering here the spectral structure. So spectral structure means the distribution of the eigenvalues you can consider. So why we are considering this? Because this is important in context, particularly in context of finance. Because theoretically it is very well known that the networks generated by the same random process have same distribution of eigenvalues. Okay. So basically, the spectrum helps us to understand some of the key properties of the network. And if you take the spectrum and you see that the extreme eigenvalue is going to capture the fluctuations in the network due to the market, and that is well documented. And the degenerate eigenvalues captures the sectoral fluctuations. For example, stocks related to the business sector and so on, pharmaceutical sector and so on. And the bulk of the spectrum is actually going to capture the idiosyncratic fluctuations in the market of each stock. Okay, so what we have talked till now, we have a co-movement network. We want to have filtering technique, which is basically nothing but removing some of the unimportant edges to get some internal structure, and then we focused on the spectral structure. Now there is another problem that the financial system actually goes through very repeatedly some turbulent periods and tranquil periods. So in some of the times there will be outside shock and the system will be changed significantly. So basically, when you construct the network, if you take daily data, you cannot really take a very long time window, because when you take a very long time window, your underlying assumption is that in that time window, the underlying network is fixed, is constant, it's not changing much. It's basically that same. However, if we take a very long time window, there is very good possibility that the underlying network will change. So therefore, what we have to do, we have to really consider a relatively small time window, or that you take the data from a small time window, maybe 1 month, maybe 2 months, maybe 3 months, but not more than that. Okay. So and on the other hand, when we talk about network analysis, you generally do not consider 10 stocks or 20 stocks. You consider much more stocks, so that you can have a bird's eye view on the system, the whole system together. So therefore, you have a significant number of variables, but less number of observations, because you have the small time window. So that means it falls in the high dimensional kind of setup, and it obviously has some effect in calculating the sample covariance matrix. So sample covariance matrix is no longer a very good estimator of the population covariance matrix. So basically here we have written the high dimensional asymptotics. What is high dimensional asymptotic is where both the number of variables and number of sample size increase to infinity. And the question is that, how fast P is growing compared to N. So those things are there. And this is one small example. This is actually initially shown by long back in 1960s by Stein. And what is showing is, so basically we have a Gaussian distribution with P variables and a covariance matrix I, identity matrix. So basically all the population eigenvalues are 1. So this dotted line is 1. All the population covariance, population eigenvalues are 1. And then if you take the sample size and you vary the sample size and the dimension, then what you will see, when the P by N ratio is small, the sample eigenvalues, which is shown by this solid line, the sample eigenvalues are nearer, comparatively nearer to the true counterpart. Whereas when you increase the P by N ratio, that means you are going more and more high dimensional case. So what happens that you deviate, you go away from the true eigenvalues. So the question is that then why we are saying these things? Because you see that we have to construct the network, the co-movement network. That means we have to calculate a good covariance estimate. But under high dimensional data, you don't have the sample covariance matrix is not a good estimate. So you need to have something else, some better estimate. So that is point number 1. So we need to consider a better estimate of covariance matrix. Okay, unless we do that, our constructed network from the sample covariance matrix would be misleading. The second layer is that we want to capture the spectral structure. That means the spectrum of the estimator of covariance matrix must retain the properties of the true spectrum, the true eigenvalues. Okay, and then ultimately we are going to propose a network filtering technique. That means we have to remove a lot of edges. That means we have to remove a lot of covariances in a lot of entries of the covariance matrix. That means we want to have a sparse estimate of the covariance matrix. So we need a sparse estimate. So that's so point number 1 is that we need to have a better estimate of the population covariance matrix than compared to the sample covariance matrix. Second, that estimator should retain the spectral properties. And third is that it must be a sparse matrix. Now there are some. The problem here is that if you see the high dimensional covariance matrix estimation literature, then you'll see that there are sparse estimate of covariance matrix, which we'll be talking about in a minute. This is called threshold operator, and there are some estimator which actually tries to retain the true spectrum, and we will also be talking about that. But the thing is that the estimator which will satisfy this problem, that means distance from the spectrum, will not satisfy, it does not be sparse. That means that will not satisfy this property. So there are two properties. Okay, so one kind of estimator will solve satisfy the one property but not the other, and the other group of estimator will solve the other property but not the first one. So there's a problem here. Okay, so one possible better estimate than the sample covariance matrix of the population covariance matrix is simply this. You take the sample covariance matrix S, and then you take a spectral decomposition P capital lambda P dash, but then you improve the estimator by regularizing the eigenvalues. Why? Because as we see in this figure, as we are in a high dimensional setup, the eigenvalues are away from the true counterpart. So what if we regularize and compress it towards the true counterpart, and thus getting a better estimate. So basically that means that you take a function of the eigenvalues, sample eigenvalues, and basically you are kind of regularizing it, shrinking it. So that's the Stain's approach, and Stein proposed an estimator which had several problems. And then later Wolf actually did executed the same concept essentially, but a little differently, and it's very influential actually. So he actually took and they actually took this a linear combination of sample covariance matrix and the target matrix, where sample covariance matrix is still unbiased in high dimension setup, but very unstable due to high dimension. And this target matrix is very stable, but highly biased. And their linear combination, if you can choose the alpha 1 and alpha 2 properly, that will give you a better estimate. So that is a Later-Floor estimator, and it can be shown that the Later-Floor estimate actually retains the properties of the true covariance matrix, true spectrum, true eigenvalues of the population matrix. So that is Later-Floor estimator. The problem with the Later-Floor estimator is that it's not giving you a sparse estimate. Okay. Whereas, and so I'm running out of time, so I will speed up a little bit. So this is a threshold estimator. Threshold estimator is exactly doing the opposite thing. So it is giving you a sparse matrix. How? By choosing a threshold, and you take a threshold and delete everything out and replace every entry of the covariance matrix below this threshold by 0, and keep everything above that threshold. So that's the threshold matrix. And there are some good theoretical properties of this threshold matrix. I'm not going into the details. I'm skipping some of the slides due to lack of time. The problem with the threshold estimator is that it gives you a sparse estimate, but it doesn't preserve the spectral structure. So that is basically the problem. Now, if we rephrase the problem a little bit, so it's like this. So we need a threshold estimator, which is giving us a sparse estimate. And the question is that what would be the choice of the threshold? So we have to select the threshold. And in another level, we need to retain the spectral structure. That is a new estimator spectrum should be close to that of the Later-Floor estimator. So these are the two things. So now, what we do, we take our solution is very simple solution. So we take a threshold estimator, but we choose the threshold such a way that it satisfies this second condition. So basically, we are kind of reconciling these two literatures in such a way that we get we can solve this precise problem of a filtering algorithm. So this is our first filtering algorithm. It's called we call maximal filtering, and this is very simple. So this is basically the S eta. Eta is the, as we have seen this is the threshold. Basically, S eta is the threshold operator or threshold covariance matrix, and S LW is the Later-Floor estimator of the covariance matrix. So S LW retains the spectral structure, whereas S eta gives you a sparse matrix. So now what you do, you choose the eta such that the distance between these two is minimum. So you get a sparse matrix. At the same time, you get minimum distance from the spectra, or you can say the proxy of the two spectra, which is a spectrum of the Later-Floor estimator. Okay. So, and then what we say is that, okay, fine, we can modify it a little bit. Why? Because of the following reasons. See that we are in the filtering, what we are doing, we are removing some of the edges, even some of the true edges. So we are deleting some of the covariances. So, and that actually has a cost, right? So because if even if it is unimportant, if it is present in the true network, then it gives us some information. So we are losing information by deleting those edges. So for that, we want to introduce a cost function here. So there is this. So this part is like before, and now here we are introducing a cost function C eta, and it is a function of the threshold, because if you take a high threshold, then a lot of more number of elements will be deleted from the threshold matrix. And so so basically, how can we define the cost? And the one way of you can do it in different ways. There's several possible ways, but this is one way. So you have the total age weight, which is defined by like this, where f is a suitable non-negative function of the sample covariance or covariance, whatever. The total weight removed by filtering is basically the same thing, but now ij belongs to the set E bar, where in the E bar is basically the set of removed edges. So basically that is the total weight removed by filtering. And then you can take any convex function of S W eta divided by W, as that would be a valid choice of the cost function. So yeah, so and there are many special cases which are reasonable. This figure actually illustrates the point. So here you see that this red line is actually minimizes the is actually calculating the distance, this distance. Okay, and we are choosing the threshold where this distance is minimum. So this is the point threshold where this distance is minimum. So this is the maximal filtering. And after the addition of this cost function, then your new line is this. And now you see this is the point of threshold where the function is attaining the minimum value, and therefore this is our solution. So this is a tune filtered network. And if the tune filtering is the threshold of tune filtering is less than the threshold of maximal filtering. So I will very quickly go through the one very small simulated data analysis, and then we will show the real data analysis. That will take 3 more minutes. Just bear 3 more minutes with me. Okay. So here in the simulation exercise, what we have taken, we have generated the data from a Gaussian distribution, and the true covariance matrix is if you consider the network from the true covariance matrix is like this. And you can see that this is not a complete graph. So basically, a lot of the covariance is at 0 or correlations are 0. So you see that there is no edge between 2 and 5. That means the correlation is 0. Corresponding correlation is 0. So this is a sparse matrix then. Okay. Now, when we get the data, I mean, you simulate the data from that Gaussian distribution with that covariance matrix and say 0 mean, and then you take the sample correlation matrix or sample covariance matrix, it comes to be like this. Now, one thing we, as a statistician, we always ask that, of course, that it will be like this, but then we don't know whether this, the 2, 5 here, say 2 and 5 here in the sample counterpart, whether it is significant or not, we can do a testing. Of course, we can do a testing, but the problem is that here you see that how many edges are there? It's huge, in the order of n squared. So there are that many tests we have to perform, which is not meaningful in case of high dimensional situation. So that's why we cannot directly go to testing hypothesis route. So what we want to do, we want to do some kind of filtering, and here we see the maximal filtering, and in the right hand we have tune filtering. And you see that for the maximal filtering, it reduces this true case. It even deletes too many of the edges. However, if you see that it picks up some of the important components of the network, true network. And for example, you see that 7, 9, and 10. This is a very important triad. You see that this is a triad in the network, the true network. Another true component is the 2, 1, 6, 5. This is with bold. Okay, and we can see that in the maximal filter also that component is being selected. However, maximal filtering is, of course, as we have discussed, it's not considering the cost function, so it is basically deleting too many of edges. Whereas the tune filtering is deleting, less number of edges and therefore retaining most of the part of the network. Okay, I will skip these things. I will give you the real data analysis results. So basically, 50 stocks are taken from the NASDAQ data over 70 consecutive days, and we take the log returns, and we consider the variance of the covariance matrix of the log return series. Okay, so this figure I have shown you in the beginning. Okay, so we have shown that this is very messy figure. We cannot see anything we cannot get a good visualization, and we don't get any insight about the system. And now after applying the filter, what we are getting is this, and which is actually very sparse and very accurate view of the network. And we can see that which nodes are very important, are really important in the network, and which are less important. Okay, and then basically we this is the distance function actually. So basically this at this point it is distance function is being minimum. Yes, I'll stop here. Thanks.
Yeah, thank you, Dr. Arnab. A very nice presentation. Any questions? Please ask questions from the audience. Okay, just I just want to understand. Suppose you want to find that distance function, you are minimizing that cost and also for a tuned minimizing things, you are adding some extra things. So can you repeat the things? Means you can you show me that?
Right, sure. So basically what we are doing is that we are basically, so initially what we had is, sorry. Yeah. So basically what we had is this two candidates of the the estimator of covariance matrix. One is S eta, which is a threshold estimator, which gives you the sparse matrix, and you have the Ledger-Fold estimator, which is giving you the which has closed it retains the spectral structure. Now what we do, so in order to get a filtering, you need a sparse matrix. So that is beyond doubt. So you need a sparse matrix. That's why you need a threshold estimator. But the question is that what would be the choice of the threshold? And we say that choice of the threshold would be such that the spectrum of this new threshold matrix is minimum from this Ledger-Fold estimator. Why? Because Ledger-Fold actually retains this true structure, spectral structure. So that is why we take this to minimize this distance. And then what we are doing, we are adding a cost function, because when you delete too many of edges, when you have higher threshold, so you are choosing the threshold here, right?
Yes.
Yeah, so when you're choosing a higher threshold, then more number of edges will be deleted, and that has a cost. So we want to account for that cost also. So that's why we add a cost function, and then we minimize that.
Yeah, for your numerical example, you are generating suppose data from a covariance matrix, normal distribution with covariance matrix. Some of the correlation will be 0, but in the suppose here, so there in the sample there will be some correlation, some covariance. So it will not be 0.
Yes.
So then how these metrics are constructed, or these distance functions are constructed?
Okay, so this distance is on the, so basically, right, so I didn't clarify that. So basically you take that, so basically the rule is that you have to construct the network from the covariance matrix. So suppose you have a good estimator of covariance matrix. That is that is the whole thing. But suppose you have a good estimator, then you take the distance of you have the threshold covariance matrix. So you have the spectrum of that matrix, right? So you have the eigenvalues.
Yes.
So you have the eigenvalues of the threshold estimator, and you have the eigenvalues of the Ledger-Fold estimator. So now you are taking a distance, and you can just simply take a Euclidean distance. There in our paper, actually, we have proposed several choices of distance, but you can, for simplicity, you can simply take the Euclidean distance or any known distance of these two vectors.
Okay.
So that's actually the spectrum. So the eigenvalues. So you have two eigenvalues vectors, and you just take the distance from between them. Yeah.
Okay.
That is how we do it.
Yeah. Thanks. Yeah.
Thank you.
Okay. So if you anyone else has any questions, any doubt, please ask.
So I have this slide where you have shown it is deviating from this the standard one. So this with different values of p by n ratios or something. The
Yes.
yes. So what is that x-axis?
X-axis is just the eigenvalues from largest to smallest. So basically, when you take the sample covariance matrix and you calculate all the eigenvalues, so the highest eigenvalues is here.
Okay.
And the
this is just the ordering. Okay, so
it's basically order. Exactly, order eigenvalues.
Okay, thank you.
Yeah. Okay, Dr. Arnab, for your nice presentation. Okay, thanks a lot. Okay, so next, I think before contributory presentation, so I think I'm going to present because next invited lecture, I think 3 out of 3, I am one of them. And thanks, Professor Sotis, for introducing me at the beginning. And let us share. Okay.
Hello, sir. Hello, sir.
Yeah, hello. Yeah.
Hello, sir. Yes,
yeah, please.
Sir,
hello.
Actually, I am waiting. Sir, actually, I am waiting. I am going to present the presentation.
Yeah, sure. Please present. So you are the contributory presenter. Okay. I'm okay.
No, sir. I am the contributory presenter.
Sir, wait, sir, 5 minutes.
Rashid Gania was in fact, you have included in the earlier session. You missed there, I think so, isn't it? So here in this session, the contributory speaker is Kumar Manikanda, isn't it?
Yes, sir. I am.
Okay.
You have to present you have to present, and if there is time, please allow the Rashid Gania.
Yeah. Please, I will give the. I think we will have some time. So so at the end, we'll request Dr. Rashid also to present in this session also. I think it is fine. Is it fine? Okay. Yeah. So I'm going to present now. I will complete. Then I will request other speaker also.
Yes, sir.
Yeah.
Okay,
so,
sir.
I'm trying to share. So, is it visible?
It is coming.
Okay.
Hello, sir. Sir, is screen sharing, sir?
Now it is just gone.
Hello, sir.
You are yeah.
Hello, sir.
Rashid Gania, you will get time only in the last, because there is time towards the end.
Yes. Yes, sir. Yes, sir. Okay, sir.
Okay, I think is it visible, the presentation?
Now, visible.
Okay, thanks. Okay, I'm full screen. So the title of the presentation is Robust Credit Risk Modeling Using Generalized Linear Models. So the goal of this work is to provide robust credit risk modeling using generalized linear model robust to the misspecification of linear predictors and or link functions. So basically, banking is built on the idea of profiting by loaning money to ones that are in need of money. Banks access the potential borrower's creditworthiness, because if bank give loan to the person, so bank has the risk that whether he will get back that money with the interest or not, because that is the business bank usually do. As a measure of creditworthiness, some assessments are made on the probability of default. So probability of default that we are going to discuss in details here. So that is one of the measure for the creditworthiness of the person who are taking loan. The risk that the credit assessment of the borrower is too modest is called the credit risk. So probability of default is the probability that a borrower will default on the debit. So default on the debit, that is the probability we are going to estimate here. So it is denoted as PD. After that we will write PD is generally estimated by reviewing the historical default record of other loans with similar characteristics. So for estimating this PD, we need some data, that historical data of the persons. Otherwise, we will not have any idea how to get the probability of default with some characteristics. Probability of default is a key figure in the daily operation of credit institution. So basically, one of the popular way of modeling probability of default is to use the logistic model. So in recent era, there are machine learning techniques, also neural network, so other random forest. There are different articles already published. You can see in the literature that probability model is probability of default is model. But one of the classical approach, and this is the basic approach still people use in research and the practical purpose using data, it is the logistic model. The logistic model are used to find the probability of default. Let y be the response variable, which is equal to 1 if borrower defaulted and 0 otherwise. So now x1, x2, xp is the covariate of the person. So and y is the responses. It is a binary response. Suppose it is defaulted, then this is equal to 1, and if it is not defaulted, then it is equal to 0. And x1, x2, xn is the P is the other covariates, for example, age, sex, their income, and their suppose credit limit, and other covariates. So maybe some social, their the other socio-economic condition of that person. So you can include these covariates here in these independent variables. So to model the PD. And then the logistic model is the probability of y equal to 1. This is exponential of eta x by 1 plus exponential of eta x. Eta x is a linear predictor. So those who are familiar with the generalized linear model, they know that a generalized linear model contains 3 components. One is distributional components. So distributional components that the responses. For example, in our case, it is binary responses, but it may be Poisson or other responses, which has some particular form of the density or probability mass function. You can write in this way, or we can write in this way. So then we say that it is in the exponential family. Then this expected value of eta, this mu I is the expected value of yi. So this is related to a linear predictor eta xi. But linear predictor is just a function of the covariates with parameter beta. So in simple linear regression, we know that this is directly we relate with the mu I with this variable. So we will give some example for more details. So this is very basic for students, those who are you can see this, understand this very clearly, that suppose the responses are Bernoulli, then you can see that the probability mass function is pi I y to the power y 1 minus pi I whole to the power 1 minus y. And then you can write in this way exponential of this in this way, where you can write this theta is log pi I by 1 minus pi I and b theta I is this. So then you can see, you can check with this form that it is also a exponential family. And one of the linear predictor you can consider, suppose you have one independent variable. So beta naught plus beta 1 xi1, it is one independent variable. So beta naught plus beta 1 xi1 plus beta 2 xi1 square, this is another linear, form of linear predictor. So these are, you may be familiar. And link function, it is actually relating the linear predictor with the expected value of yi. So in our case here, it is a Bernoulli distribution. So it is just a probability of yi equal to 1. Suppose it is pi I. This is equal to eta I, then it is called identity link function. Usually for simple linear regression, we use the identity link function. We directly link it. But in other generalized linear model, it may not be reasonable, but we may not get a good result if we use this. There will be some problem. But you can use logistic link function, because pi I always between 0 to 1. So, but if you consider this link function, it will be always between 0 to 1. And if you consider probit link function also, and complementary log function also. So there are many link functions. So now here till now whatever we have discussed, it is exists in the literature. It is very frequently used and very popular for modeling probability of default using logistic link function and the particular linear predictor. Now question is that there are many other link functions also. So we are considering to improve this link function or linear predictor. Suppose some researcher or some experimenter, they use some particular form of the linear predictor. There are different form of the linear predictor, or a particular form of the link function. There are different form of link function, but in the data whatever you are using, so it is generated from some other linear predictor or some other link function. So maybe we are assuming that there are some particular link function or some linear predictor, this data is generated, but we are using some assume link function or some assume linear predictor that is not actually correctly assumed. So it is some different. So then the estimated value, suppose if you MLE, maximal likelihood estimates, if it is the model is not correctly identified properly, so then the estimated value will be asymptotically biased. It will not be unbiased. So it will not be consistent also. So these are some of the problem. So it depends upon how a model is properly specified or not. So now here we are going to do. So even if you consider a finite sample, then also your prediction will be not good. So prediction will be wrong. So here we are dealing with this model misprecision problem. So the experiment usually assumes certain form for the linear predictor and the link function of the model. The assumption may not be correct always. Thus, the inferences drawn from the fitted model will not provide desired results. So here it is explained. So you have used some assumed linear predictor like ZX into beta. It is just it is a multivariate. That's why all bold. So univariate also you can think for a simplicity, but the estimated mean response will be h of beta x. H is the inverse of the link function. We say it is the response function. So h of zx beta hat. But the true linear predictor is like this: zx beta plus fx. So fx is any other function. So it may not be in the form of this polynomial function. It may be sin x, cos x, any nonlinear form. So that we usually don't use in the linear predictor. So but actually the true responses, it is generated from some other function. This is fx. So then we are denoting by true linear predictor is this. So then the true mean response will be h of eta tx. So h of zx beta plus fx. So if you use this assumed linear predictor, then we will not get the true mean. So that means you are here, you are committing some kind of error for predicting. So in the so now here one method is proposed by Adola and Wins 2009. So how to estimate this fx? So using a first order Taylor series approximation. So if you write dx equal to this difference mu 2x minus mu x, and if you expand using first order Taylor series approximation, then you can get dx approximately equal to this into fx, and from here f hat x equal to this in whole inverse into d hat x, where d hat x is the difference of yx minus mu hat x, because yx is the observed response, and this is the true mu tx we can consider. This is the mean. So true mean, and this is the estimated mean using the assumed linear predictor. So that then you can estimate this d hat x. So that means it is some kind of estimate. So you can use d hat x here, and then you can get the f hat x, estimate of f hat x at the design point only. Design point means where you have the responses. So that whenever you have some response values at the point of x, you can estimate this this function fx. But the other point, how you estimate this fx, because you want to predict other values in the design region also. So then for estimating this other region, we can use some you can use as a f hat x as a training data set at x, and then you can use some other method like Kriging or some non-parametric method or some other regression techniques to estimate the fx at other x. But this method based on the first order Taylor series approximation, in practical, whenever you are using a data, then we see that we don't get a very good estimate. So here we propose some advanced method. We have tried to improve it. So due to using first order approximation, the above technique does not provide desired result. So we propose an iterative method. So what we are doing, suppose this estimate what we got, it is from the first iteration, then we continue this. Suppose this is the next f hat x, and you put this value and you get a new eta hat x. So then you consider that is a new eta hat x, and then you so here basically L equal to 1, this is usually it is a assumed linear predictor. Then you use the first f1x, and then you continue. Then the L plus 1x, then this is the new eta xx. Now the R is some correction factor because this iteration may not converge always. So that's why for getting a convergence, you can this increment is controlled by the R. If this increment is very high or low, it may be divergent. This method may not work to have the convergence of this. So this convergence criteria, we can take some Euclidean distance, or here we have considered the deviance of L plus 1 minus deviance of L is less than epsilon. So it worked fine. Some of the numerical example we saw that it is work, and also some of the real data example we are continuing to do work on this in this direction. And then we also talked about link misspecification. So here also you assume some of the particular link, like some logistic link function, but they may not be correct always. There are many other link functions you can consider, and there are infinitely many other link functions that may provide a significant better fit than the logistic model or probit model. So here we are discussing here, we call is a family of link function. So basically family of link function, it is given by this way. So you may also remember that this is the logistic link function. Pi x is equal to probability of y equal to 1 given x, the exponential of eta x by 1 plus exponential of eta x. So now it is a symmetric link function, and at eta x equal to 0, this is equal to 1. So now and also around the eta x equal to 0, it is symmetrically increasing, symmetrically decreasing. So but there are many other link functions you can think of that this it will be symmetric. So here it is called a general family of link function, exponential of g alpha eta by 1 plus exponential of g alpha eta. This g alpha eta is called the generating family, proposed by Shiraza 1989. So this gives this kind of form. Here this form actually, 1 minute, sorry. So this form alpha 1 and alpha 2 to other link parameter is added. Alpha 1 is responsible for the right hand side, this right hand side this of the symmetric, this link function, logistic link function. So if you increase alpha 1 and alpha 2 value, it will not be symmetric. So based on the data, it will be adjusted, and alpha 2 is for the left hand side, left hand tail, and right hand alpha 1 is the right hand tail. And now suppose age alpha naught dot be the assumed link function. So note that whenever alpha 1 alpha 2 equal to 1 1, then this is g alpha eta is nothing but eta only. So that is a logistic link function. So you can see also that for varying alpha 1 and alpha 2, it contains most of the known link function we have. And so this family of link function contains infinitely many link functions, and also it contains our known link function like logistic link function, probit link functions, other link functions. So here suppose alpha node is the logistic link function. Suppose if you consider alpha node is equal to 1 1, then it is nothing but the logistic link function. So experimenter usually fit using the logistic link function. So we are saying alpha in general age alpha node is the assumed link function. But so now suppose then this estimated value of mean will be pi x will be h of alpha naught eta x. Now the true model is pi tx, this is equal to h of alpha t eta x, because alpha t may be different from the alpha naught. Alpha t is the link parameter. You can find from the data some suitable values of alpha t that gives a significantly better fit than the alpha naught or logistic link function. So that is another way to deal with this link misspecification problem. So we already discussed the linear predictor misspecification problem. Here we are dealing with the link misspecification problem. So here we are using basically the family of link function instead of a single link function as a logistic link function. So here some data set I have generated for assuming some of the linear predictor. It is a multivariate response. Actually, it is a ordinal response basically. And here actually true linear predictor are considered with these functions. Or functions are, you can see that it is not in the form of polynomial. Using we usually use some polynomial of x1, x2 like that with some parameter beta naught, beta 1. But here you see that the other functions are not like a polynomial. It is like a nonlinear function, sine, cos like that. So now you may not get a good fit even if you increase the parameters also using this kind of form of the linear predictor. So now we have used this is the generated data, and then we used this first. This is the assumed linear predictor, and this is the true linear predictor, and then this is the estimated value, and this is the deviance. 80.95 is the deviance. So whenever using a logistic link function and the this kind of linear predictor, the estimated deviance, so estimated parameter and the deviance is 80.95. So now if you use the generalized version of the estimation method by Adler 9, 2009, and also we proposed the iteration method. So then one by one, the deviation, first iteration deviation decreased to 43, then 23. In this way, it is in the 9th iteration, it is looks like a convergent 18.4006. So you can continue, but it is like around the 18. So deviance. So now initially we got the deviance is 80.95 using assumed linear predictor, but here you see that using our technique we are getting a better deviance or better fit. So similarly, so here it is explained using linear 80.95 we got the it is not good fit, p value is 0.001. So now after using this method we got the deviance is 18.40. We achieve better fit by rectifying the misprecision of the linear predictor. So now we did the simulation study similarly for the linear link function also. I'm not sure about the time. I think I can be like around 2-3 minutes. I'll continue. So so here also we did the simulation study. We generated x1 from normal 0, 1 and for a independent variable, and y through the family of link function generating family. This is the family of link function. So for alpha 1 equal to -1, alpha 2 equal to 1, beta not equal to -1, and beta not equal to 3. And this is the linear predictor we consider, because you are considering here link misspecification. We consider some particular link that is not usually logistic link or probability link, some other link function we generated the data. Then we consider, suppose you are using logistic link function, and then we are using a model on family of link functions. So you see that logistic link function if you use, so then these are the parameter estimates, and the family of link function use, these are the parameter estimate. So the important part is that we are testing the hypothesis whether alpha 1 alpha 2 is different from the logistic link function or not. So we are considering this is equal to 1 1 because this is logistic link function, and this is not equal to 1 1 means it is a some other link function other than the logistic link function. Then we saw that the likelihood ratio statistic is 24 with 2 degrees of freedom, because difference is 2 parameters, and we get the p value is less than 0.001. Hence we reject the null hypothesis. That means the logistic model not adequately fitting the data. So the proposed model significantly better fit than the logistic model. So now we use some real data also for the link misspecification problem also. So it is under the working. We are working on, so we will consider both linear predictor and link misspecification, and we'll see that whether we are getting a better fit or not. Here we work out for the some data set, credit default data set. Here we are considering y equal to 1 and no equal to 0 for the default, or that person is default or not. And this is the balance. Balance is the credit limit for his or her account. So there is, if you give credit card, there is a credit limit. So we want to see that this variable is related to default or not, probability of default or not. So that means depending upon the credit limit, so the person is defaulted or not. So if you use a logistic link function, so we see these estimates, and then the family of link function, we see these estimates, we get this estimate. So beta 1, beta 1, and alpha 1, alpha 2, these are the values. You see that the alpha 1, alpha 2 values are different from 1, 1. So it is an indication that there will be a different link function than the logistic link function. There may be better fit. And also here we test the hypothesis that is null hypothesis is alpha 1 alpha 2 is 1 1, and alternatively alpha 1 alpha 2 is not equal to 1 1, and the likelihood ratio statistics is this with 2 degrees of freedom. P value is less than 0.001. So here also we are getting a significantly better fit using a family of link function. So this is the concluding remark that the proposed methodology provide a better fit over usual assumed form of linear predictor and link function. The methodology provide probability of default robust to the misprecision of the linear predictor and or link function of the model. So that we just at the beginning we found this result, but we have to do some future goal also. We have to find some implement some R package, or also we have to do more simulation studies to see the robustness of this methodology. Also any existing methodology also we have to compare. So then we'll conclude that this method be significantly better usually than the logistic link function. These are some of the references. There are many other references also. So just to mention some references. Okay, thank you. So I hope you may have followed some of the topic here. If you have any questions, please. Okay, so we are running out time also. So I hope you don't anyone have a question at the end. Also, you can ask questions any of the presenter here, invited presentation. So now I request. Hello, anyone? Please. Okay. So now I request the contribution session. 1 minute. So Dr. Mr. Monikanto Bhui.
Yes, sir.
So he is presenting on association of screen time with depression, anxiety, and stress for young people, age group 14 to 25, COVID-19 pandemic, a case study in Odisha. So I request Monikanto Bhui, please start your presentation. It is around 10 minutes, and because
Yes,
some other presenter also there, so then some question
Yes,
answer session also. Yeah, please.
Okay, sir. Sir, my screen is visible, sir.
You can make a presentation mode also.
Yes, sir. My screen is visible, sir.
Yes, visible. Yeah.
Okay, sir. Respected Satish sir, Das sir, and Arnab sir and Ananya ma'am. Thank you, sir, for selecting me as a contributory speaker. I am Manikant Bhoi from Central University of Odisha. My topic is association of screen time with depression, anxiety, and stress of young people. Age group is that is 14 to 15, 14 to 25 amid COVID-19. This study is done in the COVID-19 pandemic. And this is a case study done in the state Odisha. Here is my content. That is, first one is abstract, next is objective, review of literature, methodology, result, discussion, conclusion, some reference. Now, this is my abstract. That is, first one is the background. In COVID-19 pandemic period, it's seen that the general adult spare more times in the screen than usual day. In usual day, the adults are spending less time in the screen, but in the COVID-19 pandemic, they are staying in home, so they spend more time in the screens. The increase in screen time is subsequently growing problem among the adults in relation to the health behavior and the health outcome. This is getting a big problem in COVID-19 pandemic. The screen time is growing up, and the health problem that is in the health behavior and the health outcome is coming in the adults method. That is an 18-item screen time questionnaire was used to quantify the use of the commonly used screen device, that is television, smartphone, tablet, laptop, etc. for different time point during the week, weekday, weeknight, weekend. The test rate reliability is to assess the through intra-class correlation coefficient, that is ICC, and standard error measurement. The questionnaire was deliver online using Google, that is Google form. We use this is COVID-19 pandemic, so the primary data collection is done through the Google form, that we share this questionnaire through the WhatsApp, Gmail, Facebook, etc., and we get the respective results. This is the basing on the completed Google form. There are 304 adults from the Odisha were included in the final analysis. All items in the screen time questionnaire are so fair, excellent reliability. That is, ICC is coming 0.05 to 0.90, and all are significant. Expect the item inquiry about the using a smartphone during the average weekend day, that is ICC equals to 0.49, and this is not significant. The SCM value were large for the more screen types across the different period of the study. And in the end, I will tell this conclusion. Now the next one is this is my objective. Objective is the The aim of the present study is to explore the possible association between the screen time versus the depression, anxiety, and stress for the adult age group 14 to 25. Now, review of literature. In this new learning paradigm, the teachers are working as content to curator, and the parents are also stepping the predator to learn the children. Parents have the curator role in the education of the school children, since it can be preaching the those who are using the online platform of the first time. The success of the virtual schooling considerably depend upon the self-motivation of the student and the parents' engagement with the children. The sudden shift from the classroom has been given rise to the concerns such as for a long how this online class mode of the teacher and the learning will be continue, and what will be the impact such as shift to the children as well the parent mental, physical, and social. That is previously adopted article, that is reliability of a reliability of a new measure of SS modern screen time adults in the Marie Kreman Vengiaso et al. 2019. The questionnaire was delivered online using the administrator through Amazon that is M-Truck, US worker, and the M-Truck are more similar to the US population. This previously adopted paper was done in the US population and subject to recircuit the from the traditional universities subject poll and to provide the greater diversity in the term of age, ethnicity, and socio-economic status. Now, this is also the this paper is basically we want to see the while the students are staying at the home, what is their depression, anxiety, and stress level. Now, in the COVID-19 pandemic, there are students are basically in the home for the last 2 years. That is, what is their depression, anxiety, and stress level. Here we want to see the relationship between the screen time and the depression, anxiety, and stress level, and we are trying to see any any level of depression, stress, and anxiety, that what is the time they're spending in the screen time. That is, they are in the stress or not in the stress, and what is their screen time related to their depression, anxiety, and stress level. And here we found a positive result about the relationship among them. And we see the students are getting more stressed and repressed during the lockdown, and they are spending much time in the screen device due to it. They are in this paper we see that the adults were spending more time due to they are in the home, and they are we see that they are stressed, depressed, so they use the screen device more. In the adolescents, they use the screen time based media about 98%, and the TV from the maximum used media, that is 96%, they are using TV. The mean screen time they found 3.8 hour per day, followed by the other screen time based media. Significant association observed between the screen time and watching TV while eating. We asked them that they are using they are watching TV while eating or not. This is the work done. This is one another paper, that is work done in India. That is screen based media and screen time assessment among the adolescents residing in the urban colony of New Delhi. That is 35% of, and there they collected total number of 145 children view in the television. That is greater than 2 hours per school day. This Delhi work is basically done in the time of that is the holiday summer vacation period. That is this work is done in 2017 or 18, I guess. But this work is done in the time of the COVID-19 pandemic. Our work done in the COVID-19 pandemic. The study area, our study area is Odisha. The Odisha is the state belong the world's second largest population country in India. For the research, we take Odisha is our study area, and we take all the sample from the adults adults of Odisha for our analysis. Odisha is the coastal state which is near the Bay of Bengal, and the nearest state of Odisha is Jharkhand, West Bengal, Andhra Pradesh, Chhattisgarh. This may, I think all will know this. The data collection is to collect the data about the various subjects on the screen time. the screen time depression are collected using the appropriate primary data collection technique based on the questionnaire and the screen time previously adopted article, that is reliability of measure to the assess of modern screen time on the adult, that is Veljano et al. 2009. We use this questionnaire for the data collection of screen time, and to measure the depression, anxiety, and stress, we use the DAS-21 questionnaire for the depression, anxiety, and stress. The data collection was done in the period of August 2020 to February 2021. This is basically fully the COVID-19 period. We have collected total number of 304 number of sample in our data analysis for all over the Odisha. Due to COVID-19 situation, we have adopted a data collection mode online. Due to COVID-19 pandemic, we use the online mode of data collection. We create a Google form provided by the Google, and by sharing the latest social media platform, and we collected the 304 number of data analysis procedure. For this research, we use the statistical software, that is IBM SPSS Statistic 22 analysis tool. Here we found, while the analysis, the before lockdown and after lockdown data, we collected two types of data. One questionnaire which asks them for the screen time for before lockdown, and second one is asks them for the screen time after lockdown. We found all the data normally assumption and the positively skewed, and after transformation, median and IQR are the represented by the time variable. ICC and ICC, or the interclass correlation coefficient, was assessed for the relative reliability using two-way mixed effect model. If the value is greater than 0.75, then the excellent reliability, or less than 0.440, that is poor reliability. The value between 0.40 and 0.5 is each considered as the fair reliability, and the value between 0.60 to 0.74, that is a good reliability. Here we calculated the standard error measurement, that is ACM, using this formula, and the variance of the error is denoted by this, and it is represented in the ANOVA, known as analysis of variance. Two-sided 95% confidence interval. Interval is estimated. This is the formula, where the square of error is denoted as SEE.
Manikanto, you have 2 minutes only.
Okay, sir. This is our result. The total number of 304 adults have been aged from 14 to 25 years in the Odisha are enrolled for this research. From 62% were male, 37% are female. Then this primary data collection are found to be 56.8% have the family type nuclear, and 43.2% are the family type expanded. This is done, and this is next the result. I have less time, so I have to speed up my talk. This is the table one. They have hours spent in different screen device. The primary activity that before lockdown, their median of the TV use is 1 hour, but after lockdown it is gradually increased to the 3. The interquartile range before lockdown is 1 to 2 hours, that is in weekday, in weeknight and weekend. We collected this data for the TV connected device, laptop, smartphone, and tablet. This is our totally analysis, which is done by the SPSS software. Next, this is for the weekdays, weeknight, and weekend. This is for one is before lockdown, what is their screen use, and after lockdown, what is their screen use. This is you can see here the screen is totally increasing. Before lockdown, the median is 2 hours, but after lockdown, it is 3 hours. Now this is the interclass correlation. What is first one is the weekday, that is TV ICC. We get the 0.65. The confidence interval p value. Almost we get all are the significant correlation. This result, this is the standard error measurement. This is the SCM for before lockdown. This is the after lockdown. This is the mean of the SCM. This is 95% confidence interval, and then this is one the mean. This is for the weekend, weeknight, weekday, and background use. This previous one, that is SCM and ICC and reliability. These things are three. Tell us the association. That is the screen time and the depression, anxiety, stress. All are there will be significant association. But the totally new things that we want to know, that is our interest is that is there any correlation that is if depression is increasing, then the TV time is increasing. If TV time is decreasing, then the depression is decreasing. This correlation we want to know. So we use here the chi-square test. For first one is for depression and screen time, that is TV connected device, laptop, computer, smartphone. That is, if depression is increasing, then TV time is increasing. If depression is increasing, the TV connected device is also increasing. That is, we get the significant value. That is all for the TV connected device. All we get the significant result here. Then next we calculated for stress, that is also we get the significant result, and the last one is for anxiety, that is all the significant result. But for the case of tablet, we don't get it is significant. This is in the while anxiety is increasing, the tablet time is not increasing, and when tablet time is increasing, anxiety, this is not correlate for the anxiety case. In the tablet case discussion, this is all that we get there. This is the research all about the study of the reliability, absolute reliability, relative reliability, and screen time, depression, stress, anxiety. This is what we get in our discussion. Now I have no time, so I want to go to the conclusion. The result from this study suggests that the self-administered questionnaire can be used successfully and classify individual into the different category of the screen time, that is high use or low use. It was observed that the high proportion of the adolescents use the screen time more than recommended time. There will be a recommended time by for the screen time, but in the COVID-19 pandemic, the adults are using more than the recommended time screen time. That's why the health behavior and the health outcome of the adults of Odisha, or we can tell for India also, that this screen time, increasing of screen times, is mainly affect to the health behavior. So we believe that there should be a recommendation for maximum screen time spreadly for developing country like India. For India, we recommend that the maximum screen time is spreadly developing. This is my reference, and thank you everyone.
Okay, thank you, Manikanto Bhoi. And any questions? Yeah, any questions? Okay, so I request Dr. Satish sir to decide, because we have already, but we can continue if you can kindly recommend. So then we can get opportunity to.
Yeah, you have completed the session in time. In fact,
yeah.
But the other person,
yes,
he missed in the earlier session.
Yes.
If it is possible for you, left to you, whether you can give a 10 minutes a time.
Yeah. Actually, this is with your permission, because I don't have any problem. So I request Rasid A. Gane. So to present, he is presenting on a new generation of power quasi-Billy distribution with application in medical science. So it was in the contributory session in the distribution theory 3 in the previous session. So please complete, try to complete in 10 minutes, because you know that we are running out of time. Yeah, okay.
Yes, sir.
Okay.
Yes, sir. Okay, sir. Wait. Hi. 2 minutes. Yes, sir. 1 minute. Okay, sir. One minute, sir. Still joining now.
So Rasid, are you sharing your talk? Yeah.
Yes, sir. Shall my presentation appear on the screen, sir?
Yeah, please share. Then I think it will appear.
Sir, is it present?
I cannot see.
Sir, my presentation is appears on the screen or not, sir?
On this screen, I cannot see actually. I'm not sure anyone else can see that. So you can go the instruction. You can present now link, click on that, and then before that you open your file.
Sir, entire screen, sir.
Yeah. So then share it. Yeah, you share that screen.
So now commerce, sir.
No, I cannot see actually.
Sir, where we have to go on this?
Okay.
Present now. Sir, entire screen, sir.
Yes.
Sir, is it?
Yeah, now coming. Now coming. It is coming.
Now coming, sir.
But you have to click on your file, na? You can use. Yeah.
Sir, now now appears, sir.
Yes, it is appear. Yeah. Now start presentation. Yeah.
Yes, sir. Sir, actually, dear respected sir, good afternoon, sir. Dear sir, I am going to present the new generalization of forecast linear distribution. In this distribution, we have used the model weighted model and obtain its new generalization, and also obtain its new PDF, and also obtain its new CDF, and we have also obtained its mean and also its variance. Now this is the graph PDF of weighted power cost linear distribution, and this is also its CDF, sir. Sir, in this paper we have also obtained its reliability function, survival function, reliability function as survival function, and also we have obtained its hazard function, and also we have obtained its reverse hazard function, and also, sir, we have obtained its moment through the RF order moment, mean and variance. And also in this paper we have discussed, sir, it is Bonfori and Lodian curves. We have estimated it as actually the Bonfori and Lodian curves are known as income distribution curves. They are previously used in economics to study the poverty or inequality in income. Now, sir, we have also obtained it as order statistics. In order statistics, we denote the order statistics through the random samples x1, x2, so on to xn. We take the random sample x1, x2, so on to xn from a continuous distribution with cumulative distribution function and probability density function small f of x, and the probability density function of probability density function of order statistics is f of x or x equal to n factorial divided by r minus 1 factorial n minus r factorial into f of x raised power r minus 1 minus f of x raised power n minus r. Then we have used the PDF and CDF of weighted power cost linear distribution, and substitute in this RF order statistics. Then we obtain it as RF order statistics of weighted power cost linear distribution. Then also we have obtained it as higher order statistics of weighted power cost linear distribution when we take R equal to N, sir. And also we have obtained the latest first order statistics when we take R equal to 1, sir. Likelihood ratio test. Likelihood ratio, we have also defined it as likelihood ratio test of power linear distribution. Whether in likelihood ratio test, we test whether the random sample comes from the original distribution or the distribution which is executed. And also in this distribution, we have estimated its parameters through the maximum likelihood estimation. Through this method, we have estimated its parameters and also defined its Fisher's information matrix. And Fisher's information matrix is also obtained when we derive it second times to the second time to the same. Suppose if we take del log L by del theta, then we derive it another time with expected of del log square by del log square by del theta. Same is going on del log L square by del alpha square. Then we have fit the data in a weighted power linear distribution and compare the distribution with other distributions. So in order to show, this data set, we have to show that if the executed distribution shows less values than the other distribution, then it means that the distribution shows better fit and it will be used in real lifetime data for modeling. Then in this data set, we have fitted the medical data set of 65 dental patients, and then fit in the weighted power linear distribution. And we have compared with it the power linear and linear distribution. And the executed weighted power linear distribution shows the lesser value than the other distribution. Then it means that the distribution shows better fit than the power linear distribution, then the linear and linear distribution. Okay, sir. Thank you, sir.
Okay.
Yes.
Yeah, thank you, Rasid. Any questions from the audience, please? Okay, thanks, Rasid, for nice presentation. Any questions? Okay, so any questions from other presentation also? We have already run out the time. So let us thanks Professor Satish Kumar and organizers and also the presenter to give nice presentation here, Dr. Amanna, Dr. Arnav. Thanks. Let clap for the presentation.
Thank you.
Thank you, Professor Ishapadik Das, for your for managing the session in a nice way. In fact, we invited, and even though there is only one listed, two contributory you have.
It's fine, sir. Yeah.
Very nice way. Thank you so much for your support to our society. On behalf of ISPS, I extend our gratitude to Professor Dr. Ishapadik Das for chairing this session, as well as the speakers for other speakers for their nice presentations. Thank you all.
Thank you, sir. Thank you, sir. Thank you, sir.
We need your support in future also. Okay.
Yeah, sure, sir. Well, yes. Yes, thanks a lot, sir. Yeah. So let us conclude this session, sir, today.
Yeah. Let us conclude this session. Now let us meet. I think at 3:30 p.m. The next session.
Yes, sir. Yes, sir. Yes.
Okay. Thank you so much. Thank you all.
Yeah. Thanks all. Yeah.
In this session, one invited speaker and 6 contributor speakers are there. Dr. Manoj, please carry over the session.
Thank you, Dr. Sadish sir.
So this is good afternoon, everybody. This is the third parallel session, the second day of International Conference of ISPS. So first of all, I express a sincere gratitude to the organizers to give me an opportunity to chair this session. So on behalf of the organizing committee, I welcome all the speakers and all the distinguished participants and the professors to this section. And this section is dedicated on distribution theory. And in this section, we have one invited presentation and 7 contributed presentation. So for the invited presentation, we have Dr. Manjunath MG with us. So he is currently a faculty of School of Mathematics and Statistics, University of Hyderabad. And also, I think he is currently associated with the University of California, Riverside, USA. And his areas of research include extreme value theory, distribution theory, and so on. So he's an active researcher, and these have a lot of good publication in the international journals. And I invite Manjunath for his presentation, and he will be talking on bivariate pseudo-Poisson model. And Manjunath, you have 30 minutes for presentation, including discussion. Welcome, Dr. Manjunath.
So thank you, Manoj. So am I audible to everyone, right?
Yes.
Okay, thank you, Manoj. So first, I would like to thanks the ISPS conference, the committee members, and especially Professor Balakrishna sir, giving me an opportunity and inviting for me to the talk, and the current host institute, Dr. Satish sir, and the current session chairing Dr. Manoj for introducing. Okay, so this bivariate pseudo-Poisson modeling, so it has started so one and a half year before, and our journey has started. That I'm going to explain. The complete story has been. We'll go through that, and this is a joint work with Professor Berre Arnold, so from the University of California on Riverside. So everybody knows about him. He has huge number of contribution in the distribution. So part of the work is still going on, and one part of the work is already published in Journal of Applied Statistics recently. So this May it has been accepted and published. Okay, so let's go how our journey has started in this bivariate pseudo-model. So these are my agenda of topics, so which I am going to discuss in this session. Okay, first we'll go from what we know. So we know bivariate normal density is, so this is the form of the bivariate normal density, and we know a couple of properties of the bivariate normal distribution. So if we have a bivariate normal distribution, one-dimensional molecules are all normal. This is well known, and the conditionals are also normal. X given y or y given x, both are normal. And apart from normalities, the expectation, conditional expectation, is linear function of the conditional variable. Okay. So, and one more property is that the conditional variance is free from the conditional variance is free from the conditional variable. So these are the other two properties, excepting the conditional itself normal distribution. So if you fix that, this can we extend this properties to other distributions? So can we have a bivariate mass functions or bivariate density functions which has a similar property? For example, exponential or the Poisson. Do exist a mass function, bivariate mass function or cone distribution which has marginal Poisson, conditional Poisson, and the linear combination is Poisson? So for example, normal, if you have a normal distribution, linear combination is also okay. So is normal. So how far we can go for other distribution? This is the thing. So in that, if you relax any condition on this, you will have the counter example. For example, if you fix that, if you fix that looking at the marginals are normal, you cannot say that. If you know the marginals are normal, you cannot say that the current density what you are having is a bivariate normal. Okay, so none of the single unknown thing cannot characterize a normal, but combination of them we can characterize the bivariate normal, but single unknown property cannot be characterized. So for example, this is an example where you have a marginals are normal, but the joint densities are not a normal. So if you relax, if you going with the one property, and you will have a counter example for that. Okay, combination can characterize, but single alone property cannot be characterized. Okay, for the normal case. So if you look at the conditional as a normal and the marginal as a normal, yes. So you have a bivariate normal density. It can be marginal is normal and conditional is a normal. This is one-sided. Okay, so y is a normal and x given y is a normal. Conditional distribution is normal, but y given x is a not normal here. So if you derive this, so looking at the property at one alone, it cannot characterize. So you have another counter example for that. So this is a counter examples. This is a bivariate density. So you have here, it is not a linear function. A conditional expectation is not a linear, and the conditional variance is also not free from the normal variable. Okay. So now the thing is what I already told, that can we extend this property looking at, for example, for Poisson distribution. So do you have a multivariate or bivariate mass function which can give marginal as Poisson and conditional as a Poisson? So this is my idea to look at how far we can go for the bivariate structure extending to the Poisson distribution. So for example, so if x and y are independent random variable, just you multiply the marginals, then in the independent case, you can have the marginal as a Poisson. Okay, so this is an example. Next, so this is a classical result. So Johnson and et al. If you look at the multivariate the discrete distribution, it has been discussed thoroughly. So this is a classical one. So to have dependent marginal random variable x1 and x2, the marginal is each of the marginal is a Poisson. So earlier it was independent, but here it is a dependent random variable. So now what is the x and y? So x is x1 plus x12 and y is equal to y1 plus x12. Here x1, y1 and x12 are all Poisson distribution with parameter theta1, theta2, theta12. Okay, so define or to bring dependency between the random variable which has a Poisson marginals, we need three variable to have. So here x1, y1 are both are Poisson and another Poisson with parameter x12. Okay, so you need three variable to bring the dependency between the random variable where marginals are gives rise to Poisson with the parameter theta1 plus theta12 and with the parameter theta2 plus theta1. So this is up to margin. So here the conditionals are not Poisson over here. Okay. So next another thing is so you know the conditional form of, right? So by giant density can be written in the form of conditional and the marginal. So in this case, what I assume, so here I give only one as a conditional is a Poisson case. So another marginal you can take anything. So here one marginal I can bring as a condition. One conditional Poisson property can I bring from here. Okay. So this is a general case. This is valid for any, if you take any random variable, discrete, continuous, whatever may be y. So there is no restriction on this. So in this way, if you define, it will be a priority mass function. The only one conditional is Poisson, that is x given y is Poisson. Okay, so this is well-known result. So you classical distribution theory can expect. So other thing is, so here, so if you look at Arnold published one book. So Arnold and et al. Published a book on the conditional specification of statistical model. So what they have done is, so they have done for, it is not about the Poisson or normal. It is for the exponential family also can be extended. So for example, in the Poisson case, what they did, so they fix that my conditional x given y is a Poisson with parameter lambda of y1 and y given x is also Poisson with parameter lambda 2 of x. Now they are going to characterize all those bivariate mass function which give rise to x given y is a Poisson and y given x is a Poisson. So using the functional equation theory, they have equated the two equation, obtained the bivariate mass function. The bivariate mass function is given by this Kp of lambda 1, lambda 2, lambda 3. This is a function of the two parameter lambda 1, lambda 2, lambda 3, and lambda 1 to the power of x, lambda 2 to the power of y, and lambda 3 to the power of x, y, and divided by x factorial y factorial. So what you have? So you have a bivariate mass function where both conditional is Poisson. Okay, so this is, but marginals are not Poisson over here. Only in the independence case we can have. Independence case is lambda 3 has to be 1. So independence here. So therefore lambda 3 is equal to 1. You have independence in the model. Then you have the marginal. So only in the independence case you can achieve the marginality of Poisson. So here only the conditional as guaranteed. So in this case, for example, this classical Biot-Poisson case, right? So when theta 1 tending to 0, so this has a limit distribution what we have through that pseudo-Poisson distribution. What we have current model we introduced, right? Even the classical theory will converge to our pseudo-Poisson suggested that will come later. But this, if you make a note, the classical distribution is converging to our distribution, pseudo-Poisson. Okay, so this is the another thing. So next is we have a Sheshadri and Patel article. So we come across this Sheshadri Patel article. What he says that for a bivariate distribution of x and y, where x and y are not independent, then the following word: x follows Poisson implies f given y is not a Poisson. Y given x follows Poisson implies x is not a Poisson. So what he says that if x is a Poisson, if one marginal Poisson, then you cannot have x given y as a Poisson. Okay, if y given x is a Poisson, then x marginal cannot become a Poisson distribution. So what do you mean by that? There do not exist a mass function where both marginal, both conditional can be a Poisson. So the complete normal structure what we have, bivariate marginals are normal, both conditional are normal. So that cannot be extended to the Poisson structure. You cannot see. At most, what you can see, both marginal can be Poisson. If you want to have a dependency, that is a classical Poisson distribution. And if you want to have a both conditional as Poisson, then it is from the Arnold conditional specification mass function where they characterize all those families. And other these are what we have derived. So here I can have a one mass function, x is Poisson and y given x is Poisson. This is the only possibility it can have. Okay. So if x is Poisson, y given x is Poisson, according to Sheshadri particle, y cannot be a Poisson, and x given y cannot be a Poisson according to this theorem. Okay, so this theorem as derived using equating the two moment generative functions. This is the proof of that. So this is very simple proof. If you have to equate the two moment generative function, with the uniqueness property of the moment generative function, you can obtain that only in the independence case. It is both marginal can have Poisson, and another is conditional as Poisson is another thing. So there do not exist a bivariate mass function which has both marginal and both conditional as a Poisson. So according to Sheshadri theorem, there do not exist bivariate mass functions such that the both marginals and both conditional are being a Poisson. So this is not possible. So what is the only solution we have? So this is called pseudo Poissoning. So what we have? Pseudo in the sense we have only one marginal Poisson and one conditional is Poisson. So it is not completely. So that's why we call it as a pseudo Poisson distribution. So the k-dimensional distribution is said to be a k-dimensional pseudo Poisson if there exists a positive constant lambda 1 such that x1 follows the Poisson, so marginal is Poisson, and the conditional, so xl given the ln minus 1, so the lth variable dimension. So this is the dimension of l minus 1. So dimension of 1 only, so which is the conditional on the l minus 1. So this will also follows Poisson with parameter lambda l. So here if you restrict, so the lambda l function, which is a function of so the dimension k minus 1, okay, it has to be only the positive condition has to be satisfied. So there is no restriction on the function of the lambda of x. So in this case, in the bivariate case, we assume the simple. So where lambda l is that function, we simplified the linear function of conditional variable x1. So for the simplest case, what we assume this x1 is Poisson with lambda 1, and x2 given x1 is a Poisson distribution which is linear function of with the parameter lambda 2 plus lambda 3 x1. So it is a linear function of x1. So there is no restriction on the lambda l, the function what we are derived here. It has to be strictly positive. So that there is no restriction on the form of the function. So we assume only for the linearity assumption, and we are deriving what are the properties we can achieve here. So here the parameter space is lambda 1 has to be strictly greater than 0 because marginal is Poisson, and lambda 2 is greater than 0, it is there, but lambda 2 can also take 0 values, that is also possible, I will tell you. And when lambda 3, when the lambda 3 greater than or equal to 0, when lambda 3 is equal to 0, we have, so you have independency between the random variable, that is both will be poser, that is x1 is also poser, x2 given x1 is also poser with parameter lambda. When lambda 3 is equal to 0, then lambda 2 has to be strictly greater than 0, or else that it will be a. Okay, so in this case what they have done is, so classical bivariate Poisson distribution, what I am mentioning, that marginals as Poisson, where there is a dependency between the random variable. In that case, when that lambda 1 2 parameter is converging to 0, so that limiting distribution will be our pseudo Poisson at lambda 2 is equal to 0. So that theorem is also I will mention later. So that is the thing. So it has a relevance in the classical. So now if we have a density mass functions x1 and a conditional distribution is, and now we are trying to get what are the properties it will satisfy. So the giant, so probability generating function can be derived in this form. So probability generating function is x1 comma x2. So this is if you keep lambda 3 as 0, so you can easily check that it will be independent of two independent probability generating function of the Poisson distribution. Okay, with parameter lambda 1, lambda 2. Okay, so with this kind of things, what we have derived is the marginal distribution of x2, because marginal distribution of x2 we don't know. So marginal distribution of x1 is Poisson according to the way we constructed. So this distribution, marginal distribution of x2, what we are obtaining, it has a relevance in the literature that is called Neyman-Taipei distribution. So if you look at this Johnson, Kemp and Cott's book, they have defined this. So this kind of distribution is called Neyman-Taipei distribution. This is called Poisson mixture of Poisson random variable. So that will come after next slide, and I will explain what is the application of that. So the way we define the pseudo Poisson distribution, when the lambda 2 is equal to 0, it has a relevance in the classical literature. One of the marginal is relevance in the classical literature, that is follows Neyman-Taipei distribution. Okay, mass function. So now, so this is how the bivariate distribution are. Now we do, so this is the way we define that pseudo Poissoning is so new to that. And can we look at whether the literature there existed this kind of distribution X? One is modeling the accident and fatality distribution modeling. So in that, so what we have, so in this, if you want to model, there your x be a random variable denoting the number of accident, and y will be the number of fatality. So what is the case? If x is the number of accident, for each of the given accidents, how many fatality will be y? So when x itself is 0, then y has to be 0. There is no accident, means there is no y. So in this case, x and y both cannot be 0. Okay, when x is 0, then y cannot be 0. That is completely ruled out. Okay, so this is as exactly fitting our pseudo Poisson distribution when lambda 2 is equal to 0. So they have, so this has the classical application also. It has been so it has been already done, which is relevance in this. But the way they derived and the way we are obtained is completely different. So, but when the lambda 2 is equal to 0, both model will coincide. So this is the application of this later and Yamadani articles. They are analyzing the traffic accident, the fatality data. They have derived this model. So next is another relevance is the article by Peter and Eric. So what they have done, so they work in the financial section. So in the both classical bivariate Poisson and the pseudo Poisson, what we have obtained is both cannot have negative correlation. Both are positive correlation. So what they have done to bring the negative correlation in the model also, what they have done, define the random variable Z1 and Z2. So it will be just a mixture proportion. So Z1, when pi is equal to 0, you will have, when you allow y1 density, and when pi is equal to 1, you have, so when pi is equal to 1, you have y1. So this has to be y2. So there is a, okay, so when pi is equal to 0, you have y2. When pi is equal to 1, so you have from this z1, we can have y2. So from here you will have y1. So then again it will be density of mass joint density of the Poisson random variable only. So depending on the given the pi, they are going to derive the pseudo Poisson distribution. So that is, they have introduced the lambdas in such a way that it can be extended to the generalized linear model. So where they bring the x as a covariate information which is known, and the beta parameters and the epsilon I error terms. In the picture, lambda 1, lambda 2 parameters they bring, and they are ready to fix the introduce the GLM model into that. So here what is the issue is there? Here pi has to be given. So when pi is equal to 0 or 1, which is exactly equal to our pseudo Poisson, but here what happens? So our first one pseudo Poisson is x1 is Poisson and x2 given x1 is Poisson. Okay, this one model, and another model what you can have, x2 is Poisson, we make marginal x2 as a Poisson, another is x1 given x2 is a Poisson. So there are two ways of defining the pseudo Poisson model. So but if you have a count data, if one of the model fit, other doesn't fit the model. So here this what they have done, they bring both the model into that. Your data will tell which of the order you have to follow. So whether you have to take a marginalized x1 as a Poisson or marginalized x2 as a Poisson. If you take x2 as a Poisson, then x1 given x2 has to be Poisson. Conditional distribution has to be Poisson. Okay, so they brought pi to select the order of the variable. So this is also in the literature they have mentioned all those things, and it is closely related to our model. So if you look at all the movements of the pseudo Poisson, so since x1 is a Poisson distribution, marginal is lambda 1, and x2 is not a Poisson, which is equal to the Neyman-Tapier distribution, which the mean is lambda 2 plus lambda 1 lambda 3. Okay, so variance can also be defined in this way, and the covariance you can define, and the correlation function also you can define in this way. So there are a couple of conditions on there. So when lambda 2 is equal to 0, your correlation only depends on the lambda 3. So there is no effect of lambda 1 in the dependency. Okay, when the lambda 3 is equal to 0, and we already said that rho is equal to 0 because x and y are independent. When lambda 1 is equal to lambda 3, this is a submodel. So then you have again dependency between the model. But our case is also restricted. You are on the positive side. So the correlation function is greater than or equal to 0 only. It is strictly positive. Okay. So in this already provide the relevance in the classical literature, but this characterization.
Excuse me.
Yeah.
About 3 more minutes.
Yeah. So this has the characterization of the random the pseudo Poisson. So whenever your conditional is a linear function of random variable x1 and x2 is a Neyman-Tapier distribution, then with the giant distribution necessarily has to be pseudo Poisson distribution. So in that case, we also obtain the Fisher index of dispersion also we can compute. Yes, since marginal is Poisson, x1 is a equidispersion, and you can show that x2 is a Neyman-Tapier distribution, which is over dispersion, and in the overall. So the pseudo Poisson distribution is a overall fitting a count data which is greater than 1 means it is over dispersion. For the over dispersion count data, you can use the our suggested pseudo Poisson distribution. So these are all some of the movement estimator how can you obtain. So this we have done, and so how to obtain the MLE? MLE is so for the lambda x1 it is well known you can obtain. But this has to be solved numerically because there is no direct solution. For lambda 2 and lambda 3, you have to solve by numerical. These are all the things we have done, testing and all there. So the simulation work also we have done for sample size this. So if you look at this, so when the sample size increases, the true parameter lambda, so dependency. So I assume 0.86 as the correlation. So all the limits, everything has been defined over here. So the moment estimator of the correlation, MLE estimator parameter, sample size increases, all this. So these are all the sum of the confidence interval, and for the submodel means when lambda 2 is equal to 0, when lambda 2 is equal to lambda 3, all those possibilities are the submodel. So this has application also where the health and retirement data can be fitted for this, and for that how to select whether it has to be x1 or x2. So because first you check the marginal distribution Poisson, if it is equidispersed, there exists so much of literature in that how to test for the marginal distribution. In that select First you test whether x1 has to be 1000 or x2 has to be 1000, then fix that x2 is a 1000 or x1 is a 1000. Once you fix x1 as a 1000, then x2 given x1 has to be 1000. So like that, the fitting the model can also be simple thing, and the dependency also you may resolve. So here the dependency is rejected, so that's what we are bringing into the model. So there are two models, lambda 2 is equal to lambda 3. We have fitted that. In that comparison between all those literature articles and all those things, so our bivariate pseudo Poisson model, full model is the best model, because AS is the least one for this, because our model is only the 3. So there are other model is there, COMMAXO model, the model is there, that is also bivariate Poisson, but they bring include the parameter to bring the dispersion in the index into the model. So we compared with that result, and another application accident data we consider, and we compared with the other results, and still our model is performing, because we have this Conway Axel Poisson distributed bivariate, where the margins are over dispersion index with the Poisson distribution. There are 6 parameters, but it is over dispersion data with the only 3 parameters, our model. So these are the things. So we have opened the goodness of fit test also using the chi-square, where we have restricted the count with up to 4+. So which are all higher than the 4+, we are converting as the 4. So in that also we have done goodness of is how to obtain the marginal distribution of x2 using the probability generated function also we have done. And another approach is using the distance measure. So the distance measure is difference between the actual probability generated function minus the empirical probability generated function. So this is actual and this is the empirical. So that measure also we have done. And the one data is accepting the null hypothesis, that is Chaudhary and the L data is accepting, but other data, Liter and Ahmadini data is rejected according to the distance measure of goodness of it. So these are all other future work is coming like. So we are introducing the generalized introducing of GLM and the Bayesian analysis and the model selection. So since you have conditional, right, the order has to be there. So if you have only bivariate, order is x given yr to x2 given yr. So if your dimension is more, how to select the order. So that also we are doing. And all this is coming in a R package that is going to be published soon. So these are the references I have mentioned. So I thank the to correct chair session. So thank you for giving an opportunity to present my work. Yeah. Any questions?
Thank you, Manjunath.
Yeah.
Any question? We have a little time. Only one question from the audience. Sorry.
Manjunath, can we just extend this model for generalized Poisson also? Have you looked?
Yeah, that's what. Yeah. That's what the thing we are doing. So that we don't know how far we'll go, but the extension thing and all is there. So the only one thing is the Conway Maxwell is there. The Conway Maxwell model they will call bivariate distribution, that is very flexible. So with the over dispersion, under data, under dispersion, all those things will fit, but it has higher number of parameters. On the computation, everything you have to depend on the numerical. Even the marginal computing the probabilities also, cell probability also, everything is you have to depend on the numerical solution. There do not exist a closed form expression for even for the probability computation also. Our model is very simple. You can do all the exercises, and also the linearity is there that can also be extended for other function of conditional variables also.
Okay. Thank you.
Yeah.
Okay. Thank you, Dipesh, and thank you, Majna. If there is not time for further questions, if anybody has any question, please contact Manjunath personally. So let us once again thank our speaker Manjunath for the nice presentation and it's a good work. Thank you.
Thank you, sir. Thank you.
So now we have contributor presentations. We have 7 presentations in the list. So before starting, just make an attendance. That's Nandini is there. Nandini.
Yes, sir.
Okay. Divaga.
Yes, sir. I am present.
Yes.
Here,
Okay.
sir.
Mariam Muhyiddini. Mariam.
Yes, sir.
Okay. Arbi Ade.
Yes, sir.
Yes. Govada Tarun.
Yeah, present, sir.
Remy Reddy Nagini.
Yes, sir. Present, sir.
Okay. Okay. All the seven speakers are here. So first presentation is by Nandini V, and I invite Nandini V for her presentation, and she is talking on record-based transmuted power law max distribution theory and application. So for contributor speakers, you have total 15 minutes, including discussion. Okay.
Okay, sir.
So our first speaker, Nandini, please.
Okay, sir. Thank you, sir. Shall I start, sir? My screen is visible, sir?
Yes, visible.
Yes.
Okay, sir. Thank you, sir. Good afternoon to all. I am V. Nandini, Department of Statistics, Bardiyar University. My study is a record-based transmitted power law mix distribution, theory and application. Abstract of my study. In this study, we present a new 4-parameter continuous probability distribution called record-based transmitted power law mix distribution. In shortly, RBPLX distribution, which is more useful for modeling lifetime data set. Further, we present a various statistical properties such as moments, quantile functions, entropy, order statistics, and its expressions. The maximum likelihood method is used to estimate the parameters of RBPLX distribution, and the new extended model is applied to a real data set, and it shows that the performance of RBPLX distribution is relatively better when compared to other well-known suitable distributions. Introduction of my study. In statistics, record values or record statistics is the largest or smallest value obtained from a sequence of random variables. The theory of record statistics is closely related to order statistics. Record values and its associated statistics are important in many real-life applications. In industry, many products fail under stress. For example, a wooden beam breaks when sufficient perpendicular force applied on it. An electronic component ceases to function in an environment of too high temperature. A battery dies under stress of time. But the precise breaking stress or failure point varies even among identical items. Hence, in such experiments, measurements may be made sequentially and only the record values are observed. Thus, the number of observations made is considerably smaller than the complete sample size. This is also known as a measurement saving method. That is, when the measurements of this experiment is costly if the entire sample was destroyed. There are situations in which an observation is sorted only if it is a record value. This includes studies in meteorology, hydrology, economics, athletic events, and live testing studies. This is my contribution part. Record-based transmitted map. Balakrishnan and he 2021 proposed a record-based transmitted map to generate new probability models. At x1 to x1, x2 be a sequence of independent and identically distributed random variables with the distribution function. Let x of u1 and x of u2 be a first two upper records for the sequence of IID random variables. We defining the random variable y, which is equal to x of u1 with probability 1 minus theta, x of u2 with the probability theta. Theta belongs to 0, 1. The distribution function of y can be described below. The record-based transmitted distribution is obtained by the above equation, that is f y of x, which is equal to g of x plus theta g bar of x log g bar of x. X belongs to the positive real line and theta belongs to 0, 1, and its corresponding probability density function is given in the below equation. Lomax distribution. The Lomax distribution, also known as a Pareto type 2 distribution, was proposed by K.S. Lomax in 1954. It is a heavy tail distribution and which is basically a shifted Pareto distribution. which is widely used in survival analysis. It is popularly used as an alternative to power law, exponential, gamma, and Weibull distribution for modeling heavy-tailed data in the domain of business, economics, and actuarial science. This is a definition. A random variable x follows the Lomax distribution with the two parameters, shape parameter beta greater than 0 and the scale parameter lambda greater than 0. Its cumulative distribution function for x greater than 0, f of x, which is equal to 1 minus of 1 plus x by lambda the whole power minus beta. And its corresponding probability density function is f of x, which is equal to beta by lambda 1 plus x by lambda the whole power minus beta plus 1. Power Lomax distribution. The power Lomax distribution is obtained by using the power transformation of a random variable x, which is equal to t power 1 by beta. The random variable t is said to follows the Lomax distribution when x follows the Lomax distribution. The random variable x follows a 3-parameter power Lomax distribution with the shape parameter beta and theta greater than 0 and the scale parameter lambda greater than 0. The probability density function and the cumulative distribution function of power Lomax distribution are described here. Record-based transmitted power Lomax distribution. The random variable x is said to follows the 4-parameter RBPLX distribution with the shape parameter alpha, beta, theta greater than 0 and its scale parameter lambda greater than 0 if the CDF of x greater than 0 is given below. And the corresponding PDF of RBPLX distribution is described over here. This is the plot. This is the cumulative distribution plot of the RBPLX distribution. Figure 2 shows that the probability density function plot of RBPLX distribution. Here we are fixing that the values of alpha and theta, alpha equal to 1.5 and theta equal to 1, and changing the values beta equal to beta and lambda. We are getting that the curve is right skewed, increasing and decreasing over time. The survival functions, the second figure is for the theta value equal to 0 and then changing the values of beta and lambda. The survival functions of RBPLX distribution is also obtained here. Then the hazard rate functions of RBPLX distribution is obtained as follows. And the figure 3, which is a hazard rate plot of RBPLX distribution, the hazard rate curve, which is decreases over time for the values of alpha equal to 1.5 and changing values of beta and lambda and the fixed value of theta. Quantile function. The quantile functions of RBPLX distribution is obtained as follows. The closed form of quantile functions can be derived with the help of Lambert W function. Lambert W function is defined as the solutions of this equation below. W of v, e power w of v, which is equal to v. V is a complex number. For a real number, v greater than or equal to minus 1 by e. The Lambert W function has only two branches such as w0 and w minus 1. W0, which takes a value between minus 1 comma infinity, and w minus 1 takes a value between infinity comma minus 1, and for v belongs to minus 1 by e comma theta. Finally we got the closed form of quantile functions of RBPLX distribution. And then the moment generating function, the orth moment of this distribution is given below, and by using this orth moment, we are getting the first moment and the mean of the distribution. And then the incomplete moment of RBPLX distribution is obtained as follows. The first incomplete moment of this distribution is described here. By using this incomplete moment and the first moment to get the Bonferroni and Lorentz curve, which is most useful in the economic studies, order statistics. Let x1, x2, xn be a sequence, be a random samples of size n, and let xk is to 1 denotes the ith order statistics. Then the PDF of xk is to 1 is given by the below equation. And then we can rewrite the above equations as follows. Then from this we getting the PDF of order statistics. Then record statistics, let xu of 1, etc. xu of n be the record values from a sequence of xi, which is IID random variables from an RBPLX distribution. As a probability density function of upper record values, x of un is defined as follows. F un of x, which is equal to r of x the whole power n minus 1 by gamma of n f of x. x ranges from minus infinity to infinity, r of x which is equal to minus log of f bar of x. F bar of x ranges from 0, 1. The PDF of nth upper record values x u of n for the RBPLX distribution is defined below. F un of x which is equal to alpha beta lambda power alpha x power beta minus 1 by gamma of lambda plus x power beta the whole power alpha plus 1 into minus log of lambda power alpha by lambda plus x power beta the whole power minus alpha 1 minus theta log of lambda power alpha by lambda plus x power beta the whole power n minus 1 and 1 into 1 minus theta into 1 plus log of lambda power alpha by lambda plus x power beta the whole power alpha. This is the PDF of nth upper record value. And then the PDF of nth lower record values, that is xl of n from the RBPLX distribution, is defined by using f ln of x which is equal to 1 by gamma n into minus log of f of x the whole power n minus 1 into f of x. By using this, we getting the lower record PDF of nth lower record values. By using this nth upper record value and lower record value to get the records of our distribution. And then the entropy provides an outstanding tool to compute the amount of information or uncertainty contained in the random observation concerning its parental distribution. A large value of entropy implies the more uncertainty in the data. Here we have derived the Rini entropy. Maximum likelihood estimation. Let x1 to xn be a random sample from an RBPLX distribution with unknown parameters alpha, beta, lambda and theta. Then the likelihood function is given below. By using this,
Excuse me?
Sir?
You have 2 more minutes.
Yeah, okay, sir. From this, we are getting the first order partial derivatives and equating them to 0 for each and every parameters to get the estimated values. And then here we have discussed two different data sets. The first data set is the blood cancer data set of 40 patients. Then the table 1 shows that the estimated values of the parameters and likelihood value and information criteria value among this 3 distribution. Our RBPLS distribution gives a better fit when compared to other 2 distributions by using the minimum information criteria values and maximum log likelihood values. Table 2 describes the goodness of fit test of RBPLX distribution. Here we have discussed here 3 different test statistics. Among this 3 distribution, we are getting that RBPLX distribution gives a better fit. The data set 2 is that the dataset contains exact time of failure of fatigue fracture of Kevlar 3735 epoxy. And then table 3, the estimates and information criteria of RBPLX distribution for second dataset. Among this 3 distribution, RBPLX LOMX and Half Logistics LOMX, RBPLX distribution gives a better fit by using the minimum information criteria values and log likelihood values. This is the goodness of fit test. Then conclusion of my study. In this study, a new 4-parameter LOMX distribution is proposed called RBPLX distribution based on the record-based transmuted map. The usefulness of newly defined models is illustrated using the real data sets. The application illustrates that the proposed model provides a consistently better fit than other advisory models. These are my references. Thank you, sir.
So thank you. Any quick question?
Nandini?
Sir?
Hello, Nandini?
Sir?
We are using goodness of fit now. Which test do you fit? Which test statistics?
Cromer von Miss test, Kolmogorov-Simoneau test, and Anderson-Darling test I have taken.
Why are you not using chi-square?
This is the parametric test, sir. I have used this 3 tests.
Oh, okay.
Okay, sir.
So, okay, fine.
Okay, sir. Thank you, sir.
Okay. There is no more question. Let's thank Nandini for the nice presentation.
Yes, sir.
So thank you, Nandini. The next speaker is K. Divagar
Yes, sir.
And he will be speaking on transmitted sine diagram distribution and its properties. Divagar, please.
Yes, sir. Yes, sir. Good evening to everyone. First of all, I would like to thank to the organizing committee of this ISPS conference for giving me a wonderful opportunity to present my paper through the virtual mode. Shall I present my presentation, sir?
Yes.
Yeah.
It's my visible, sir?
It is fine now. It is fine.
Okay, sir. Thank you.
Yeah.
Okay. Now I am going to present my paper entitled Transmitted Sine Diagram Distribution and its Properties. I am K. Divagar, Research Scholar of Department of Statistics, Bharatiya University, Coimbatore. And statistical distribution is very useful in describing and predicting the real-world phenomena. The lifetime distribution played a vital many research areas such as economics, engineering, finance, medicine, biological science, among and so on. Yes, sir. In recent years, extension and generation of probability distribution have attracted. One second. Hello, sir. Okay, sir. Hello.
Okay. Carry on.
Okay, sir. In recent years, extension and generation of probability distribution have attracted many statisticians and the researchers. For example, exponential family of distribution proposed by Gupta et al. 1998. The exponential family of distribution provides the flexibility by adding a one more parameter to the distribution and attract the several statisticians and the researcher. The several classes of distribution have been introduced by adding one more parameters to generate a new probability distribution in the statistical literature. Here we listed the sum of well-known generating family of distribution like Marshall-Algin family. Generative family is introduced by Marshall and Algin 1997. Exponential generating family is introduced by Gupta et al. In the year of 1998. Quadratic rank transfer map is introduced by Shaw and Buckley 2007, and the Kumaraswamy generating family is introduced by Cardier et al. 2011. Now I am going to concentrate the three parameter of continuous diagram distribution is proposed by Cabello diagram in the year of 1977, particularly for the empirical income and wealth data. The diagram distribution is classified into the two specification, type 1 diagram distribution and the type 2 diagram distribution. In this research paper, I have focused the type 1 diagram distribution. The type 1 diagram distribution has one scale parameter and the two scale parameter. It is also known as a inverse per dual distribution, particularly in the actuarial literature. The type 1 diagram distribution also heavy-tailed distribution. Damma et al. 2002 studied the characteristic of diagram distribution. Its hazard function can be monotonically increasing and the decreasing. In this paper, we introduce a new generalization of transmitted sine diagram distribution using the transmitted sine G family studied by Sektivel et al. 2021. We obtained some mathematical and statistical properties for the proposed distribution. It's namely transmitted sine diagram distribution. Some of the authors done the literature work in this field. Here I mentioned a few of work. Recently, I focused the last four work. Rasit et al. 2020 proposed the top-down diagram distribution for air conditioning systems data. Nasir et al. 2019 introduced the exponentiated generalized exponential diagram distribution for failure time dataset. Kumar et al. 2015 introduced a new generating distribution. It's called sine function. Its application to Platter-Canson patient data. And Saktivel et al. 2021 studied the transmitted sine G family of distribution, some properties and application. The diagram distribution. The PDF and the CDF of the diagram distribution given in equation number 1 and 2 respectively. Here we have the three parameters sigma and theta, beta always greater than 0 and the random variable also greater than 0. Here sigma is represented by the scale parameter and theta and tau are the shift parameter. And recently, Olidev et al. Developed a comma diagram distribution for income and lifetime data. It is pertinent to note that if
If you put the value sigma is equal to 1, the PDF of diagonal distribution became a birth redistribution, and if theta is equal to 1, it's became a log logistic distribution. The transmitter Jain Sine G family. Introduced by Satyul et al. 2021. This family has only one parameter. The transmitter Sine G family is a mixture of transmitter map and the sine function. The PDF and the CDF of transmitter Sine G family of distribution given in equation number 3 and 4 respectively. Here we have only one parameter lambda. Here we represent the small h of x is the probability density function of the base distribution, and capital H of x represented by the distribution function of base distribution. Here we have the parameter lambda. It's range between -1 to +1. Here the proposed model transmitter sine diagonal distribution. The PDF and the CDF of the transmitter sine diagonal distribution given in equation number 5 and 7 respectively, and also we simplify the PDF for using to find the characteristic of transmitter sine diagonal distribution. Here we have the 4 parameters sigma, theta, beta, and lambda. Its range greater than 0. Here sigma is the scale parameter of diagonal distribution, and theta are the same parameter of diagonal distribution, and lambda is the parameter of quadratic rank transmitter map. Here you can see the behavior of PDF for transmitter sine diagonal distribution. Here we fixed the 3 parameter value sigma 0.5, theta is equal to 1, beta is equal to 2, and different value of lambda 0.1, 0.3, 0.5, 0.7, 0.9. We obtain like this curve. You can see the second density function. Here we fixed the 3 parameter value, and another one parameter is the sigma is the different value. We obtained some properties. It is a right-tailed distribution. The behavior of CDF of transmitter sine diagonal distribution given this slide. It is satisfy the condition, satisfy the properties. The value is increasing from 0 to 1. Likewise, we obtained the reliability function of transmitter sine diagonal distribution and behavior of Cassault rate function for transmitter sine diagonal distribution. We have obtained some of the reliability measures in this section. The reliability function and the Cassault rate function given in equation number 8 and 9 respectively, and the reverse Cassault rate function, cumulative Cassault function, sign failure rate function given in yes ma'am, given in equation number 10 to 12 respectively, and mean waiting time, mean residual life function given in equation number 13 and 14 respectively. So, shall I continue, sir?
Yes.
Yeah.
Sir, shall I continue, sir?
Yes. You have 4 minutes more.
Okay, sir. We have obtained some statistical properties like earth moment. We have obtained the first 4 moments given in equation number respectively, and the variance of transmitter sine diagonal distribution given in equation number 17. The moment generative function, characteristic function, cumulative generative function given in equation number 17 to 20 respectively, and also we obtained the incomplete moments for the transmitter sine diagonal distribution given in equation number 21, and central moment also obtained. Now we move to the order statistic. The order statistics used for the parametric test and the order statistics. The J order statistic for transmitter sine diagonal distribution given in equation number 24, and a PDF of the smallest order statistics, PDF of the largest order statistics, PDF of the median order statistics given in equation number 25 to 27 respectively. And also we have obtained some income inequality measure like Lawrence curve, Pohnpeier index, Jenga index given in equation number 29 to 30 respectively. Now we move to the parameter estimation of transmitter sine diagonal distribution. The maximum likelihood estimation method used to find the unknown parameter of transmitter sine diagonal distribution. Here we given the likelihood function in equation number 31, and the log likelihood is given in equation number 32. We take the partial derivative with respect to the parameters lambda, sigma, theta, and beta given in equation number respectively 33 to 36. The above mentioned four nonlinear equations are very difficult to solve analytically. We can solve these nonlinear equations through iteration method like neat absorption method and regular policy. However, we estimate the parameter using the R software package. Now we move to the application for transmitter sign dagger distribution. Here we can see the data set is expressed about the time to failure of 100 centimeter polyester viscose in textile experiment in order to evaluate the tensile fatigue characteristic of the yarn data. It is a strain level is 2.3%. This data set is recently studied by Nasiri et al. 2017. We have selected the statistical model selection based on the minimum value of the statistical measures like log likelihood, archaic information criterion, Bayesian information criterion, corrected archaic information criterion. Like in table 1, I explain about the summary statistics for tensile fatigue of characteristic of yarn data. And table 2 expressed about the estimated parameter values and the information criterion value for tensile fatigue characteristics of yarn data. Here we compare the different statistical model like exponential Kumarasamy distribution, McDonald dagger distribution, exponential generalized pressure distribution, likewise, and the proposed distribution transmitter sign dagger distribution. You can see the statistical measure of the transmitter sign dagger distribution provided the less value compared than other statistical model, so that we conclude our proposed model is the best model and if best fit for this particular data compared than other statistical model. Now I move to the end of this presentation. In this paper, we present a new generating distribution named as a transmitter sign dagger distribution from the transmitter sign family of distribution. We have studied some reliability measure like reliability function, hazard rate function, reverse hazard rate function, cumulative hazard rate function, sign failure rate function, mean waiting time, and mean fast life time also. We have obtained some basic statistical property like moments, moment entry function, characteristic function, cumulant generative function, incomplete moments, central moments, and order statistic. We also derived some income inequality measure, including Lorentz curve, comparative index, and Jenga index for the proposed deep probability distribution. The maximum likelihood estimate method is used to estimate the parameter of proposed new probability distribution. Finally, we have analyzed a real lifetime data set for the proposed probability distribution. These are my reference. Thank you, sir.
Okay, thank you, Divada. Any question or queries? Okay, if there is no questions or query, let us thank Divagar for the presentation. Thank you, Divagar.
Okay,
Our
thank
next
you,
speaker is Mariam Mahuddin. Is Mariam here?
Yes, sir. I'm
Okay.
here.
Okay, and she will talk on the alpha power transformed Cauchy Ardhana distribution with its properties.
Yes, sir.
Welcome, Mariam. Please proceed.
Yes, sir. Start sharing. Not sharing your screen, the other one. Wait, sir.
Yeah.
The presentation. Sir, I will send you the presentation first.
No. You please put in a presentation mode.
Yes, sir. You try and share the screen. Meeting.
Can I present, sir?
So how will I share this presentation?
Okay, in the Google Meet, there is a option not present now. There is an upward arrow in the
Here is options. Share
present
screen.
share screen. Okay.
Sharing.
Here, fifth option is the present now.
Yes, sir. Okay. Am I audible, sir?
Yes.
Okay, sir. Thank you, sir. Visible, sir, slide?
No. Now
No,
is
no.
it?
Good evening, sir. Good evening, all of you. Myself, Rajeshwar Ade.
Excuse me. Excuse
Hello,
me,
sir.
Rajeshwar. Is Mariam is going to present now?
No,
Not
sir.
you?
Next, fifth number, sir. Fifth number.
Okay,
1
sir.
minute.
Sir, I am unable to share this screen.
Okay, you just try. Never. So you can present the next presentation also. So just now I invited Rajesh to present paper.
Okay, thank you, sir. Good evening, all of you. Am I audible, sir?
Please try.
Hello, sir. Am I audible?
Okay.
Okay, sir.
Yeah,
Good
yeah,
evening, all of you. Myself, Rajeshwar Ade. I am doing research under the guidance of Dr. N.W. Andure, Department of Statistics, Government Reserve Institute of Science and Humanities.
Wait. Just wait. Rajeshwar.
Rajesh, sir.
Ah, sir.
You please stop your presentations. Mariam is.
Otherwise, Mariama is stopped the presentation. This is better, sir. I think she was starting in mobile. I think she was in mobile.
Yes, sir. I'm in mobile. Mobile.
No. You go
Mobile,
to
with
laptop
mobile,
is
it's not
better.
possible, sir, I think.
Not possible.
Presentation.
Mobile is not possible, sir.
Not possible.
Mariam,
Yes, sir. I'm hearing.
are you able to present?
But sir, without screen sharing, I can present, but
You
I can
can't because of you using mobile now. You can't present. There is no option in mobile.
There's no option on mobile.
Yes, sir. Yes.
No. There is option number also. Present.
But it will be complicated, sir.
Nikila,
Okay.
The 99 amtuna papa.
Okay, Mariam, you please try after the presentation. Now I invite Rajesh Radhe to present his paper.
Okay, thank you, sir.
Divakar,
Please visible, sir.
Yes.
Good evening.
Divakar, please unmute.
Myself, Rajeshwar
Divakar,
Ade.
please unmute. Divakar.
Divakar K.
Please,
Sir, Divakar.
mute.
Please mute.
Okay.
Good evening, all of you.
I have muted.
Myself, Rajeshwar Ade. I am doing research in the guidance under the guidance of Dr. N.W. Andure. Today, I am going presenting here the new length bias Cauchy-Lindley distribution and its application. Now, there contains introduction, length bias Cauchy-Lindley distribution, reliability analysis, and this some of all the part in this paper. Now, introduction. The Cauchy-Lindley distribution was introduced by Shankar and Misra in 2013. The Cauchy-Lindley distribution has two parameters, alpha and theta. The Cauchy-Lindley distribution reduced to one parameter Lindley distribution if alpha equal to theta, and if alpha equal to 0, it reduced to the gamma distribution with the parameter 2, theta. The probability density function of Cauchy-Lindley distribution is combination of exponential and gamma distribution, and their PDF is f of x theta, that is equal to theta upon 1 plus alpha into alpha plus theta x into e to the power minus theta x, and their x greater than 0 variable, and this parameter theta is greater than 0 and alpha is greater than -1, and their CDF, that is cumulative distribution function of Cauchy-Lindley distribution, is f of x theta equal to 1 minus 1 plus alpha plus theta x upon 1 plus alpha into e to the power minus theta x. Now, review of literatures. Elvatal et al. In 2013 studies the various property of transmuted Cauchy-Lindley distribution. He also discussed the Kumar-Swamy Cauchy-Lindley distribution. Bora et al. In 2015 developed two-parameter discrete Gaussian linear distribution and it discussed its application to lifetime data. Maravi et al. In 2015 studied the McDonald Gaussian linear distribution and its application. Now, Alcarni in 2015 obtained the power Gaussian linear distribution and it discussed their properties. There some researchers also have studied the Gaussian linear distribution. They transmitted Kumar-Swamy Gaussian linear, Poisson Gaussian linear. So now, length bias Gaussian linear distribution. Length bias distribution is a special case of weighted distribution, which were the first introduced by Fisher in 1934 to model ascendant bias. These were far ahead formalized in unifying theory by Rao in 1965. Weighted distribution arises when the observation generated from a stochastic process are not given equal chance to being recorded, but they are recorded in accordance to some weight function. When the weight function is depend only on the length of unit of the interest, the resulting distribution is called length bias distribution. The length bias distribution concept was firstly given by Cox in 1969 and Zelen 1974. Weighted distribution have become a milestone for efficient modeling of statistical data and prediction. When the standard distribution are not suitable, there are a lot of work has been done in the length bias and original distributions. Lappy and Belli in 1987 used weighted distribution to analyze ISPS diameter increment data. Mir and some of the authors have studied the length bias beta distribution and length bias negative distribution. Now, the definition of weighted distribution, the non-negative random variable x is said to have weighted distribution if the PDF means probability density function. PDF of weighted distribution random variable is given by here f of x equal to w of x. This is our weight function and this f of x is original density function and upon this is expected function of this weight function into PDF that is less than infinite. For the different weighted models, different choices of different weight function can be done. When x tends to c, the resulting distribution is termed as weighted distribution. In this paper, the length bias version of Gaussian linear distribution is studied. Here, choice of c equal to 1 is done as weight in order to get the length bias Gaussian linear distribution. And the PDF of length bias Gaussian linear distribution is given by, so here x into f of x theta upon expectation of x, where expectation of x equal to this integration 0 to infinity x into f of x dx. So by substituting the equation 1 and 4 in equation 3, the PDF of length bias Gaussian linear distribution is obtained as this. This is the PDF x into theta square upon alpha plus 2 into alpha plus theta x e to the power minus theta x, and their CDF is LBQL, length bias Gaussian linear distribution, that is a short form is LBQL. So this is alpha into incomplete gamma 2 comma theta x plus incomplete gamma 3 theta x and this. Okay, so now the the PDF, this is the plot of PDF of length bias Gaussian linear distribution. This is PDF and now this is the CDF plot of their parameter there 1.4 alpha 0.4. This is parameter increases and also alpha is increases. Now reliability analysis. In this section, the survival function, hazard rate function, reverse hazard rate function, Mills ratio are discussed length bias. The survival function is also known as reliability function and this is hazard rate function, reverse hazard rate function and Mills ratio. Now next, this is the survival plot and this is the hazard plot. Here theta value is increases, then the hazard ratio is decrease. Here theta equal to 1.2 and alpha equal to 0.5. And next theta equal to 1.4, alpha equal to 0.6, theta equal to 1.6 and alpha equal. Parameter is increased, theta is increases, then also hazard rate is decreases. Now the next, statistical properties. In this section, the statistical properties of length bias Gaussian linear distribution. Let x denote the random variable of length bias Gaussian linear distribution with parameter theta and alpha. Then the earth order moment about origin of length bias Gaussian linear distribution is obtained as, and this is our earth moment theta square upon alpha plus 2 into alpha gamma into r plus 2 plus gamma r plus 3 upon theta raised to r plus 2. Now substitute the value of 1 to r equal to 1 2 3 4, then we will get the first 4 moments, and after is mu1, mu2, mu3 and mu4, and this is variance, coefficient of variation, coefficient of dispersion. This is like this all. Now next, the moment generating function. Moment generating function is the expected function of random variable. The well-known definition of MGF is given by, this is the MGF, and this is, and now similarly characteristic function phi of x to the mx it, and now this is harmonic mean. Now the order statistics, the probability density function of the order statistics, jth order statistics. Here this is definition. Now substitute the equation 5 our the CDF, and equation 6 is our PDF of length bias Cauchy Lindley distribution equation 8. Now we will get the jth order statistics of length bias Cauchy Lindley distribution. Now next, for j equal to 1 in equation 9, therefore the probability density function of first order statistics of length bias Cauchy Lindley distribution. This is the first order length bias Cauchy Lindley distribution, and this is nth order Cauchy Lindley length bias Cauchy Lindley distribution. Now entropy. Entropy is the most important role in reliability and other. So for the given probability distribution of renew entropy is given as, this is equation 1 upon 1 minus delta, and theta log of theta to the power theta square upon alpha plus 2, and this. And now next, Tesla's entropy. Tesla's was introduced in 1918 by C. Tesla's. The basic for generalizing the standard statistical mechanics. The generalization of Boltzmann-Gibbs statistical property presented by Tesla's has been discussed. For the continuous random variable x, Tesla's entropy is defined as follows. This is after simplification for this final answer. Now Born-Ferronian-Lorentz curve. So here Born-Ferronian-Lorentz curve. This is utilize a field like reliability, medicine, defense, and demography, financial matters. So this is Born-Ferroni curve and Lorentz curve. Now next, likelihood ratio test. Let x1, x2 up to xn be a random sample from the length bias Cauchy distribution. The test hypothesis is h not equal to f of x alpha comma theta against s f1, and this is the likelihood ratio. This FL is length by Cauchy Lindley, and this f of x is Cauchy Lindley distribution. Now after simplification, this for the large sample length n, 2 log delta distribute the chi-square distribution with 1 degrees of freedom, and also p-value is obtained from the chi-square distribution. The reject null hypothesis when the probability value is given by, this is probability of delta square in B star, and the product of xi is observed value of the statistics. Now we'll discuss parameter estimation, that is by using MLE, maximum likelihood estimation. This is the likelihood function of length bias Cauchy. Hello sir.
You have 2 more minutes.
Yeah, okay sir, thank you sir. This is the likelihood function, and here we estimate parameter by using MLE, and we use R software. So now next, the application. In this section, 2 real life data set are the study of the flexibility of the length bias Cauchy Lindley distribution. Now, and with the criteria like that, AIC, BIC, AICC, HQIC. The first real life data set is break mistakes carbon, and second is real life, that is fetish life data. Now these results show that the length bias Cauchy Lindley distribution is better, and this Cauchy Lindley, this is a base distribution. This is length bias Cauchy Lindley. And now conclusion. In this paper, the length bias Cauchy Lindley distribution is proposed as new extension of Cauchy Lindley distribution. Now the generated by using length bias technique and taking the Cauchy Lindley distribution as the base distribution. Now they studies various statistical property of proposed distribution have been derived and discussed. Supremacy of the new distribution in real life is established with the demonstration of real life data set, and it is found from the result data set that the lengthwise Gaussian distribution is performs of better than the Gaussian distribution. There are several references here we use this paper. This is a, and thank you very much.
Thank you. Thank you, Rajesh sir. Any questions from the audience? No? Okay. If there is no question, let us thank Rajesh sir for the presentation.
Thank you very much, sir. Thank you. Thank you, sir.
Again, so next presenter is Provada Tarun.
Yes, sir, I'm here.
Yeah, okay. And
Shall I go?
working on identification of risk factors associated with overweight or based on urban area of Visakhapatnam. Yeah.
Sir, my voice is clear, sir?
Yes.
Shall I go now, sir?
Yes.
Yeah, good evening to one and all. Myself, Govada Tarun, working as a research scholar under the guidance of Professor B. Muniswamy Garu, Department of Statistics, Andhra University, Visakhapatnam from the Andhra Pradesh. So my research paper entitled with Identification of Risk Factors Associated with Overweight Obese on Urban Area of Visakhapatnam. So abstract: obesity is strong associated with multiple risk factors. Worldwide, morbidity and mortality are significantly increased to the risk of chronic disease. So the study used the binary logistic regression model to investigate overweight and obesity among the urban area of adults on the basis of their demographic profile, medical history, and daily lifestyle characteristic, including gender or sex, region, eating speed, number of meals per day, sweet and meat habit. The respondents are influenced by obesity in family and interaction between ethnic and routine meals intake. The odds of the respondent being overweight and over.
Tarun, your
Sorry, sir.
slide is not moving. You just choose the slide from the left side. Your slide is still in the first slide.
1 minute, sir. Is it okay now, sir?
No, it's now presentation. Yes, slide is visible.
Is it okay, sir, now?
It's visible but not moving.
Yeah, now?
Yes, yes, yes.
Yeah, okay, sir. Okay. The study of the measurement and proportion of the human body status was assessed by the calculating by the body of body mass index. So that is nothing but BMI. So actually my research paper is outliers of this paper is introduction and objectives, literature review, methodology, analysis, and conclusion, inferences. So first of all, first one is introduction. So my paper is based on only logistic regression. So my introduction is divided into two categories. First one is about logistic regression, and second one is for the body mass index, overweight and obese. So first one is, what is the logistic regression? So the logistic regression is a sort of regression analysis used to predict the outcome of a variable categorical responses variable based on one or more predicted variables. So it is also called binary logistic regression is one of the logistic regression analysis technique where by the response variable is dichotomous. So dichotomous means nothing but it's a two categories. So if we code it as the two categories into 1 or 0. So for the one is success and the second one is failure is coded as a 0. And the final results is not predicted of a numerical cost. In the linear regression, however, a probability of belonging to certainly one of conditions that may take any values between 0 and 1. Each theoretical and empirical outcome suggests that when the response variable is binary, the form of a response function is curvilinear that resembles either as a fitted S or reserved titled S. So in this case, if the logistic regression is by the case of, if it is two categories, we can use binary case, that means binomial distribution. If it is more than two cases, we can use Poisson distribution. It is also called multinomial logistic regression. So now it is about obesity introduction. A health weight or normal weight means that your body mass index falls within the weight range that is not associated with an increased risk weight related disease and health issues. So body mass index is determined by the height and weight. So body mass index does not measure body fat, but it's often correlated with direct measure to the body fat. A higher body mass index tends to indicates a higher body fat, and a lower body mass index lower body fat. Adult body mass and children and teens are calculated by differently. It's also important to remember that body mass index BMI weight category is not an indicator of your overall health. Being within a healthy weight range does not necessarily mean that you are healthy. Being underweight or overweight does not necessarily mean that you are unhealthy either. So how to calculate body mass index? So here the formula is mass in the kgs divided by height in meter squares. So for example, in the weight equal to 74 kgs and the height is 164 centimeters, then we can calculate body mass equal to 74 divided by 1.64 meter square, that is 27.51. So there is totally classification of the body mass index. So here we have only underweight, overweight, obese. So if it is underweight means less than 18.0. In this underweight, we have 4 categories: several thinness, moderate thinness, mild thinness, normal range, and the overweight is pre-obesity is also available. And here the classification is obese. So 3 categories: first obese 1, obese class 2, obese class 3. So obesity means greater than 30. In the case of here, we can use body mass index values. Okay, 27.51 means that value undergoes so pre-obesity. So like that we can classifying the body mass index here, and my objectives are to investigate the obesity on the adults living in the Visakhapatnam urban area, to study the cause of overweight and obesity, to analyze the overweight and obesity on this basis of the demographic region. So demographic region means age, gender wise, like that educated persons are not. So to study the gender based changes in the overweight and obesity, to analyze the measurements and proportions of the human body status was assessed by calculating the body mass index. So these are the literature of review. So Nagendra K et al. So they done work on the same logistic regression, but they done work in the rural area of the students. And the Rajan Kumar P. Jitendra Gowda 2004 have studied the prevalence of overweight and obesity among the women. So they studied about among the women. And Daniel JC and Subramania SP 2019, they study cardiovascular. So there is a relation between heart diseases and also obesity or overweight diseases. Okay, they studied about cardiologist diseases, and the risk factors of the represent a major and increasing burden of death and disability in India. And the last one, Pengpid S and Pedles K 2019 have studied the prevalence and correlates of underweight and overweight of or obesity among women in India. So So methodology is nothing but by the using logistic regression. So generally, logistic regression is from the regression model. Actually, regression having two types. So linear and non-linear. In the case of linear, we can use simple linear and multi-linear regressions. In the case of non-linear regressions, we can use logistic. So in that logistic regression, we have either another two types. So if it is logistic regression dependent variable having two categories, then we can use binomial dichotomous logistic regression. If the logistic regression more than two categories, we can use multinomial logistic regression, that is nothing but Poisson distribution we can use in that case. In the case of dichotomous logistic regression, we can use binomial distribution. In this research paper, we done with dichotomous dependent variable having dichotomous. That means we can use binomial distribution. Here we have used in this research paper. So another concept, odds and odds ratio. So that is the logistic regression. Actually, the logistic regression is from the generalized linear model. So in that generalized linear model,
excuse me, Tarun, you have 5 more minutes.
Yeah, okay, sir. So in that generalized linear model having dependent variable and independent variable, nothing but random component, that is y dependent variable, and systematic component, that is explanatory variable. And the third one is very important, that is the logistic link function. So that is nothing but link function. We have to use logistic regression function. So there odds and odds ratio. In that logistic regression, we have used odds. So what is the odds? Odds is nothing but the ratio between ratio of the success and failure. For example, in the case of, so see here, the odds are p given 1 minus p. If the p given 1 minus, for example, p small, probability of success equal to 0.8 and probability of failure is nothing but 1 minus 0.8 means 0.2, then the odds value equal to 4. That inference, that means, so 4 times of every success having one failure, that is the odds. And odds ratio is nothing but ratio of two odds. So here the logistic regression function pi equal to exponential terms of beta naught plus and so on beta k x suffix ki over 1 plus e power same value, numerator value, e power beta naught plus and so on b suffix k x suffix ki. So next, my analysis, actually my data is purely secondary data from the Visakhapatnam urban area, and by using SPSS package, statistical package for social sciences. So by using that package and the frequency distribution of body mass index. So my sample is out of 450, among them overweight persons are 115 and obesity 185, normal 150. And these are all the analysis. So gender wise distribution of respondents and age wise. So here females are 264 out of 450, males are 196. So these are the age wise distribution. So below 30 168, 31 to 40 184, above 40 is 98. So logistics means, so dichotomous variables. So here we are using grouping variables, means whether the person having or male or female having obesity or not. So with respect to gender, so then we get the significant value between our H0 null hypothesis. There is no significant association between gender and grouping variable. So here our association is highly significant. There is at the rate means not significant value, significant at 5% means 1 star, double highly significant means it's significant at 1%. So from the above table, chi-square is significant at 1%, a rejected null hypothesis. It means that there is a significant association between gender and grouping variable. So, and also chi-square for the gender and age wise, gender and BMI, body mass index. So coming to the logistic regression here, variables in the equations. So out of my 6 variables, there is 3 variables, that is gender, age and BMI are highly significant. So my conclusion is, through this model, likelihood for getting outcome of a particular factor is determined by explanatory odds quantitative relations. The results of the study indicated that being overweight and obesity among the urban area adults. Influencing factor are age, gender, BMI are highly significant. The risk of urban adults being overweight and obesity increased with their weight of the respondent. In the study, observed that the lack of exercise and who are taking routine meals, those who respond are suffering with obesity and overweight in this urban area of Visakhapatnam. So these are the my references. So thank you, sir.
Okay, thank you, Tarun. Any question? So any question? Yes.
Yeah, I have a question.
Okay, please.
And one comment. Thank you for very good presentation, dear presenter. But I have a comment in objective number 2. You are saying to study the causes of obesity, to study the causes of obesity. So in my opinion, I think you could say to study the risk factors of obesity instead of saying causes, because in regression analysis, no matter how strong the statistical relation, no cause and effect may be implied by the regression analysis. So there, I think you should use to study the risk factors of obesity. That's one. So I didn't hear the research yet of this study. Maybe the presenter can say something. But also the research design also. I didn't hear about the research design of this study. That's all. Thank you.
Okay, thank you. If there is no more question, let's thank the speaker Tarun once again.
Thank you, sir.
And, is Mariam here? Mariam? No. Okay. Our next speaker is Ramaredi Munangani. Is ready, Ram?
Yes, sir. I'm ready, sir.
Okay, and he'll be talking on extreme value characteristics and the analysis of means based on exponential inverse Kumaraswamy distribution.
Yes, sir.
Please.
Okay, sir. I hope my screen is visible to all of you.
Yes.
Thank you, sir. Good evening, one and all. So myself, Ramaredi Munangi, a research scholar on the guidance of Professor K. Roshia, Professor of Statistics, Acharya Nagarjuna University, and I co-guide Mr. Dr. B. Srinivas Rao, Associate Professor. Okay, today's my talk is on extreme value charts and analysis of means based on exponentiated inverse Kumaraswamy distribution. Okay. Now, in our study, the main abstract of the study is the probability model of a quality characteristic is assumed as a exponentiated inverse Kumaraswamy distribution. So, in short, we can say it as EAKD. The variable control charts are established based on the extreme values of each subgroup. Okay. The constants of these control charts depend on the probability model of the extreme order statistics and size of each subgroup. The procedure of analysis of means for a skewed population is executed to exponentiated inverse Kumaraswamy distribution. And
Excuse me?
Yes, sir.
If possible, can you increase the size of your screen?
Yes. Okay, sure, sir.
You can make it full screen. Yeah.
Yes, sir. Slide show. Okay, sir. Yeah. And these studies, that means extreme value charts and the ANAM control charts, are given with some illustrated with some live examples also. Okay. And the main references I have taken for this paper, for this analysis is the first one is the statistical properties and applications of the exponentiated inverse Kumaraswamy distribution, published in Journal of Reliability and Statistical Studies, given by Kazer, Fatima, Uzma, John, and S.P. Ahmed. That is the main distribution we have considered for our study. And for analysis of means, we have considered ORT, ER, and Rouse ER CV reviews. And for extreme value charts and INM charts, we have considered Srinivas Rao, Pratap Reddy J, and Roshia's paper. Okay. And main introduction of the distribution. See, our considered distribution, the probability density function of the exponentiated inverse Kumaraswamy distribution, in short we can say it as EAKD, is given as f of x is equal to alpha beta lambda into 1 plus x whole power minus of alpha plus 1 into 1 minus of 1 plus x whole power minus alpha to the power of beta lambda minus 1, where x greater than 0 and alpha, beta, lambda are the parameters of this distribution. And these three are shape parameters only, which are greater than 0. And the CDF is given as like this, that is a capital F of x in equation 1.2. And the corresponding mean of the distribution is expectation of x, which is given here. And the corresponding quantile function, that is q of u, is defined like this. That is 1 minus u power 1 by beta lambda whole power of minus 1 by alpha minus 1. Okay, where u follows the uniform random numbers from 0 to 1. Okay. And the corresponding PDFs of EAKD and CDF of EAKD at different parameter levels are provided here, presented in these graphs. Now, the first one, that is extreme value charts, control charts. Actually, the control limits are obtained by the concept of extreme order statistics based on EAKD model, with the assumption that the specified sample follows EAKD model. These control lines are established based on the randomly selected observations xi from the given sample that falls inside the limits with a probability of 1 minus alpha whole power 1 by n. And these can be formulated as probability inequalities as P of x1 less than or equal to L, that is equal to alpha by 2, and P of xn greater than or equal to U, that is equal to alpha by 2. Where here x1 and xn are the extreme values of the given sample. Okay, and in this construction of the control limits, we can use the solutions of the equations 1 minus f of x whole power n, that is equal to 0.00135, and f of x whole power n, that is equal to 0.99865. So the main reason to selecting these limits, that is 0.00135 and 0.99865, is within these limits the probability is 0.9973, that is on par with the normal distribution 3 sigma control limits actually. Here f of x is defined as the cumulative distribution function of the selected EAKD model. And the solutions of these equations for the sample sizes for n is equal to 2 to 10 are given in the table 2.1, in this table only. And these are all the percentile values based on the at a different sample sizes we are constructed in the based on the percentile values of the distribution. Okay, these are the control limits of extreme value charts. And the values of above table 2.1 indicate the following probability statements. The first one is the probability of the percentile values is in between. That means any z value is in between these percentile values with probability of 0.9973. And by considering that x value, so sigma of z into z less than xi less than sigma of z upper limit value, that is equal to 0.9973. Now, by considering the estimate of sigma as x bar into 2.5089, this 2.5089 is the mean of the selected distribution EAKD, and this equation becomes probability of Lx bar less than xi less than ux bar, that is equal to 0.9973. That means any sample point comes in the limits of these two, Lx bar and the ux bar, is with the probability 0.9973, where L is defined as the low, that means the specified percentile value at 0.00135 divided by 2.5089, and upper limit value correspondingly given like this, where this L and U would constitute the control chart constants for the extreme value charts. Okay, so for the sample sizes for n is equal to 2 to 10, the L and U, that means the lower limit and the upper limit, are presented in this table. So for different sizes of n, 2 to 10, n is equal to 2 to 3 up to 10 values, we have presented the lower limit values and upper limit values, and these are the constants for preparing the extreme value charts. Okay, and based on that we can even write the, that means we can even calculate the average run length of the extreme value charts, and these average run length values are calculated using this formula 1 minus p by p, where p is equal to this formula, that is 2 minus of f of u whole power n minus 1 minus f of L whole power n. These average values are calculated here for different sample sizes. N is equal to 2 to 10 it is. These are average run length values based on the extreme value charts. And the next analysis is analysis of means. Now, the control charts are developed using the subgroup means to examine whether the population from which these subgroups are taken is operating with admissible quality variations. We state that the production process is under control when all the subgroup means fall in the control limits, else we decide that it is out of control. If alpha is the level of significance in the above conclusions, we can have the following probability statements. That is, the probability of any sample mean within the limits of LCL and UCL with the probability of 1 minus alpha. Since we consider all the samples are independent, generally we consider all the sample means would be in the limits of LCL to UCL with the probability of 1 minus alpha whole power 1 by k. Now, with equitable probability for each subgroup mean, the two constants L star and U star, this is a simple name, a different name only, can be calculated such that the probability of xi bar less than L star, that is equal to probability of xi bar greater than U star, that is equal to 1 minus alpha whole power 1 by k divided by 2. These constants are computed in accordance with the subgroup size n and the number of subgroups k. Suppose if you consider some k subgroups are there, and in each subgroup we consider some n sample observations are there. Then for that all levels we have considered we have calculated the constant values, and we obtain L star and U star for alpha at different levels alpha, that is 0.01, 0.05, and 0.10 at specific n and k through the percentage of EAKD using the equation 3.3, this above equation, and these results are provided in the tables 3.1, 3.1, 3.3. So with the space for the purpose, just I given a hyperlink for this to provide this constant actually. So I can show you these all values here at different levels of n and k. So for n is equal to 2 to 10 sample observations, and for k is equal to, these are all subgroups actually, 1 subgroup, 2 subgroups, 3 subgroups, like up to 50 actually at different levels I have taken. So in the table 3.1 I have presented for 1 minus alpha is equal to 0.99, where alpha is equal to 0.01, and in table 3.2 as we are given the same value, same type of values at 0.95 probability, and thirdly that means we are given at 0.90, that is alpha is equal to 0.10. Okay, now coming to my slide. Now if the conclusion in any control chart for averages displays in control, which specifies that all the subgroup means through differ among themselves but are homogeneous in some sense. This conclusion supports the null hypothesis stated exactly in the analysis of variance technique. Hence, the constants supplied in tables 3.1, 3.2, and 3.3 can be used as an alternative in analysis of variance technique. In general, for a normal population, we can use the tables of given in 1967 for EAKD, and for EAKD, our tables can be used. Herewith, we exhibit a few examples for which the goodness of fit of EAKD model is assessed with the QQ plot technique, that is the strength of linearity between observed and theoretical quantiles of a model, and tested the homogeneity of means involved in each case. See, that's we have considered one example here for testing the our values of EAKD on par with the normal distribution values. See, in example 1, here we have considered some data of 25 observations manufacture of metal products. That means that was considered for 5 suppliers here. In each supplier, there are 5 sample observations are there, and these are the proportion of weights or percentage of weights in the metal actually, percentage of iron weights in the metal actually. 5 samples are taken in each supplier. And as a second example, we have considered 3 brands of batteries, considering the life of the battery in weeks actually. So 3 brands are tested here: brand 1, brand 2, and brand 3. Okay, in third example, we have considered 4 catalysts that may affect the concentration of one component in a 3-component liquid mixture. So particularly 1 component mixture measurement we have considered here. So total 4 catalysts are taken. That means 4 subgroups we considered, 4 subgroups, and in each subgroup there are 4 observations in this example. So for these 3 examples, yes, we have tested. That means we have checked with whether the data is fitted with the distribution or not, or selected distribution. So by using the QQ plot technique by the correlation coefficient method, the given examples or the data given in the previous 3 examples are better fit with the EAKD model with a probability that is 0.92 double H, and example 2 is a better fit with a correlation value of 0.84, and third example is a better fit with correlation value of 0.837. Whereas these are all examples are not much better fit with the normal distribution actually. And these QQ plot graph also are presented in the hyperlink like this. Okay. Yeah. And now, after the construction of this ANM control charts, we can conclude that we have presented some values based on these in accordance with the comparison of normal distribution. So first of all, we have constructed some normal distribution control limits actually. By using this normal distribution, Based on the previous 3 examples, in example 1, the LDL, that means lower decision limit and upper decision limit values are given like this. And whereas all the sample subgroups means actually are in out of 5 values, out of 5 subgroup means or 5 subgroup observations, only 3 are in control and 2 are out of control actually. So 60% of the values are in control and 40% of the values are out of control. Whereas in example 2, by applying the normal distribution, we observed that there are only 2 observations or 2 subgroup values which are in control and only one value out of the control it is. And in example 3, we observed that there are only 2 observations which are inside and outside. There are 2 observations, so 50% only. But whereas if we apply our distribution, that is EAKD model, which is that means we have given some constants of the EAKD model values for ANAM charts. So here we got some LDL and UDL values for examples 1, 2, and 3 constructed here. And now by comparing with the normal distribution, here we can say that the number of observations or number of sample subgroups actually which are in the control, that means inside the control limits, are 5 up to 5 observations only. Out of 5 are inside, in control. And in example 2 also, out of 3 observations, out of 3 subgroup values, 3 are inside only, that means 100% only. And example 3 also, actually in example 3 we have considered 4 subgroups. All these 4 subgroup values are in control only here, so 100% it is. And for this, the main reason is we have previously we have tested the given data is better fit our distribution when compared with the normal distribution. So it is better to use our distribution, that is EAKD, in the construction of ANAM charts. And finally, the conclusions are the decision lines using the normal distribution indicate that the number of means inside the control limits for each data set is 3, 2, and 2 respectively, and that outside of the limits is 2, 1, and 2 respectively, based on the given examples. Whereas by using ANAM tables of our model EAKD, for the same data sets, the number of homogeneous means are 5, 3, and 4 respectively. That is 100% without presenting any deviation from the homogeneity. So here finally we have confirmed that EAKD is a better model than normal model through the QQ plot correlation coefficient of each data set, which was established with normal as well as EAKD separately. As a result, we have confirmed that more error is likely to be associated with the decision process of normal distribution when compared to the EAKD model. Okay, so in this quality control applications, one may consider other models for the construction. Actually, this is a skew distribution model actually. Okay, so if your data set follows this type of skew distribution, it is better to follow apply this type of distributions when compared to the normal distribution model. Okay, and finally, just I given some references here, which is given as hyperlink. Okay, so with this, I conclude my presentation. Thank you, sir. Thank you very much.
Okay, thank you, Ramaredi.
Thank you, sir.
Any question? Any questions or queries regarding the presentation? Okay, if there is no question, let us thank the speaker, Ramaredi. And we have, is Mariam present here? I think Mariam is not here. So this is the end of our section. So on behalf of the organizing committee, I thank all the speakers to complete the presentation in time. So once again, I thank each and everyone. I also thank the organizers to give me an opportunity to chair this section. And the section is over. Now the session over to our organizers.
Okay, thank you. Mariam is not here, or one is missing, isn't it? So, contributory speakers.
Yeah, and she is not able to present. He is presented in the early part of the session, but he is not able to present.
Okay. Then she will come. Whether she is in the group?
Not. So she was not able to present. So.
Okay. She was not here in the group, isn't it? So she's not here in the group, isn't it?
Yes. She's not here.
Okay. Okay, if she is not here, let us conclude this session. I utilize this occasion on behalf of the Indian Society for Probability and Statistics and University of Kerala, Department of Statistics, I extend our heartfelt gratitude to Dr. Manoj Chaka for chairing this session, and Dr. Manjunath for his invited talk, and other speakers for their presentation, nice presentations. Thank you so much. Thank you. Thank you all. Let us give a big clap to each one of them. Now, yeah. Now the next session will start at 5:35. Yeah, 5:35.
So I think you have 15 minutes to relax.
Yeah, 15 minutes.
I think today, I think this session got over much early. Manoj.
One speaker is missing here. The one contributor speaker is
I
not
see.
here.
I think in Madurai, when you also, there were 3 contributing speakers were absent.
Okay. So she was here in the group earlier, but she couldn't present it.
Maybe some network problem.
Yeah, maybe network issues. Yeah. Anyway, let us.
Let us take break for 10-15 minutes.
Yeah.
Okay. See you at 5:35.
Okay. See you.
Yeah.
Okay. Thank you.
Thanks.
Okay, sir.
Thank you, sir.
Thank you, sir. Thank you.
Okay. Thank you. Okay, welcome to all to the session. In fact, now we have a session on biostatistics, and the 2-hour session start from now. To chair this session, we have Dr. Sebastian George. I have already given an introduction today morning. Even then, just a brief introduction to him. Dr. Sebastian George is presently the head of the Department of Statistical Sciences of Kannur University, and he is an active researcher and did several works. Especially, he has some works related to biostatistics, and is in fact adjunct faculty of Department of Biostatistics of Christian College, Vellore Christian College. And I am not extending too much because our Thomas Matthew are waiting for his. Everyone is waiting for his talk. Nice talk. I invite Dr. Sebastian George. Please carry over this session. Better, nice way, please. Sebastian, you are not mute. You are, please unmute. Please unmute.
So we have 6 talks in this session, 2 innovator talks and 4 contributory talks. The first innovator talk is by Professor Thomas Matthew. I'm very happy to introduce Thomas Matthew here. He is a friend of all research scholars in Kerala and India. He is an alumnus of Indian Statistical Institute. He was a lecturer there.
In Kerala University also?
He was an alumnus, I'm sorry, he was an alumnus of Kerala University also. In fact, he is hailing from middle part of Kerala. And he is winner of W.J. Uden Award by ASA and Fellow of ASA IMS. And at present, he is working as a professor, Department of Mathematics and Statistics, University of Maryland, Baltimore County, USA. He was a strong theoretician. He did his PhD in robust regression, I suppose I'm correct. After that, at present, he is working in biostatistics, applied statistics. With your permission, I am inviting Professor Thomas Matthew to give the talk.
Okay, let me start by sharing my screen. Give me one second.
That upward arrow mark, that is the share button.
First you
Yeah, I know.
open the slides and place somewhere, and
Let me
then go to
see.
the upward arrow mark in the bottom. There is upward arrow mark. There is a just to go present now button is that is a present now button.
Okay, give me 1 second. Let me try a different browser.
Sure, sir, no problem.
Hi, Thomas Matthew. How are you? Sebastian.
Yeah. So 1 minute, Professor Matthew is taking the slides up for presentation.
Okay.
Can you see my screen?
Yeah, it's pretty good. Yes,
Okay. That's good. Okay. First of all, I want to thank the organizers, in particular Dr. Sadish Kumar, for inviting me to give this presentation, and Dr. Sebastian for chairing the session and for mentioning some kind words about me. And it is always a pleasure to meet familiar faces, at least online. For example, Dr. Balakrishna. So I could briefly chat with them before the session. So thanks to everyone, and thanks to everyone who is present listening to me. Okay, I'm going to talk about this, a very applied problem, what is called inter-laboratory calibration. And the problem is one of estimating, one of confidence interval calculation. So I'm going to start with an example. So this example deals with measuring the concentration of the chemical cadmium in various samples. And the measurement is done using what is called graphite furnace atomic absorption spectroscopy. I don't know much about it. In any case, we don't have much time to discuss the details of that either. Now, cadmium is a chemical that could be toxic, and that is present in soil samples, then rock, then coal, and so on. So prolonged exposure to cadmium can cause kidney problems, cancer, and so on. So accurate measurement of cadmium is very important. So the question we want to address is this particular measuring method called AAS, how accurately can it measure the cadmium concentration in a sample? So the way it is done is as follows. So you prepare samples in a laboratory when you know that these samples contain a known concentration of cadmium. Basically what you do is you take some sample, soil or whatever, then you spike it with a known concentration of cadmium. Then you measure the cadmium concentration using the methodology AAS. Use the data to set up a model relating the measurement to the cadmium concentration. And then we can use the model to estimate an unknown cadmium concentration in a sample. So this is pretty much the problem. So here is the data. So we are actually looking at 4 replicate measurements of the cadmium in a sample by the method AAS. So there is the data. In the first sample, the cadmium concentration is 0, no cadmium. And then the AAS method, one measurement was indeed 0, and then some measurement. These measurements are scaled and coded in some way. That is why they come out as negative. Then you spike the sample with a concentration 2.7784 part per billion. Then take the measurement 4 times. You keep repeating it a few times. And then here you have an unknown, you have a sample with an unknown cadmium concentration mu. But you can still take the AAS data, and these are the 4 measurements corresponding to the unknown concentration mu. So the absorption measurement AAS data, we are going to fit a model that will relate the AAS data, we call that Y, to the cadmium concentration X. Think of like a linear regression model. Now, an important feature you can notice is the following. As the cadmium concentration goes up, the standard deviation in the data also increases. So you can see that here. And this is an important feature in many chemical measurements. When the concentration of a chemical goes up in a sample, the standard deviation or the variance will also go up. It is not a constant variance sigma square. So you want a model that will capture this feature. So we need to capture increasing variability with increasing concentration. And remember that the problem of interest is the statistical inference concerning this unknown concentration mu. So this is the problem of interest, inference concerning the unknown concentration mu. So as I just said, one feature of many chemical data analytic measurements is that when you increase the concentration of the chemical, the standard deviation will go up. But when the chemical concentration is at a very low level, the standard deviation is nearly a constant. So you have near constant variability when the chemical level is low, but increasing variability when the chemical concentration increases. So this well-known and well-cited paper in Technometrics 1995, this is the model I'm going to introduce is referred to as the Rock-Lorenzato model. It is known after them. They introduced this model in 1995, and I'm going to show you the model. And the model is known to give excellent fit to many chemical data sets. So that has been noted over the years. So notation, so let us write as YJK. This is the kth measurement at the jth concentration level xj. Okay, go back. So x1 is 0, then y11 is 0, y12 is minus 0.7, y13 is minus 0.1, and so on. So this is the notation. So xj, x1, x2, x3 represents the concentration, and the y represents the AAS data. So you have yjk corresponding to the known concentration level xj, and then you have the data yk corresponding to the unknown concentration level mu. So the number of measurements at each concentration, they need not be the same. In our application, we have all the nj equal to 4. They could be unequal. Here is the model. So first, you look at the non-concentration xj. It's almost like a linear regression model, except there is this exponential term here, e to the power eta jk. So you have a intercept beta 0, slope beta 1 times the concentration times e to the power eta jk, where eta jk and correspondingly the eta k when the concentration is unknown. So they are assumed to be normally distributed. And then you have an error term, ejk and ek. So the first model here corresponds to the non-concentration, and the second model here corresponds to the unknown concentration mu. So since eta jk and eta k are normally distributed, so the exponential will be a log normal random variable. So this is the model that Rock and Lorenzato introduced. Now notice what happens to the variance of yjk or the variance of yk. So the variance of yjk will be beta 1 square xj square times the variance of e to the power eta jk plus the variance of ejk. These random variables are assumed to be independent. So since one component of the variance is beta 1 square xj square times e to the eta jk, you can see that when the concentration xj increases, the variance will increase. So the variance of e to the power eta jk is the variance of a log normal random variable, which is already known, which is a known quantity. So this is the model that Rock and Lorenzato introduced, and it gives excellent fit to many chemical data sets. And that is why this model became very popular. And it continues to be used. Now, right now we have data collected at one laboratory. You can also have data obtained from several laboratories, which I will not get into today. So you have data from a single source, single laboratory or single measurement method, etc. And later on, people have generalized this to multi-laboratory scenarios. So here is a multi-lab generalization, even though I will not look at it today. Basically, what this now means is the concentration used is specific to the laboratory. So my laboratory will use one set of concentrations. Your laboratory could use a different set of concentrations. But we all want to determine the unknown concentration in one sample. So basically, we are just to see if there is variability from one lab to the next. So you have multi-lab generalizations. So this was written by, again, a couple of papers in technometrics. There are other articles as well by Gibbons and Paumick. These are two articles that appeared in technometrics dealing with multi-lab generalizations. Okay. So today we are going to focus only on the single lab model, the model I just showed you. So here is the likelihood function. So the likelihood function, because of this random quantity here, random effect, you can say e to the power eta jk and e to the power eta k. The likelihood does not have an analytic closed form expression. It will stay as an integral integrated over the normal distribution of eta jk and eta k. So obviously, if you want to maximize the likelihood, you have to do that numerically, which is no big deal. All right. Now, one of the things that is, notice that in our data, the sample size is not big. We have just 4 replicate measurements at each concentration, and the number of concentrations also not too many. So we are in a small sample scenario. So if you do the usual likelihood-based asymptotics, the result will not be good in terms of, for example, coverage probability of the confidence interval. We will come to that. So we are going to do a modification of the likelihood methodology. So here is one such modification. I'm going to present that in general. You look at the log likelihood function as a function of the vector parameter theta. You partition theta as a scalar parameter of interest mu and a vector of nuisance parameters lambda. Denote by theta hat the MLE of theta. And right here as theta tilde, this is the constrained MLE of theta. That means you compute the MLE of lambda for a fixed value of mu. So we call that theta tilde. And then we have what is called the signed root of the log likelihood ratio test statistic that is given by the following. Basically, this quantity R mu, if you square it, you get the usual LRT statistic, right? Minus twice log likelihood ratio test statistic. That is the square of R mu. So you can think of this as a square root of the usual statistic, except that you attach the sign of the MLE of mu minus mu. Remember, mu is unknown to us. So the sign means it is +1 or -1, depending on whether that argument is positive or negative. So the usual asymptotics will apply to R mu. And you can show that if you compute a tail area based on R mu, and if you use a normal approximation, then the error is of order n to the -12. This is what we call the first order asymptotic accuracy. So the phi of t is the standard normal quantity. Okay, now we are going to modify this so that the accuracy becomes order 3. So the modification appeared in this article in the Scandinavian Journal of Statistics, 1994, and then further explored in this Canadian Journal of Statistics article. You do something very simple. remember, we expect R mu to be standard normal. When you square it, you get a chi-square. Remember, the mu is a scalar parameter, so the chi-square will have degrees of freedom 1. So I expect R mu to be standard normal for larger samples. Okay, before that, I want to point out one thing. So I'm talking about a sample size n. We are assuming that we have IID data here. But remember, in the application I showed you about measuring cadmium concentration, that is not IID data. But this methodology I am presenting in an IID scenario. All right. I expect R mu to be a standard normal, but in small samples that may not hold, the mean of R mu should be 0 in large samples, but in small samples, the mean could be non-zero. I denote the mean by m. And that will be a function of the parameter mu and the nuisance parameter vector lambda. Same with the variance. I write the variance. I expect the variance to be 1 asymptotically. Otherwise, it is going to be 1 plus some factor v. What you do is you standardize R mu once again using its mean and standard deviation, but you evaluate it at the constraint MLE lambda. Then these people, Decisio, Martin, and Sten, showed that if you do this modification, call the modified quantity R1 mu, you get third order accuracy. Significantly more accurate, even for small samples. We will see that shortly. So this is the modified quantity we are going to use. Now the question comes up. How do you compute the quantity, the mean m, and this factor v? So it is not possible to compute them analytically, but you can compute them numerically. Remember, we are evaluating it at the constraint MLE lambda. So a major problem is the computation of these quantities, and you can do that using a parametric bootstrap approach. So quickly, here is what you do. You specify a value of mu, any value. For example, you can specify a value of mu close to the MLE. And once you fix mu, then you compute the MLE of lambda. That is what we call a constraint MLE. So at the fixed value of mu and at the constraint MLE, now I know the parameters. Mu I am fixing, then lambda I am replacing by its constraint MLE. I generate a sample from my model corresponding to these parameter values. Then evaluate the quantity R mu, the signed log likelihood ratio test statistic, call that R tilde mu. You repeat it as many times as you want, let's say 500 times. That will give you 500 values of the signed log likelihood ratio test statistic. You simply compute the mean and variance of those quantities. That will give you m and the variance 1 plus v. Now we standardize. Of course, so the whole thing is numerical, but it can be implemented, right? So now all you have to do is equate R1 mu to the standard normal percentiles and solve for mu. That will give you confidence limits for mu. Now remember, the whole methodology has been rigorously developed in the case of IID situations, but people apply it to non-IID situations as well. So there is this comment by Skovgaard, who talks about such higher order modifications, mentioning that you simply apply to other scenarios, believing that the procedure will work well. Obviously, you have to verify it numerically. And it has been numerically verified in a lot of applications and found to be quite accurate in numerous applications where you don't have an IID situations. Anybody interested? Here is a book dealing with what is called small sample asymptotics or small sample statistics that talks about modifying the usual likelihood ratio procedure so that you get accurate performance in small samples. Back to your data. Here is the data once again. Remember, the focus is the parameter mu, but we will look at the other parameters in the model as well. So I showed you this likelihood ratio, likelihood function earlier, and the parameter of interest is mu. So the remaining parameters, beta 0, beta 1, and sigma eta square, sigma e square, those are the nuisance parameters lambda. I wrote an algorithm to implement the calculation of R1 mu. In the interest of time, let me not go through the steps. I told you how to implement it, but having it written as a step probably will be helpful. If you want to write a code, for example, You compute R1 mu after specifying a value of mu equal to mu 0. Then check if the value specified is equal to the standard normal percentile. If not, you change the value of mu. So you have to iterate it a few times until you get the value of mu for which R1 mu becomes equal to the standard normal percentile. And that value of mu will be a confidence limit, lower, upper, or two-sided, depending on what you want. So based on the data, here are the MLEs of the slope beta 0, intercept beta 0, slope beta 1, then that variance associated with that random effect, sigma eta square, error variance, and this is the MLE of mu. When I don't know mu, the cadmium concentration in a sample. Here are the coverage probabilities. If you use the original likelihood ratio test statistic, the coverage falls short of 0.95, as you can see. However, look at the modified quantity R1. All the coverage probabilities are pretty much equal to 0.95. Just goes on to show you that if you apply that modification, you can indeed get a very accurate result. I also computed the confidence interval for the variance parameters, and you can see some differences among the interval corresponding to R and R1. Notice that the interval corresponding to R and the modified quantity R1, they are mostly quite different, and that is especially the case for the quantity sigma eta square. The confidence intervals can be quite different, and typically the interval based on R1 will be slightly wider because the coverage is better. I'm almost done. So the overall conclusion is, if you use the usual likelihood ratio procedure, you may end up with significant under coverage. And I did not show you a multi-lab scenario.
Professor, very interesting. Please mute your mic, sir.
Dr. Sebastian, please mute your mic.
Yeah.
Okay. The modified quantity provides accurate coverage, and we looked at various multi-lab scenarios when the lab-to-lab variability is common, or that means homoscedastic or heteroscedastic, and R1 gives excellent coverage. And we do have R codes available for implementing the methodology. So this talk is based on a work jointly with a doctoral student, Zhao, and another colleague, Bebu. Bebu has visited St. Thomas College, Pala. Some of you may know him. Actually, Sebastian mentioned about my Uden Award. This work again got the Uden Award this year. So I'm pleased to mention that. So in 2021, at the joint statistical meetings, this work was selected as the recipient of the Uden Award from the American Statistical Association. So these are some of the references. This is that article by Rock and Lorenzato that I mentioned in the beginning. And this work is also part of the doctoral thesis of that student, Zhao. This concludes my talk.
Thank you, Professor Matthew, for finishing the talk in time. Now we have time for asking one or two questions.
Dr. Sebastian, I have a question.
I also have. Okay, Ramathan, please go ahead.
Yeah, Professor Thomas Matthew, I just wanted to know, is there any goodness of it things done on this? Because how you make sure that the model actually fits the data?
Right, yeah. We did not do it because the data was taken from that Rock Lorenzato paper. They did do the model fitting.
Okay.
Yeah. If you look at that paper, you can see the model fit. I think people who have applied this, people have noted that the model gives excellent fit to many chemical data sets due to some reason. That is why the model became popular. Yeah. Obviously, it is important to know if the model gives a good fit or not. It does.
Thank you.
Professor Srivastava, please.
Yes, sir. Very nice presentation, sir. And if the number of replications increase, sir, and hello, am I audible, sir?
Yes, I can hear you.
Yes. Yeah. And the second thing is that in most of the outputs which you have seen, and sir, if possible, if it is a published work, I would like to see the R codes of the program which you have mentioned in the last slide. We are also doing some calculations over here. I am from Baroda, MS University. And sir, the second thing which I wanted to know is that all the intercepts are coming negative. Any reason for that?
Now, let me answer the first question. Thank you for your questions. Now, the R code I can definitely send you.
Thank you very much.
But remember, the R code is specific to this application.
Yes, sir.
Do you mind sending me an email?
Oh, sure, sir. Sure, sir. I'll be
Please
more
send me
than
an
happy.
email so that I will remember to do it. Anybody who wants this article of ours or my slides or the R code, just send me an email. In fact, I can send you the whole thesis if you want. I'll be happy to do that.
I'll put a mail to you, sir.
Why the intercept comes out negative, that I am not sure. My feeling is that okay, let me show you that. You see, when the concentration is 0, some measurements are coming out as negative. These are coded measurements, by the way. This is not the actual concentration. I think they did some coding to it.
Yes, sir.
Because of this, probably the intercept is coming out negative. Because of this.
Because of
but I'm not
coding,
sure about it.
Because of the
I'm not
coding,
sure
sir. So my concern was if you are using a particular type of coding of the concentration level, which might have resulted into the negative slope, negative intercept, I'm sorry.
Right.
Might be if you change, is it robust to the coding procedure? That's the next question.
Yes. The if you code the data, that will change the I think that probably
the output, yeah,
will be equal to some type of a reparameterization.
Yes, sir. Yes, sir.
Yeah.
Thank you.
See, what happens is, many of these data sets, at least in the US, there is a lot of confidentiality.
Yeah, I can understand.
So people don't want to reveal the actual data, even though this data on some soil sample. What is confidential about it? But still people are concerned about it. I don't know. That is why very often the data, published data, will not be the actual data. It will be coded data.
No problem, sir. We can understand. That is very well taken care of. Thank you very much. Thank you, sir.
Yeah, Professor Matthew, I think your likelihood function is actually that n-fold integral, right?
Yes.
Yeah, because we have similar problem while model is stochastic volatility. So there, I think we introduced this MCMC method to come out of this problem.
Right.
But I think you don't know that problem
Mr.
because
Sebastian, you can mute so that will not be going. Sebastian, sir. Sebastian, sir, you can mute.
Yeah, sure.
So that there not be a lot of echoing. Yeah.
Yeah, I hope my comments are clear.
Yes, I got your question. Let's see. What my student, what he told me is that he did some type of a quasi-Newton procedure. The dimension of the integral he had to deal with was 4.
Oh, that is very small.
That is very small, correct. Yeah. Now, if it is too big, you're right. You may have to think of something else. I agree.
There is one more reason. Actually, in financial data, you don't have the scarcity of the data. So here you have only 5 points, whereas so in finance you have plenty of data. So
right.
Yeah.
Just
a comment. That's all.
Yeah. So the whole logic behind the procedure is: can we do something accurate when you have a small sample?
Right.
When you have a small sample.
That's very interesting. Actually, that is what in biostatistics.
Right. So if you encounter applications where continuous data, by the way, not for discrete, if you encounter applications where the sample size is not big,
yes,
and you don't trust your likelihood-based asymptotics, here is a method you can think about.
Absolutely right.
Good. Yeah. Thank you.
Yes, sir.
Okay.
Okay, sir. Okay, thanks a lot. So we will give an online clap to you, sir.
Well, thank you.
For your kind presentation. Yeah. Thank you very much for the nice presentation. Okay, our next speaker is Professor Kanjan Jain. Yeah, she is here.
Yes, sir.
Yeah, Professor Jain is from Punjab University. She is a member of ISPS, and he is a member of IAI, the Institute of Actuaries of India. He has published many important articles and a fellow of Royal Statistical Society, elected member of National Academy of Sciences, and visiting scientist in a number of universities, for example, University of Calcutta and Research. I invite Professor Jain to present their work. Please.
Thank you, President. Oh, sorry. Just
Yeah, I will mute.
are my slides visible, sir?
Yes, yes.
Yes.
Visible.
Yeah, yes.
So, good evening, all. You see, at the outset, I like to mention that I am not a very expert biostatistician. I've just tried to venture into this area and done some work. Basically, I'm a reliability or person or a probabilistic person. So, I think my work, whatever I have done, will be okay with everybody. And if there are any questions at the end, naturally I'll be answering them whatever I can. So I think I'm getting this. Is it okay now?
I think it's okay.
Okay. So you see, specific bivariate classes of distributions with given marginals can be used for contribution of the linking distribution between conditional and unconditional effectiveness using copulas. Here, we propose a Bayesian model for meta-analysis of treatment effectiveness data, which are discrete, binomial, and sparse. Then a bivariate class of priors has been imposed to accommodate a wide range of heterogeneity between multi-center clinical trials and applications to real data are provided. Now, what is meta-analysis actually? Meta-analysis provides the statistical analysis of a large collection of analysis results using individual studies, and this is done for the purpose of integration of the findings. And it is a scientific method for accomplishing this goal, which uses some statistical procedures, and meta-analysis gives us a stronger conclusion than the one provided by an individual study. Now, objectives of meta-analysis, they are for testing the homogeneity of the existing findings, for drawing general conclusions on a particular topic, estimating an average effect size, testing potential moderates if the studies are homogeneous, and to provide methods for meaningfully combining the results from component studies. Now, why do we need meta-analysis? Because sometimes there is a lot of information from various studies, which is sometimes contradictory also, and meta-analysis gives us a way to investigate this. It may increase the statistical power, resolve uncertainty, and improve the estimate of the effect size. It may answer some questions which are not posed by individual studies, and many studies on a research topic are carried out rather than a single study to strengthen the overall conclusion. There are few references for meta-analysis by Hedges and Alkan, Cooper and Hedges, Hasselblad and Hedges, Irving and al., Sutton and al., Egger and al., Schulz and al., and Krasonsky and Hand. Now, by a copula, we mean a function which completely describes the dependent structure. It contains the information for linking the marginal to the joint. And to get a valid multivariate distribution function, it's sufficient to combine several marginal distribution functions with an underlying copula function. And there are many copula families available, which have parameters controlling the strength of dependence. And this book by Nelson, An Introduction to Copulas, gives very detailed description of copulas. Now, copulas have many applications in the area of biostatistics. They are used in MRIs for segmentation of images. This was illustrated by these authors. Then for providing graphical models in imaging genetics in schizophrenia, for differentiating between normal and Alzheimer patients, for studying neuronal dependencies and spike counts in neuroscience, and in oncology for jointly modeling the genotypes and phenotypes, for diagnosis of colorectal lesions using colonoscopy images, for classification of cancer subtypes, and in meta-analysis of diagnostic studies in biometrical research. So copulas have lot of applications in biosciences, and some of the papers are quite recent, like this 2019 paper. Then Moreno and all, they studied a Bayesian model for meta-analysis of sparse discrete binomial data. They use the treatment effectiveness data of n centers, because we are considering multi-centers, by denoting this MI is the Bayesian model for the observational study in the ith center. M0 is the Bayesian model for the unobservable meta-treatment effectiveness, which is denoted by X, where this MI actually is now a model, Bayesian model, where we have Bernoulli setup, and pi theta is the prior distribution. Theta I here is the probability of success of the treatment, conditional on the ith center. M0 again, sorry, there should be a bracket, Bernoulli with x theta. Pi theta is the prior, and theta is the unconditional probability of success of the treatment. And priors that have been used are uniform and Jeffrey. Then this crucial linking distribution between the effectiveness conditional on the healthcare center and the unconditional effectiveness is constructed from some specific bivariate classes of distributions with the given marginals. Now, for formulation of the Bayesian model for meta-analysis, a linking distribution is required, and this conditional distribution, the linking one, has to be compatible with the marginals. This means if we have this bivariate distribution, pi of theta I theta, then these equations, integral equations, should be satisfied. So they are giving us the marginals. Now, a class of bivariate distributions that satisfy this integral equation is the FGM copula. This is that Farley-Gumbel copula, whose equation is given by this, and parametric class of probability distribution which satisfies 1. This is written like this, and Moreno and all used this linked distribution for linking the experimental parameter, which is theta I, and the meta parameter theta. Now, limitations of this family are that between center heterogeneity captured is not sufficiently wide. Actually, this heterogeneity is measured by the conditional variance, which is given by theta I. This is the conditional variance of theta I on theta and k, and this is the expression for this conditional variance, and this comes out to be a decreasing function of k for any theta. Now this rho comes out to be k by 3, and it follows that this conditional variance is a decreasing function of the correlation coefficient rho. Again, this k varies in 0 to 1, so rho lies between 0 and 1 by 3. So FGM class will not be able to model a class whose correlation coefficient between theta I and theta is more than 1 by 3, because we are putting this restriction on rho that it has to be less than or equal to 1 by 3. So although this is an interesting family, but it cannot be used for representing a joint distribution of two highly correlated variables. Then, assuming a uniform prior for rho in this interval 0 to 1 by 3, the induced distribution on k is uniform on 0, 1, and the linking distribution we write like this. And to increase dependence between the variables, in 2002, by Ramov and Coates, they extended this distribution to generalized FGM distribution or family. And the main features of this generalized family are that it increases the dependence between the underlying variables, as there will be additional parameters, and it also allows us to achieve correlation which will be more than half. The equation for this generalized FGM copula is given by this 5, and corresponding parametric class of distribution, which is pi now, it's given by this, and range of k here is between these two limits. So lower limit is minus minimum of these two, and upper limit is given by this. And range of rho for a specific value of p is again given by this. Now it is observed from this range that as p will go to infinity, rho will go to 0. So for large p, rho will be very small. So this means there will be weak dependence between the components theta I and theta. And these two authors, they showed that rho maximum is 0.5 when q is taken to be 2.89 and p is 1.5, and rho minimum is minus 0.48 when q is 2 and p is 1.5. So the fact that this rho maximum exceeds half, slightly exceeds half, is advantageous for practical purpose. So what is done is q is taken to be 3 now. So we put q to be 3, and then conditional variance for GFGM generalized model comes out to be this. Again, this conditional variance is a decreasing function of rho. Now, if we have Jeffrey marginals, then we use Sarmanov-Jeffries family instead of FGM or GFGM. And the corresponding probability distribution of this family is pi Sj, and k here is between 0 and 4. Conditional variance has this expression, and which is a decreasing function of correlation coefficient, which comes out to be k by 8. So when k ranges over 0 to 4, we have rho lying between 0 and half. So this class needs to be enlarged so that we can get a correlation coefficient which is more than half. Then, assuming a uniform prior for rho in this interval, then k induced distribution on K is uniform, and this is the linking distribution. And these persons, Lin and Huang, they considered a generalized version of Saramanov family. And they showed that this family has a correlation which approaches 1 regardless of the marginals, as long as the marginals are of the similar type. So we consider these generalizations which were constructed by these people, and they have a simple analytical form like the FGM, and as in the normal case, this correlation coefficient will govern the dependence. So this is the equation for generalized Sarmanov copula or family, and with the corresponding parametric class of probability distribution. Again, these two equations, this gives the range for K when P is greater than or equal to 1, and when P is less than 1, this is the range for K. And rho is obtained to be equal to this. So it is observed that the range for rho is given by these two limits for 0 less than P less than 1, and by these two limits when P is bigger than or equal to 1. This shows the expression again for the conditional variance, and it is seen that conditional variance again is a decreasing function. So in all the situations, conditional variance is coming out to be a decreasing function. Now for the meta parameter theta, the likelihood has to be derived now. So this is the probability. Xi's were corresponding to ith center, Ni is the size, and this is the equation. And when we replace this distribution, conditional distribution, by the linking distributions, so if we have FGM family, this is the conditional likelihood. For GFGM, we have this expression, and these two are the generalized hypergeometric functions where we define A, B, A1 and B1 in this manner. And for the Sarmanov and generalized Sarmanov class, this probability is given by this expression, and for generalized Sarmanov, this is the expression for the conditional likelihood, we can say. So actually, those are conditional probabilities. Now, conditional likelihood is given by, for the whole data set, will be the product I from 1 to capital N. This X vector includes all Xi's, N is including all small n's, and W here means we are considering either FGM or generalized or Sarmanov or generalized Sarmanov. Now, when we assume that the links under the uniform marginals are a priori equally likely, we assume these two probabilities to be half, and the conditional likelihood then is written in this manner. Similarly, assuming these two to be half, these two probabilities, we can write the conditional probability of this as, we can say, a combination, a weighted combination, or even it's a convex combination also. So from the conditional likelihood and the prior, the posterior can be written in this manner now. And this is under the uniform marginals. So here, this is a mixture of the posterior probability of theta under these two models, and weights will be the posterior probabilities of these two models. And Bayesian models for FGM, I just write FGM here, we are taking this to be uniform, and similarly for this we are taking it to be uniform. So corresponding posterior probabilities, they are given by this ratio, and these similarly, if I have to write now for generalized, it will be 1 minus this, and mx given n like this, these are given by these integrals. For the Jeffrey marginals, the posterior will be written in this manner, because now we have beta, theta, half. So again, my Bayesian models are, this is actually, okay. This is for Jeffrey marginal. So these are two Bayesian models for Sarmanov and generalized Sarmanov. So again, we write down this probability as the ratio, where for generalized it will be 1 minus this, and mx given nw, w we can replace by sj or gsj. Then testing for equality of treatment effectiveness. This is of great importance, and suppose we have two alternative treatments which are applied to patients in N1 and N2 healthcare centers, and let these be the center effectiveness samples of the treatments. These two, they denote the conditional likelihoods. These are the conditional likelihoods. This is the prior for alpha, and meta effectiveness, they are denoted by alpha and beta for the two treatments. So we wish to test this H0, that alpha is same as beta and they are same as theta, and versus that alpha beta belongs to this. Now this is equivalent to model selection problem between the two Bayesian models. This into this, because this is my, I have two, I'm considering two treatments, and here it's assumed that x1 and x2 are independent, conditional on the meta parameters. The optimal solution to this decision problem under 0-1 loss function is to reject the H0 if posterior probability is smaller than half. So this is the posterior probability, and we just write, we leave N1 and yes?
Professor Jay, your time is more or less over. Please wind up.
Over? Okay.
Okay.
So I think I'll just show the examples we have taken up. So these are two real data sets. And in the first data set, we are considering 15 independent clinical trials of Progavit, an anti-epileptic drug. And these are two, N1 and 2, X1 and X2 are given. We have found the posterior model probabilities under different marginals and considering FGM, GFGM and all that, and then found posterior probabilities. And these values, they indicate a strong empirical evidence to accept the equality of efficacy of this drug for open and closed studies for uniform marginals. But when we are using Jeffrey, then null hypothesis is rejected. Then second data is from this 16 control trials of intravenous magnesium in prevention of death following myocardial infarction. And these are the observations. These are the posterior probabilities. And again, these are the under H0, under null hypothesis. So we, again, actually, this is the decision that there is moderate empirical evidence to accept that both the groups are same under both marginals. So these are the references.
Thank you. Thank you, Professor.
Thank you.
The time is running out. We have time for one question. Yeah, no problem, no problem. We have time for one question.
Just one question.
Yeah.
Yes, sir.
I just wonder that when we talk about Bayesian, of course, apart from the testing part when we talk about the 0-1 loss function, but when we talk about the meta parameter or the Bayes estimator of any parameter, are we considering any different type of loss function, or is it under the squared error loss function?
Actually, we did not consider
Okay,
any
ma'am.
other loss function, but it can be thought of.
Yeah, because when we talk about the Bayesian paradigm, I mean, of course, prior and the current sample information and the loss function plays a very important role.
Yes.
And in such kind of studies, particularly related to this kind of data, I think maybe the asymmetric loss functions. I am not very, as I can also confess, like you, as you confessed in the beginning, I am not that much into this, but I'm a hardcore inference person. But loss functions could play a very important role in this kind of studies.
I understand, and we can explore that.
Yes, ma'am. Thank you.
Thank you.
Thank you, Professor Jain, for the very nice presentation.
Thank you.
Yeah.
Thank you, Professor, for inviting me.
Yeah. Good evening, Madam Kanchan Jain.
Thank you, Professor.
Good evening, Madam Kanchan Jain. Very nicely
Thank
presented.
you, all the organizers.
Yeah, how are you?
Okay, sir.
Yeah. Now it's the time for contributory presentation. The first speaker is Dr. Lalita Deni. Dr. Lalita.
I think Sebastian, you can call everybody.
Yeah. I think the other one is Dr. Magina Venkatalavanya.
Yes, sir.
Yeah, she's here. Yeah, so shall we? Can she present now?
Yeah.
Okay.
Yeah, I think the first person is not there.
Yeah, in between you can check if somebody is coming. Otherwise, you can go into the schedule.
So Ms. Lavanya, you can start now.
Yes, sir. Yes, sir.
Yeah.
Okay, sir. Now let's share my. Sir, is my screen is sharing, sir?
Yeah, it's fine.
Sir, am I audible, sir?
Yes, you are audible and you are visible. I mean, slides are visible also.
Okay, sir. Okay. Good evening, one and all. I am M.V. Lavanya, a research scholar under the guidance of B. Muniswamy, Professor and Honorary Director, Population Research Center, Department of Statistics, Andhra University, Visakhapatnam. My title is Data Reporting and Quality of Health Management Information System, trends in Andhra Pradesh and Telangana during 2017 to 2020. So, coming to introduction, the Health Management Information System web portal was launched by the Ministry of Health and Family Welfare on 21st October 2008 to enable capturing of public health data from both public and private institutions in rural and urban areas across the country. This portal is envisaged as a single window for all public health data for the Ministry of Health and Family Welfare. The Ministry of Health and Family Welfare initially rolled out the Health Management Information System up to the district level and now being expanded to the sub-district or block level facility-wise data entry. The information available on this website is being compiled from varied information sources such as National Family Health Survey, district level household survey, census, simple random sampling, and performance statistics. For continuous monitoring of the process and outcome indicators of the National Rural Health Mission interventions, there is need for good quality data on the regular basis. As such, the ministry has launched a web portal known as National Rural Health Mission Health Statistic Information Portal, where all the districts in the country are expected to upload the data on a monthly, quarterly, and yearly basis as per the different formats designed by the ministry for this purpose. So one of the major contributions of National Rural Health Mission has been put to in place of nationwide health management information system. Currently, on a monthly basis, we are gathering reports from over 653 districts. So here, HMIS enables monitoring with predefined health indicators, which facilitates decision making at sub-district, district, and state level without much paper-based report processing. So Health Management Information System under National Rural Health Mission has its significance in terms of assessing the progress, quantifying output, as well as outcome of interventions and decision making as well. So it is generated, compiled, and collected data at various levels across variety of programs under National Rural Health Mission provides the base for corrective actions, decision making for the health functionaries and program managers. So here the data is analyzed and presented so as to help districts and to find data errors and correct them. This data is analyzed primarily for 3 years. So here we consider 3 years data, 2017 to 18, 2018 to 19, and 2019 to 20. So coming to the context, the continuous demand for good superior quality of information on inputs, outputs, and outcome indicators mentioned in the plan of action for the involvement of data and micro-level planning and program, the Ministry of Health and Family Welfare has devoted a specially designed web portal named NRHM Health Statistic Information Portal. So, since 2008, HMIS shows the regular data uploading has improved to a large extent, and more than 640 districts all over the country are now regularly uploading monthly reports. Not only the timely uploading of reports has improved, but if we analyze data contained in this report, the quality of data being uploaded on this website seems to be improved. Ensuring this data quality is a key concern in building an effective HMIS. So here the data quality has different dimensions, including first dimension is correctness. So every time data should be within the normal range of data collected at that facility. There should be no gross discrepancies when compared with data from related data elements. And next dimension is completeness. So data for all data elements for all health facilities or blocks or talika or districts should have been submitted. And coming to the consistency, data should be consistent with data entered during earlier months and years while allowing for changes with reorganization, increased workload, etc., and consistent with other similar facilities. And last dimension is timeliness. All data from all health facilities or blocks. So if we have a poor quality data, we will have garbage in, garbage out situations. So use of pure quality data leads to all informed decisions. Hence, the health management information system software should be. So coming to the scope of the study, the main object of the study to make a trend analysis of HMIS key indicators, such as so many key indicators are there in Andhra Pradesh and Telangana states during the period 2017 to 18 to 2019 to 20, with a view to find out whether there is an improvement in the upload as well as quality of data year after year. So here our objectives is to find out the status of health facilities, whereas functional and non-functional, or to observe the status of facility-wise data coverage or upload, to examine the quality of data pertaining to some selected indicators, to observe trends about institutional deliveries to total antenatal care registrations. Coming to the review of literature, a health management information system is a critical tool for effective and efficient healthcare delivery. According to World Health Organization, the HMIS is responsible for generating, compiling, analyzing, and synthesizing, and communicating and using data for decision making and ensuring their overall quality. Among other functions, the information system provides information that supports patent and health facility management. During 2008, district health management information systems provide inputs for the formulation of national and regional policies. Here, the author Lepwell, Sorbonne, and Borat studied quality assurance with respect to the study referred to the plan and systematic components performed satisfactorily in health service. So our methodology is, first we have to find out the data reporting. So here the data uploads from the web portal from facilities that are functional in Andhra Pradesh and Telangana, which is shown in the above table, during the years 2017 to 18, 2018 to 19, and 2019 to 20. So here we consider 3 years of data. So during the year 2017 to 18, the percentage of facilities that uploaded data is better in Andhra Pradesh than in Telangana. So here the Andhra Pradesh is better. So the percentage has shown improvement from April 2017 to March 2018. During the year 2018 to 19, the upload is almost complete for all months in Andhra Pradesh, while it is more than 2019 to 20 in Telangana. So in coming to Andhra Pradesh, the upload of data from SCs and CHCs is recorded as more than 100%. So these are the facilities. There are 5 facilities: SC, CHCs, and CDH coming. So in that, SCs and CHCs are recorded more than 100% during 2018 to 19, and this continued same as in during 2019 to 20 up to June 2020. This data needs to be rectified. So the details is here, the details of monthly wise from 2017 to 18. Here the 5 facilities. Every month data for 5 facilities and for 3 years. So after that, here in SC at the year of 2018 to 19, from April to March, we have obtained as a percentage of more than 100 as 100.9 like this. And coming to the 2019 to 20 also, here in this SC facility only, we have obtained April, May, June as more than 100%. And coming data more than 100%. So which is a error. So in Telangana, it is okay. Its maximum is 95%. So after data quality, so here information on the percentage of institutional deliveries to total ANC registration. The proportions of deliveries reported at institutions during 2017 to 18 to 2019 to 20 in Andhra Pradesh and Telangana is presented. It shows that the institutional deliveries to total ANC registrations in both Andhra Pradesh and Telangana during the 3-year period 2017 to 18 to 2019 to 20. So the total ANC registrations are more than 100% in Khammam district and Warangal district of Telangana during 2017 to 18. And coming to the year 2018 to 19, the same situation was observed in the Khammam district and Warangal district from Telangana, and Hyderabad and Karimnagar and Warangal districts are from Telangana during coverage, especially in 118.9, 131.9, 125.7, 163.1, and so on like this. 151.3% recorded for Warangal district, Khammam district, Adilabad, Hyderabad, and Karimnagar districts of Telangana during this 3 years period. So it needs to be examined for duplication of data. While we are entering the data, something error we are entering. So this is the table for 3 years institutional deliveries to total ANC registration. Here in Andhra Pradesh, 2019 to 20, we have obtained in 2017 to 18 as Warangal district as 118.9, and coming to the 2018 to 19 in Warangal district only 131.1, and coming to the 2019 to 20 year, Adilabad has occurred 103%, Hyderabad occurred 116.1, and Karimnagar occurred as 116.2, and coming to the Warangal list. So these are the graphs for 2017 to 18 to 20. So coming to the conclusion, the percentage upload of Telangana. So the percentage has shown improvement from April 2017 to March 2017. During the year 2018 to 19 and 2019 to 20 are almost completed uploaded data. Interestingly, in Andhra Pradesh, the upload of data from SCs and CHCs is recorded more than 100% during 2018 to 19, and this is same continued for this SC during 2019 to 20 also. So here we need to rectify considering the duplication of data entry, as a percentage upload of any type of facility cannot be more than 100. So coming to the antenatal care, the institutional deliveries to total antenatal care registration are more than 100% in both Andhra Pradesh and Telangana during this 3-year period. This situation is occurred in the districts of Anantapur of Andhra Pradesh, Warangal, Khammam, Adilabad, and Hyderabad, Karimnagar of Telangana during the 3 years. So here also we have to need for duplication of data.
More or less over.
Okay, sir. Okay. And these are the references. We have collected this data from all this. And thank you.
Thank you, Lavanya.
Okay, thank you.
Now there is time for one question.
Okay, sir.
If no question, then I will call the next speaker, Abhinav and Madhavan.
Hearing Professor Mia.
Okay.
So shall I share my screen?
Dr. Sebastian, Lalita Devi will not join because she has already completed her presentation yesterday. Because she had another meeting today, that is why.
Okay.
Is everyone able to see my screen?
Yes, it is visible. But you could make full screen.
I am making it full screen.
Yeah.
Now it is okay.
Okay. So good evening, one and all. So let me give a quick introduction about myself. I'm Abhinav N. Madhavan. I'm a research scholar from the Department of Statistics, my name is Tanna University, Tamil Nadu, and I will be presenting my research paper on the impact analysis of security breaches in the American health sector. This research project is specifically for the American health industry, and what are the types of security breaches and cybercrime. Hello?
Can you talk a little bit loud? It's not audible. Also.
Oh, how about now?
Yeah, now it's fine. Okay.
Okay, so shall I repeat? Okay, so I'm Abhinav, and I'm studying as a research scholar in the Department of Statistics, my name is Tanna University, Tamil Nadu, and I will be presenting on the impact of security breaches in the American health sector. All right. So let me give you a quick introduction about the cybercrime in the United States. So cybercrime in the United States is in an increasing trend right now, and based on the Federal Bureau of Investigation, we have more than for the year 2019 we have more than 467,000 cybercrime cases, and they amount to at least a loss of $3.5 billion, and this is with regard to the FBI's yearly report, the Internet Crime Report, IC3. And similarly, for the year of 2015, we can see that it is around $1.1 billion. So we can see that the loss which is caused due to cybercrimes is in an increasing trend right now. And business email compromise frauds, which is basically cybercrime that is caused due to cost via the email, whether they use it as a Trojan or whether it's a clickbait. So we can assume that business email compromise fraud is the costliest kind of fraud, because it is most probably followed by extortion, and we can see that it is costing organizations nearly $1.8 billion. Apart from the business email, though business email compromise is the most common type of fraud and common type of cybercrime, we can also see that there is an increasing trend in elder fraud. Usually citizens who are above the age of 60-65, they are targeted, and they are specifically targeted, and they are extorted out of their money in one form or another. The modus operandi, the way in which the crime occurs may be different, but the target audience are elders, and we can see that almost 68,013 people are the casualties for this kind of crime. And if we compare it with if we take age as a bar, and if we see what is the if we can see that under the 20s, the people who fall under the under 20s age group, they are just 10,724 casualties. So we can see that the senior citizens are targeted more. And let me give you a quick update on the types of cybercrimes and cyber threats that is caused. So first is the malicious software, that is the malware attack. It is one of the most common types of cyber threats, and it is usually used by the hacker to deliberately damage the user system. More or less, most common way malware is spread is through the email, usually via hyperlinks. If a particular user clicks on that particular hyperlink, it is the malware software is automatically downloaded into the system, and then the system is compromised. And then there are, so this is the other types of cyber threats are viruses. Everybody knows the virus is actually a self-replicating program that usually is sent via emails and other forms of communication. But once it gets into the system, it usually replicates quickly and usually destroying the files and data within the system. The Trojans are software, are actually malicious software, but they are designed to look like legitimate software, and it usually Trojans is used to create a backdoor so that a particular hacker can gain access to the particular system. So usually the modus operandi will be like this. First, the Trojan is introduced, and using the Trojan, the hacker will get access to the particular system, and based on getting access, it can either be identity theft, or it can be data theft, or it can be ransomware. But all of these attacks can be launched only when a particular hacker gets access to a particular system, and that usually happens via Trojans. Is everyone able to follow with me, or am I going too fast? Okay, I'll take.
It's okay. It's okay. Go ahead.
Okay, I'll sure. So, and then the other type of software is the spyware, which is usually software that is used for recording the activities of a particular user. The user does not know that there is a software that is actually monitoring him and is actually monitoring each and every activity that he is performing using a system, and that is in turn the information is sent to the hacker so that he can take advantage of the user. So that is the spyware. Adware is the most common feature that you see in third-party websites, meaning websites that are not of good repute. So usually advertising software, it is used for it is a pop-up that once a particular user clicks on it, it is used for downloading malicious software. The botnet is basically a type of malware that will take control of a particular user system without his or her approval, and then the bot will start performing tasks based on based on instructions from the intruder. So that is a botnet. Basically, the user system will become a slave of the hacker. So that is a botnet. Then let me quickly go through the other types of cyber threats here. The man-in-the-middle attack is basically a person who is intercepting communication from the user. So when a communication is sent from point A to point B, the man-in-the-middle attack is when a particular person intercepts communication from point A and decodes that information, and he tries to misuse that information. So usually the information, when it is sent from point A to point B, it is intercepted, and again the information is sent to point B. But the intercepted communication is also used by that particular man in the middle to take advantage of the user. So mostly how it is used is unsecured Wi-Fi. So that is the most common way in which man-in-the-middle attacks take place, public Wi-Fi. So usually that Wi-Fi network will be compromised, and if a particular user connects to that Wi-Fi, when he sends receives information, that information is also sent to the hacker. Then DOS attack. DOS attack is the denial of service attack. It is usually targeted. It usually targets systems and servers. So basically, let us assume that IRCTC is a website. So in that website, if a particular person decides to launch a denial of service attack, it is targeted to ensure that the function of that particular portal does not happen properly. It is not able to function properly. So that is why DOS attack is launched, so that the service is disrupted. And so coming back to the research topic, the main objective of the study is to have a detailed understanding of the security breaches in the American health sector. This is achieved by collecting data from the various care providers in the United States, vital data that is gathered from security firms. For example, I have taken cyber security wings. This is the organization from which I collected the data, and then the data is used, of course, secondary data is used for this particular purpose, and then it covers various industries, and between the years of 2019 and 20. So 2 years data set I've taken. What are the main objectives of the study? The main objectives of the study is to understand the magnitude of the cybercrime incidences in the American health sector, to understand the type of breaches and the point of breaches. First is what is the type of the attack that is caused, and then the point of breach, meaning through which way the hackers attack that particular health company. So, and the other than that, to study if there is an association between the business associate and the type of day in which the attack takes place, the type of breaches, and the point of breach. So is there any association between these? So that is the third objective of the study. So in this illustrated graph, we can see that based on univariate analysis, we can see that the hacking corresponds to the large portion of the breach, the largest portion almost. For the 2 years that we have taken, 75%, 71.7% directly corresponds to the hacking incident. And then coming close second is 18.5, that is the unauthorized access, which forms the second largest percent. Theft is comes at 6.1%, which is the third most common type of hacking. And then the theft can be even subcategorized into data theft, and also identity theft, of course, comes next, which is 1.9%. And so from the graph, we can conclude and say that 71.7%, that is hacking, corresponds to the largest portion of the hacking corresponds to the largest type of cybercrime within the American health industry. 1 minute. I have somehow lost control. Okay. And so again, this is regarding the point of breach. What is the most common point of breach that is being used? So we can see that the most common point of breach is the laptop and the desktop. Almost all electronic devices, those are the most common type of using those devices only, the most common type of breach occurs. Coming in close second is the email. Most of the time, emails are also being used. That is again 30% of the overall incidences. And of course, below less than 10% is the physical what do you call it, paper trails, improper disposal of company property. So using that route, hacking happens. So that comes third, but that is less than 10%. So coming to the non-parametric tests, the first hypothesis is to check if there is any association between the presence of a business associate and the incidence of cybercrime. So you are basically checking if a cybercrime occurs when there is a business associate physically present within the company, or if it happens at a place where there is no supervision. So from the chi-square test, we can see that there is a close association between the business associate and the type of incidences. So at 60.3%, we can say that from the total person, 60.3% of cybercrimes occurred during the absence of a business associate. So only when the system is not monitored and it's not supervised, cybercrimes, the chances of it occurring is very high. And it can be inferred that the lack of employee presence is conducive to the cybercrimes that occurs there. Then there is the second hypothesis. Excuse me. There is the second hypothesis, that is there any association between the point of breach and the cybercrime. From the analysis, we can see that there is a strong association between the point of breach and the cybercrime. First is we can say that 53.8% involved network servers, desktops, laptops, and portable devices, and that 37.5% of the breaches occurred via email, while 8.7% of the breaches occurred via the physical.
Dr. Abhinav,
yes,
your time is over now.
Oh, okay. Okay, I'm also almost done. How do I unshare this? Can anyone help me? Oh. Yeah. Thanks for the opportunity, everyone.
Thank you, Abhinav, for the wonderful presentation. Now we have time for question. So if no question, time is also running out. We will go for the next talk by Dr. Roy, Ujjwal Roy.
Yes, sir.
Yeah. Okay.
Yes. Good evening, all. So, am I audible clearly?
Audible. Please put your presentation.
Okay. So, screen is clearly visible.
Yeah. Please carry on.
Okay.
Make the PowerPoint more enlarged. Yeah, full screen.
It's already full screen. Okay. So, I am Ujjwal Roy, a PhD research scholar, Department of Statistics, Central University of Odisha. So, today I present use of genetic algorithm in type 2 progressive censoring scheme. These are the contents. So, introduction. Now, with rapid advancement of technology and increasing global market competition, manufacturers naturally intend to produce high quality product to satisfy customers' expectations, to perform their intent function for which it was designed without failure for a larger period of time. Manufacturers often pay heavy penalty because of non-fulfillment of customers' requirement. So, for this purpose, we need some live testing experiment. So, what is live testing experiment? Live testing experiment are designed to measure the average life of the component or to answer such question as what is the probability that the item will fail in the time interval T0 to T0 plus T, given that it was working at time T0. And come to the different censoring scheme. In type 1 censoring, there are several censoring schemes. So first, the type 1 censoring scheme, the experiment continues up to a pre-specified time x0. The problem with type 1 censoring is that a significantly less number of failures, because the number of failures to be observed is random, may lead to a poor estimate of the model parameters of interest. In type 2 censoring, the experiment is continued up to prefixed number of failures. In this case, although the fixed number of failures provides a relatively good estimate of model parameters, but the termination time in type 2 censoring is random. In most of the case, three general censoring schemes, namely hybrid, progressive, and progressively hybrid censoring schemes are used. Type 1 and type 2 censoring schemes are special cases of these three general censoring schemes. This is the schematic representation of type 1 hybrid censoring scheme. This is the schematic representation of type 2 hybrid censoring scheme. Next time to the progressive censoring scheme. One of the drawbacks of type 1, type 2 and hybrid censoring schemes is that none of these schemes allow for units to be lost or removed from the test at any time point other than the final termination time point of the experiment. But sometimes units are lost or removed from the experimentation before they failed. Type 1, type 2 and hybrid censoring scheme are the special case of progressive censoring. This is the schematic representation of progressive censoring scheme. For practical purposes, we need some optimal scheme for the experiment. So the various methods are existing to determine optimum live testing plans under different censoring scheme. Most of the work has done to considering different information measure as the optimality criteria used A and D optimality criteria, variable neighborhood search algorithm, etc. But all methods considered small values of N and M using exhaustive search method. To overcome these difficulties, we use the genetic algorithm, in short, GA. So GA is a meta-heuristic inspired by the process of natural selection. The whole algorithm can be summarized as: first, randomly initialize the populations; second, determine fitness of population; and third, there are several steps. Actually, select parents from population, then crossover and generate new population, then perform mutation on new population, and then calculate fitness for new population. This process is continue until convergence is done. Convergence is occur. So in our problem, we consider fitness function from this equation. Following the idea of Bhattacharya et al. In 2014, we introduce a cost function associated with the live testing experiment under progressive censoring scheme as given by Zayer, and represent like this, where C1, C2, C3 are cost per unit failures, cost per unit of time for the duration of the experiment, and cost of imprecision of the estimates of the unknown model parameter respectively. Here, T is the random variable representing the duration of the live testing experiment. To use genetic algorithm, we actually use the real coded genetic algorithm. So our fitness function is this equation. Then to select parents from population, we use some selection methods. Actually, there are several selection methods are there, like Rowlett-Wheel selection methods, the rank selection methods, tournament selection methods. So in our problem, we use tournament selection methods. And second, to generate new offspring population using crossover. So crossover also, many crossover are there, like linear crossover, blend crossover, and simulated binary crossover. In our problem, we use simulated binary crossover. For this, we fix a spread factor and some crossover probability, then use the SBX crossover. Then we perform a mutation on new population and calculate fitness for new population. In our problem, we use some polynomial mutation where we fix a mutation probability, and then this process is continue until we reach a convergence. In conclusion, in this work, we have proposed a meta-heuristic algorithm which has an advantage over the complete search method in the sense that the proposed algorithm can find near optimum schemes for moderately large values of N and M with less computational burden. Okay. These are the references. And thank you.
Thank you, Dr. Roy, for the nice presentation. Now, if you have any questions, you can ask. No question, Dr. Sadish Kumar, we can wind up now. So thank you for the opportunity to witness such a nice session. I am particularly thankful to Dr. Thomas Matthew for presenting the award-winning paper here.
Oh my God.
And Professor Kanjan Jain, and her presentation was nice. Good theoretical context as well as applied biostatistics methodologies also. Thank you, Dr. Sadish.
On behalf of
And I am thankful to the ISPS office bearers, especially Professor Balaji for giving the nice opportunity.
Yeah, on behalf of the Indian Society for Probability and Statistics and University of Kerala in particular, I extend our gratitude to Dr. Sebastian for nicely chairing this session in a beautiful way and concluded within the time frame. Also, let us give a big clap to our Thomas Matthew and Kanchan Jain and other speakers in particular. Yeah, all contributing speakers. Thank you all for your support to this conference. Now I hope we can conclude this session here, and all of you are please join to the keynote address there at the 9:45 in the main venue. There the MCMK 2 Professor Hiralal Kaul's keynote talk is there. All are welcome to join there in before the time.